Miss you, Stella here. Want to test video?
Hello, folks.
Hello.
Hey, Terry. Yeah, I'm still preparing.
No worries.
Well,
Can you see my screen?
yes.
Okay, then I will stop. Tested, we're good.
Well,
Unless something unknown happens, of course, that's always possible.
yeah. Unpredictable dynamic. Hello? Anomaly and Pocket, are you there?
Yeah,
Yes,
I'm here.
I can hear you.
Cool, cool. I guess we don't have many people in the Zoom. How about we share the Zoom link to the YouTube audience?
Yeah, I was thinking about it. It's your personal link, right? You didn't create the link just for the workshop, right?
I think I'm fine because I have a waiting room I can control.
Okay. Oh, this is live streaming our conversation.
Yes.
Yep.
Yeah, and once you put it on the chat on YouTube, you can't take it down, so your personal link will be forever there.
Oh, I see.
So I can
I
say
think
seeing faces doesn't really matter that much to me. I don't know how many people are on YouTube is not an audience. But I'm quite used to teaching where most of the students turn off their cameras for bandwidth issues. So
Okay. Yeah. Then don't share. I guess we can get started. Let me see. I'm gonna share my screen.
Yeah, we can wait for another minute or so. People usually jump in between talks and workshops, so give them a minute or so.
and unfortunately, you don't have a big name for the first draw. No, you should have had Efros go first.
Eddie, you are a big name. All right, let's see. Yeah.
Hey, Pocket and Bob, can you admit people when you see they are in the waiting room?
Sure, we'll do that.
Okay.
yeah, I will.
I think we should get started, and it is time. Let me, I don't know, present. Okay, so folks, this is an open world vision workshop at the CVPR. My name is Shu. I'm gonna make the opening remark here. First, I welcome all of you in Zoom in the open world. And I hope everyone is safe, happy, because this is a Father's Day. Of course, we are doing the virtual conference using Zoom and YouTube. You can see some folks here, and they are still working hard in Zoom to make sure that our workshop goes well. And in YouTube, please feel free to drop questions, but most importantly, enjoy the workshop and the conference. The goals of the workshop are to connect with people and exchange ideas. And we also make use of the opportunity to think about new opportunities and the challenges of computer vision in the open world. So the format is like this. We have invited speakers who will present their thoughtful thoughts. And at the same time, some of them are graciously joining us for a panel discussion. And we further have 3 teams from the teaser challenge to present their insightful techniques. Okay, we have a teaser challenge, and we want to express our special thanks to DARPA program. And DARPA program largely inspires the design of the workshop, the teaser challenge. And yeah, there are so many people, I cannot read out their names, but importantly, I want to thank Pocket and Anomaly who really make this teaser challenge happen. And I want to thank CMU Argo AI Center for autonomous driving research. They donate some money to host the challenge. Of course, even though we have so many sponsors, we don't have a monetary prize, but we will do next time. Even so, we have more than 20 teams participating. We have 3 teams who will present their techniques. So here are some of the keywords to attract you. They show success based on self-training, test time optimization, open world data, self-supervised learning, and contrastive regularization. We study many problems through the lens of image classification, especially when we want to study the robustness of a trained model to non-cast data that has some novel attributes, like a rainbow colored pickup truck to a vehicle classifier. And we want to study self-awareness of the trained model to novel cast data, like a dinosaur on the street. Of course, this won't happen, but this is just an example. Okay, so for the detailed schedule, please visit the website. You will see. You can also search open world vision in the CVPR platform, and you will see the schedule. Okay, for me, I'm gonna deliver some my personal flavor about the open world vision and what I want to talk about why do we care. Okay, let's get started. I want to say open world vision is computer vision, but emphasize the open world. So open world has not, but should have been embraced sufficiently well. To note, computer vision cares about the open world in its day 1. Here's some evidence. David Marr says the main goal of a vision system is to create a 3D representation of the environment to interact with it. If the vision system is a computer vision system, then the environment is the open world, and we should handle the open world well. Of course, there are many textbooks talks about computer vision, and all of them hint at the open world. Like a robotic vision system should deal with the environment, which is the open world, and the computer vision as a trick is to extract descriptions of the open world from pictures and videos, so on and so forth. So as we know, computer vision is too hard to solve. That's why we focus on specific sub-problems and put aside the open world. So we studied different approaches like a statistical learning, mathematical modeling, feature designing, and we study different tasks from a low-level edge detection, boundary detection to mid-level like a grouping, grounding, geometry, motion, to high-level like a recognition, the detection, segmentation. I think we are lucky enough to witness the great progress made by our computer vision community. And that paper shows the joint force of large-scale data, neural networks, and computes. So based on the joint force, we address different various sub-problems independently. And our solutions start to work at a scale. And the computer vision as a whole start to do good to human life and the real world. So I want to say that today it is a good time to call back the open world, thinking about new challenges, opportunities, and embrace the open world to create new opportunities. So I want to deliver some personal insight about the open world. Let's talk about the life cycle of a computer vision system. Usually in the literature, we set up a problem, we get some data, we design the algorithm, and we deploy the trained machine. And we hope that the different modules in the pipeline will handle different open world challenges. But this is not enough in the open world, because in the open world, our system has a cycle life. We do everything again and again. So here's my sort of a controversial claim. Our community has not thought enough across modules, but doing so will make sense of our research. I'm gonna expand on this point in the rest of my talk. I'm gonna do a little diving and analyze the open world data and say something about new opportunities and challenges. First, as we know, in the open world, the data naturally follows a long-tailed distribution. So I like this figure. This figure is not my paper, it's from another influential paper. Let's define a classification task. The data follows long-tailed distribution in terms of the class labels. And so in this figure, it says, oh, in the long-tailed distribution, we care about some classes, like we do K-weight classification. And within the K-weight classification for the very tailed classes, we only have a few training examples, and then we do few shot learning. But for many others, very tailed classes, we don't have data in training set, or we have only very few data that we don't think they are enough to create a specific classifier for them. Then we gather them as an catch-all open class. So from this figure, I agree that a long-tail distribution is the root of many problems, like a few shot learning, open set recognition. But what I think the figure is missing is the outlier data. So open world also has outlier data, which is almost at an infinite scale. I want to say that our community has embraced the outlier data more or less, but not enough. In some fields, we use outlier data to improve open set detection or out of distribution detection. So in this paper, they show to address out of distribution detection, we can get some outlier data and train a binary discriminative classifier, and that can boost the performance of out of distribution detection. At the same time, I want to argue that pre-training is also a way to make use of outlier data. For example, if I want to address medical image analysis, I grab an ImageNet pre-trained model, then the pre-training is using outliers. Okay, so here's my another controversial statement. It empowers the study of few shot learning or open set recognition without acknowledging the long tail and outliers. So this is so the next is an independent point. Forget about that earlier, but not much. So when we say open set is a rare data, is a crucial, and we want to detect them better and better, right? We want to find them through some open set or outlier detection algorithm, and we do some active labeling to label them, and we want to refine our model to do continual learning. So this is a cycle. We do this again and again in the open world, in autonomous driving, in some companies, Google, so on and so forth. But I have a question. Once we have enough data, like we have enough riders data for autonomous driving, should we split it into new fine-grained classes? Like we have a horse rider, we have a skateboard rider. So imagine that we do downstream tasks like motion planning, and the planning depends on the motion or categories of the riders. And then in this sense, we should split, right? To improve the safety of autonomous driving. So here, I want to argue that in the open world, class incremental learning should be formulated as class splitting. And the typical class incremental learning actually splits the open class or outliers into new classes. And this is different from the typical view of a continual learning or class incremental learning, because they always add new classes without modeling the open class. Okay, I don't have time. Okay, almost there. So this is the end of my talk. I have some takeaways for you. First, of course, this is the only one. The natural long-tailed data distribution is the root of many problems we care about, like open set, few shot, so on and so forth. And the long-tailed data distribution is the right place to address them. We should not ignore the nature of the long-tail distribution. And I wish I could have time to expand on many points here, but I will do so in the future talks. But I'm open to discuss offline after the workshop this week during the CVPR. Okay, so I'm done here. I'm gonna introduce the next speaker, Terry Boult. So Terry Boult is known for open set recognition, open world recognition. He's the pioneer in this field. So let's welcome Terry. So Terry, please take over.
Okay, let me start my video. See my screen now?
Yes.
Okay, so Quo Vadis really just means where you're marching to, where you're coming from, where you're going. And so this talk is about where I see open world learning going. So on the first bit here, there was a QR code and a URL. I'm actually asking you to do a quick survey to answer a question, which I'll get to on the next slide, that I'm going to use later on in my talk when we talk about how we measure some open world learning. So this QR code, right, if you want to scan it or just type in, it's relatively short, etc.ch/FO_GT for forget ground truth. But we'll come back to that. So in the survey, there's really just it's one question where you can pick up to 3 answers. What should we do? Maximize the accuracy on knowns, maximize the accuracy on unknowns, weigh all classes equally, weigh all instances in the data set equally, maximize the probability of correct ordering of all scores in our system. So just trying to get your feedback on what do you think is important. So that survey will be up for a little while, and I'll remind you a little bit. So I'm going to talk with a little bit about why I started researching open set and open world vision, talk a little bit about what closed set, open set, and open world mean to me, why feature spaces matters, what we did in the competition, what to measure or what not to measure in open set, and then some views on open world learning protocols and some new results in open questions. So hopefully my talk will have something new, something interesting, and something controversial to engage discussion, and at least some intersection between those 3 sets, but we'll see. Shu and I will definitely have some disagreements about what things are. So why I started doing open set research? Well, when I started moving my stuff, I've been involved in multiple startup companies. When I started deploying the stuff from the lab to the real world was really messy and had some very high operational demands. So in my second company, we're looking at deploying some surveillance systems. And if I, just running the numbers as we set out, our goals would have less than 2 false alarms per day, because if you have too many, the security guards will just shut the system off or ignore it. And looking at the number of pixels, the size of our targets, the number of frames, how many hours, how many cameras, we needed to have an exceedingly low false detection rate, like 1 in 10 to the 12th, right? And so you got to really think hard about how to design a system where you're playing with 1 in 10 to the 12th errors that you're allowed to have. And detecting things like moving branches, birds, bugs, animals, all of those are considered false alarms. Anytime I make the security guard go look at something that isn't real, they're unhappy. And we developed models for lots of this stuff for noise and shadows and clouds, but birds, bugs, and bags were killing us. So rolling trash bags were just impossible for us to predict what they were going to do, what they would look like. And so in the end, we ended up doing things with one set classifiers to sort of satisfy a bunch of what we needed to do. There's that URL. If you've joined us late, we're doing a quick survey there. But it turned out this was not a one-off kind of problem. The next company saw the same kind of impacts of unknowns in both visual recognition systems and in biometrics. So in our visual recognition system, we were trying to identify endangered animals, and they're small, they're far away, there are not very many of them, but you got to handle all the normal stuff, pose and lighting, which makes the problem hard. But then we also had to handle all these other things. Unknown random animals would show up, blowing trash, blowing objects in the world. And once again, I realized this is not an individual problem. This is a problem we're going to face in the real world. There's lots of things we will simply not know. There's no way we're going to know what's going to happen with them. And Some of the things we saw in both of these cases didn't make them infrequent. It just made them things we hadn't anticipated. So in the end, our lab ended up going down this path, and we defined closed set, open set, and open world, which I'll go sort of through, right? So the reason closed set is, that one's pretty straightforward, right? The boundaries between all the classes are closed. The partitions and all the space, they partition all of space, and everything is known. And if I have a small enough data set and I get my classes, things look great. But when I zoom far away in my feature space, there's a whole bunch of space. If I've used standard linear classifiers, I've labeled all of space. And things very far away from anything I ever trained on will now be labeled. And that was part of our problem. And you can do some things by doing one set classifiers, one class classifiers to make that a little bit better. We moved to this idea of open set, and we call it open set because the things we know about and the things we're interested in exist. But we don't actually know exactly where the boundaries of the classes are. The boundaries are open in the set sense because there's not a clear end to the boundary. It's not anything less than or equal to 1. It's like less than something, but we don't know what something is. And in doing this, and I'll get a little bit more formal on the next slide, we have to balance the open space risk, what happens when I label stuff far from my training data, and empirical risk. But that to me wasn't the only problem. And in some of our deployments, that was enough. But in biometric systems, for our watch list systems, we have to add people to the watch list. So it's not enough to train a classifier to say, these are things I know and everything else I don't know. That was, for some problems, that's okay, right? We were only looking for a certain number of endangered animals and endangered species. So we could have an open set classifier for that problem. But for the biometrics problems, we actually have to learn new people. We can't just ignore them all. We have to actually detect and learn new things. So in a sort of robotic system, this is a paper from this year from Pantali and all. But it sort of typifies the problem. I see things I know. I have to decide something is unknown, and then I'm going to have to go learn what that new thing is, do some incremental, and add it back in. And to disagree with Wang, I don't believe this is about long tails. This is a fundamental property of a problem that can be entirely a small number of objects in an indoor setting. And actually, I can see these objects every day. I've just never actually asked what a banana was. And one day I decided I want to know what the label for this. So we have to be able to incrementally go add a class within our space of known classes. Okay. Now, I agree there's an interesting question with respect to the long tail distribution. But to me, long tail distributions are about the natural world. And I can have an imbalanced long tail distribution in a closed set setting where I assume they're just logarithmically distributed probabilities and say the set is closed, or I can have an open world problem where there's a finite number of objects. A robot in Amazon really doesn't have to deal with an extremely long tail distribution. There's some things that it's looking for, but new products will show up tomorrow, right? New products will have to be added. So it'll keep having to learn new things and avoid the random junk, but it's not really about the long tail distribution. So some interesting questions we can get into in the panel there. So, and again, reminding you if you haven't done it yet, there's a survey there. Hopefully we'll see some results when we get a little further in talk. So open space risk is part of what we went on when we formally defined this problem. And I will say we struggled, by the way, to get these papers published in the beginning because people just did not understand what we're trying to get at, despite the fact that now it seems like a natural problem. So open space risk to me, open space is the space away from my training data. It doesn't mean the class doesn't exist over there, but if I've never seen an instance that far in that part of my feature space, then that's open space. And we define open space risk as, and there's a risk to labeling things, to labeling this positively to some known class because it's far from my training data. How far should I extrapolate? So we actually end up with a formal definition in some of our early papers where we define the open space risk as the integral over this space of how much I've labeled divided by the integral over some larger space, some ball around, just make it so we can do some of the math we wanted to. And this gave us a model of open space risk. And then using that, and I'm not going to go through the formal definition, I'm just going to put it up there so I can point to some bits. The important part here is this last bit, which is the open set risk definition, which basically says I have to balance the empirical risk over the classes that come from my known positive training samples and my known samples, and the risk from the function labeling parts of space unrelated to what it's supposed to do. And then, of course, there's some regularization constants that balances how much do I balance open space risk versus empirical risk. And that trade-off to me is very fundamental. How much do I label my open space? Every time I take an area of open space and label it, I increase my risk because it's far from my training data. Now, the idea of classifiers with rejections is very old, dating back to the 1960s. So you can, this is actually from the Chow's paper in 1960-61. And they had this idea of a region where you reject and a region where you accept. And around the classifier boundaries, there's always some uncertainty. And so they had these classifiers with reject. And in my view, just because I have reject doesn't make me an open set algorithm. If I don't bound the open space risk, I still have infinite open space risk, then it's not a truly open set algorithm. And when I first started out, I thought this was really important and insightful, and some people think it is, and lots of people think it isn't. And I can probably count on this hand the number of papers published in the last 5 years outside of my lab that have proven they actually bound open space risk. Almost no one cares. They just like the idea of calling it open space. They're dealing with open set problems, and they're not formally following this definition. And I'm not going to change everyone else's mind. They're going to use the words however they're going to use them. But in my view, bounding that risk is actually still very important if I want to have some properties I'd like to be able to prove. But we also learned that that became problematic. So now I'm going to move to the next part of my talk, why feature learning and overlap are critical. So this is a classic LANA++. Here's a feature space I've learned for the various digits. And when you learn this, at the top of your softmax classifier, the actual softmax classifiers are a bunch of planes that cut off for each class and say, this is, if you're above this plane in the right way, then you're in my class. And it's a complicated space, but all the planes are infinite. So formally, the open space risk here is infinite. And we were a little worried about that, and we're doing some of this work. But the real problem turned out to not be the open space far away, as you can sort of see here. So these black points are now a bunch of out of distribution letters that happen to show up. And here's where they map in our feature space. In this 2D feature space, some of them exactly lie on top of other things. Some are in the space between classes, but an awful lot of them are just obliterating. They're laying on top of or overlapping the class. And that's where we run into a lot of our problem. Because even if I take some of our open set algorithms like OpenMax or EVM, this is what the space they would label given the original class training data. They don't, the EVM will depend on if you've ever trained with no negatives. This is all just training with just the positive classes. You'll sort of see that the stuff is red is what's unknown. And most of the unknownness does not overlap with this unknown data. It also turns out to be relatively trivial. We've never published this, but it's, if I want to make any deep network into something that is truly open set, all I have to do is put a ball around it and say, okay, anything that's within this ball, I'm going to say is known, anything outside of this, and now it's finite, right? It's at least finite. But the real question isn't just, is it finite? Finite risk is always imbalanced because the empirical risk is finite and infinite open space risk is infinite. But here, what I have to worry about is where should these features be? But as you can see, the real problem here is nothing's going to do a good job of separating them because there's too much of this space where they exactly overlap with all of the classes. So we started looking at how to do some feature learning techniques, and this is from our NERC paper in 2018. With Alexei, who's my PhD student. Softmax, this is what I just showed you. Now you can say, oh, I'm going to use a background classifier. So I add a background class, I go train that, and now I can reject stuff. Well, yes and no, right? The black, it shows where these classes go if I did, after I do background class. There's still a lot of overlap. They've got their own little space, they've done better, but there's still a lot of overlap. And we came up with this idea of objective sphere, basically using the known unknowns to drive the class someplace else. And what known unknowns you use is very important. And then recently we actually scaled this, trying to do this on top of existing networks where we took some pre-trained VGG2 face network, added a sort of connecting adapter layers, did the training to push known faces outside the sphere and unknown faces and background things inside the sphere and get some training. So this shows that we can actually do this on larger scale problems. And if I look at the feature magnitude, you can sort of see the distribution for background and unknown in here and in the known classes. And in this region, the knowns and unknowns so overlap, they're very hard to separate. But if I come down here to the objective sphere, we've now pushed the background class way to the left. We've pushed the unknowns feature magnitude to the left, and we get better separation. This is also a useful place for us to sort of think about why one of the metrics we'll talk about in terms of absolute ordering can sometimes be difficult, because if I take a blurrier image, so a lower quality image, whether the person is known or unknown, lower quality images will tend to have lower feature magnitudes, will be harder to recognize whether or not the person is known or unknown. So the problem has multiple dimensions. And so ordering them just by looking at feature magnitude alone is not going to be enough. We'll have to do a little bit more. But by playing this game, we can then go in and produce a separation that's sort of meaningful here. So the first, I'm going to start with VGG, the basic face algorithm. Here's its performance. And this is what we call a DIR versus FAR plot. The detection and identification rate, because I first have to detect where the face is and then identify it, and those two cascade errors. And then, whoops, false alarms per image. We look at this per image because from a biometric point of view, that's really what matters. How often does it go off? And so VGG was good. EVM helped a bit, right? Especially in this part of the region of the plot. Worse over here, doesn't get anywhere near over here. So whether EVM is better than VGG2 depends on where in the space you're going to operate. By using the idea of known unknown classifier improved training, so we can take our softmax classifier from the original VGG2 and extend it with an adapter that just does background classifier using known unknowns and backgrounds. And that does much better. And if we use our objective sphere, we do better in some parts of the curve and not as good in the far right-hand side of the curve, which in my view is actually quite natural. In almost all problems, the right-hand side of the curve is where it is a closed set problem, and the problem becomes more difficult, more open as you sort of go to the side and care more about the unknowns. So there's a trade-off between the space. So now, and that's to sort of show you the kinds of ways we've been trying to address some of these problems. I'm now going to remind you one last time about the survey. So the survey questions, etc.ch/fo_G_t. And these are the sort of questions I'm looking at: maximize accuracy unknowns, weight all classes equally, weigh all instances, maximize the scoring, or include multiple measured conditions, and you can pick up the 3. So I'm going to briefly say a little bit about what we did in the competition. So first of all, with all due respect to the many good members who put this together, this competition is not at all, in my view, about open world learning. It is at best open set recognition, because I never have to learn anything new. It is simply, here's a set of knowns, and these are things we should reject. But I'm not even sure it's really an open set recognition problem, because the primary metric so favors closed world algorithms that you don't really see any of the open set characteristics. The macro top one accuracy of 413 classes with one unknown class strongly favors the knowns no matter what the unknowns are considered. For example, if I considered an algorithm that was 79.7% accurate on knowns and 100% accurate on unknowns, so it's perfect in all the unknowns, that system in the primary metric for the competition will be worse than a system that has 80% accuracy on knowns and 0% on unknowns, right? The performance is on the open part means almost nothing, because the primary metric is so far off. It doesn't even help that the evaluation system won't let you upload a new system that doesn't do better on the primary metric, which frustrated my students. But almost all the other metrics really are not that appropriate. And I'm going to talk about metrics next, so that's why I'm going to sort of use this to lead it. The CCR at particular FAR is a good metric, but it should, and I have already asked me, right, why is almost everybody scored a score of exactly 0? Because the focus was on the far right-hand side of the curve. What happens at the highest CCRs, which means I pretty much ignore the lowest, right? And so we have to look at when we're going to do metrics. So we submitted some things to sort of learn some stuff on our point of view. So we submitted 2 versions, which if you look in the scoring tables, right, are called total ET and balance ET. We ended up making, the names don't necessarily make sense. We were going to originally do 2 different things, but so the first one is just F1 scores. We use an F1 network trained on this, on the known classes, and pure softmax results is from the network. No thresholding in. So this is just submitted network. You get a score. We then looked at using, instead of submitting the softmax scores, using the energy functional from this recent NeurIPS paper, energy-based techniques for detection. And then we selected the threshold, so we have no false detections on the validation data, and that gives us the highest threshold we could use without having any false detections on the validation data. And between these two, there is 0 measurable difference of any kind. There's only one metric, AUPR, that shows a slight difference, but overall, there's nothing is statistically significantly different between them. So does energy help with this problem as the problem is formulated? No. We then looked at another technique where we added basically one of our adapter layers, an MLP adapter on top of it, and then we have 2 versions of that. one where we trained it using just knowns, which is the top two. And one of those we threshold, one of them we don't. And if we add a threshold, so we're throwing away a number of things, softmax thresholding now, we reduce our primary performance metric from 0.68 to 0.65. While we improve our micro accuracy, this is a trade-off between different metrics, what matters, how are they weighted. But our paired, we find no real difference overall across all the metrics. So using a non-trivial threshold to reject unknowns decreases performance on the primary metric with no significant change in the remaining metrics. So we don't gain much for losing on the original metric. And if I'm not going to gain much, then I'm not going to play that game. I'm just going to optimize on the metric. The last one, we tried to say, well, how much does this idea of using known unknowns help? But again, with known unknowns, we actually increased our primary metric from 0.68 to 0.69. Not a big change, but which is actually also the same 0.01 increase we got on the closed set K-class accuracy of the classifier. Again, going back to the point that what really matters here is, could we improve our closed set accuracy? And if we did, then we could do better. And again, t-tests on all the other metrics really don't show that background class doesn't help much. It doesn't actually help much with the classification of unknowns. It just really helped with the classification of knowns, and that's where we got our performance. So there's still some good things in the competition. We'll sort of see what we learn from some of those later. But in my view, part of what we've been struggling with is the distinction between what I mean by open world and what a bunch of other people mean by open world, but also what do we want to measure? So that's the next part of my talk. What we want to measure and what we don't want to measure. And the good thing is there's lots of things we can talk about here. This will stimulate some discussion. But when we're talking about measuring this stuff, we have to hit knowns and unknown fractions of data. We got to get those measured. In an open world, there's actually a cascading of errors. So we have to be very careful to put that in the right order. In our early papers in this space, we messed up. We didn't actually cascade the errors, so it made things look unrealistic. And then we have to look at what are these different costs of errors. So now let's see if this is going to, oh, darn. I was hoping this should supposed to be a live. Either no one has done the poll, but somebody's done the poll. Darn. I don't want to, I'm already behind in time. I'll just go ahead.
It was live on your first slide, I think.
I'm sorry, I've clicked on it. It just goes on to the next slide.
Yeah.
So, so there's lots of things that will go off, and I'll talk about what some of these mean, right? So the balance between these affects what metrics make sense. If I'm doing things like accuracy, then I have to assume things are balanced, and that these two are equally important. If I'm going to do F1 measure, these two have to be equally important. If the question of whether I weight my classes equally or instances depends on what do I care about. Do I assume all classes are equally occurring? Or if I have a long tail, I have to look at the instances, because long tails are not equally driven by the classes. The ordering of classes, I'll come back to, right? That shows up in some other things. So my answer, my hope is that most people would say include multiple measures. I don't know if that's the case or not. We'll see later at the end of the talk when I'll get there. So I'm going to first talk with why I hate AUROC or almost any other average or averages type measures. So the first and foremost, I deployed real systems. We had systems that were in theater. We had systems that were deployed at ports and whatever. Real systems operate at a setting. I have to deploy it. I have to choose a parameter and make the system run in a field and make it work. I don't get to average perform over different settings. I can't say, well, you know, if you take the average of these three different values, my system looks okay. So here's a classic example from our real data. Here's the data subset one, a couple of different system parameter tunings, right? If I look at the green one here, up down 0.05, it's not doing well in terms of AUROC. This is actually a DET curve, which is log, but in terms of AUROC, it would not be the winner. But if I look at data sets up two, which actually just collected more data, so now you can sort of see the false alarm probability plot extends way to the left. Before it ended at 10 to the -4. Now we're just going farther to the left, which needs more data. All of a sudden, as we get to low false alarm probabilities, that green algorithm starts to look a whole lot better. So what parameter I want to use, and the real value of an ROC and where it started was to help an operator choose a parameter in which to operate, not to decide which algorithm is better overall, because who's better over here, who's better on the left, and who's better on the right is very different. But the second reason, and maybe even to me the bigger reason, is that I don't actually just have one score threshold. That doesn't determine the primary means of adjusting performance for my algorithm. If I want to do something at very low FARs, I will probably combine information using probabilistically ands, this and this and this, so that I can reduce how often it can be true. Whereas if I'm trying to do very well on the far right-hand side of the curve and making it a convenient system, I'm going to use ORs, this or this or this. So I changed my algorithm to operate at different points. The idea that I just have one score threshold that goes from top to bottom just isn't the way systems are really developed, at least not the people I've talked to. Now there are people who want to say that AU-ROC can be interpreted as the probability that a positive example is assigned a higher decision score than a negative sample. To which I say, so what? Ranking and sorting is not my problem, right? It's not open set recognition. It's not why I care. So if that's what it's equivalent to, then it makes it very clear. That's not what I want to do, so I shouldn't care. Another problem is that even if I look at ROCs, they hide way too much. As the real world is rarely balanced, and in open set and open world problems, we don't know what that balance factor is. So this is an example from a website on some of this discussion, but not mine. There's three ROC curves here. They're exactly the same. The percentage of true positives are varying from 0.5 down to 0.01. The AU-ROC is the same for all three conditions. But if I look at the precision recall curves, I get very different behaviors between these three algorithms. So in this setting, average precision or AU-PR is more meaningful because at least it can differentiate the effect of the real world's balance. But it still suffers from why I hate it from numbers 1, 2, and of course number 5. Our problem is not binary, so we shouldn't be using ROCs and PR curves anyhow, right? And we can play some games to try and make them multi-class, but most of the ideas don't work out very well. So what have we been doing? So in our first papers on open world, this is from our first paper towards open world, we actually had top one accuracy because that's what everyone in the field likes. Not what I really wanted, but we have to get the paper published, so we have to use the metrics people accept. And then we varied the number of unknowns, the number of knowns, and we get this complicated plot. And there's a lot of data here, a lot of effort to put one of these together, but it highlights the things that matter. We were trying to show that we could do a good job as both the number of unknowns and the number of knowns, right, we're increasing, and we could understand what that trade-off space looks like. In our biometrics problems, we do these DIR versus FAR plots, right, because they help us understand how many false alarms you get per image and what's our detection rate. In our objective sphere paper, we introduced the idea of what we call an open set recognition curve. It's a little bit like an ROC, but instead of binary detection rate, we have the correct classification rate. And you'll see this is actually just a generalization of the DIR. The DIR had detection and identification. This is just the identification rate. And this allows us to draw some interesting things. But please, and I've already seen 2 papers doing this in the last year, don't do AUOSRC. It doesn't make any sense, especially if you look at an R plot, right? Almost all of the traditional area plot will really consider things, right? 90% of the weight goes on this part of the plot, but it's not showing what's happening at low false alarms, right? So it depends on what kind of problem you're looking at. And more recently, what you want to plot depends on what's important for your problem. If we look at true open world learning, where we're doing incremental learning, one of the important questions is, how does my detection accuracy from phase 1 help or hurt me at phase 2? And so this plot is actually doing that. This is a plot where we have the fixed UDA accuracy. And there's some interesting surprises to this, because increasing my unknown detection accuracy to higher percentages reduced my overall performance. Not intuitive, and some interesting stuff to show up in one of our archive papers. Finally, in our first paper, we were using openness, this measure that was defined to assign what's open. That's a bad idea. We just don't use it. It assumes things are just so far from true. Much better, we more recently introduced the idea of the wilderness ratio, which is simply a count of how many examples for unknowns divided by how many examples for knowns. And then in terms of impact, we've been looking at this new measure called wilderness impact, which looks precision and closed set divided by precision and open set -1. And then we can do plots of these things or tables where at a fixed recall, I look at my impact and understand what it is. And I was pleased to see there's a CVPR paper this year that's going to be building on these ideas. And then finally, the size and quality of your images and data sets matter a lot because things vary a lot. So this is a paper from the generalized Odin paper from last year. And in this, you can sort of see their baseline Odin, Manhalanobis, and then their algorithms performance across CFAR10 and CFAR100, which are both, in my view, toy data sets. There's some learning you can make, but you have to be careful because lots of things don't really generalize. This suggests that Manhalanobis is actually really good and probably better than the base than Odin, which is better than the baseline. But here's a nice plot from a recent PLOS1 paper by Rode et al. And here this is on ImageNet scale testing, and it's still a binary ROC, which has got its own problems. But if I look at something like the true positive rate up here, right, the ordering of algorithms would be like OpenMax, Odin, Softmax, Manhalanobis. almost the opposite of what you would get from these small problems. So you have to be very careful. Dealing with 1,000 class problems and a 10 class problem is very different. Dealing with 32 by 32 images is very different than dealing with 200 by 200 images and understanding what's going on. So in the words of Albert Einstein, everything should be made as simple as possible, but no simpler, right? Open world problems, metrics need to reflect the underlying problem. 30 ablation studies on a toy don't help me near as much as one meaningful data set. But most of us are just building tools, so we can't tie it to the problem. And we cannot simplify it better to a single number. So just don't do it. It's complicated. You got to report lots of stuff, but just don't do it, right? And I like to read AUXYZ as academically useless XYZ, right? We've made it useless by taking away the information we could have given you to a point that you can't make any decision about it. So now some quick things on where things are going and where our lab has been heading. So in our original definition for open world learning, right, we went through this process where there was some labeling of data. It's important if we want to do real open world learning that we only label the data we said we should label as opposed to just label everything. A more complicated protocol from one of our ongoing recent archive papers, right, goes through all the stages where you have to detect stuff, add it to memory, learn from it if you want to do new learning, and go through this process. It's a lot more complicated to build an evaluation model for this kind of problem, but you can do it. And there's actually a nice CVPR paper, again, not mine, coming out oral session 5. This is on the open world object detection. They've incorporated tables like this are complicated. You have to spend a lot of time to think hard about this, which has probably made it hard for these people to get stuff published because complicated tables take a while to parse as you're reading through it. Finally, as we go back to the closed and open world, where have we been going in our lab? So one of the things we've been looking at is how do we replace that labeling of data with just pure clustering? How do we move to open world learning with unlabeled data? And we've shown that supervised feature spaces help, right? If I actually do supervised labels plus self-supervised feature spaces, I can actually get pretty close to where I was going with just supervised labeling with labels, and actually do a little bit better than even using bad self-supervised feature spaces with labels. Don't help. So we need both labels and self-supervised things to do well. If we go to truly unlabeled spaces, learning with unlabeled spaces, we need metrics. So we have to mix some sort of accuracy unknowns plus some clustering measure on unknowns. And we've been able to do that. We get some interesting learnings out of that. So here's some where we added some ImageNet classes. We started with 1,000 classes of ImageNet and started adding stuff. And here's what it learns from the things that were added. So these are just some subsets of image clusters, but you can sort of label this one maybe as treetops. This one is yellow leaves and flowers. This one is trunks and feather-like leaves. Nothing wrong with these clusters, but these are not the names of what ImageNet would have used. These are not the ground truth classes in ImageNet. Oops. Because these classes are white birch, cork oak, white birch, chicote, I don't know what that tree is, gray birch, white birch, yellow birch. We've mixed up the types. The actual underlying labels are classifications, binary, botanist type biological classifications of different types of trees. We clustered them based on the visual features. So if we really want to start looking at these sort of more complicated open world learning without labels, we have to come up with metrics that allow us to evaluate the fact that the ground truth labels from humans were trained with stuff way beyond what our system has seen, and we're learning the best labels we can with a limited amount of learning. So it leads to some interesting questions. So to end up, where is open world learning going? In my view, it's opening up. It's being applied to a wider range of problems, and some very good, interesting work going on in terms of applying it in segmentation, applying it in object detection, in actual applications outside of vision where people are just solving the real problems in SAR or satellite image processing or whatever. There are still some people pursuing purely academic studies, unrelated, in my view, to the actual world problems. And there's still a bunch of people reusing the term open world to mean something very different. They really mean the natural world, but they call it the open world. The open world recognition learning needs to learn new classes and ideally improve its features, or it's not going to learn very well. In a meaningfully large context with metrics that lead readers draw useful conclusions, and not just claim that you beat the state of the art in some academic context. We really have to be trying to help end users figure out how to use our stuff, not just say, I'm better than that last group. So a little bit of controversy, hopefully a little bit interesting, and maybe some stuff that was new. So we have any time for questions? Because my timer was going, I lost track.
Well, thank you, Terry. We don't have questions in the YouTube chat, so maybe I just ask a quick one. So you're talking about open set recognition. Is that a problem of a feature learning, or is that a problem of a classifier designing?
Okay, so in fact, when we first defined it, it was very clearly, right, this is nothing about features. This is just, I have a classifier, and the definition of open set says balance your open set risk and your empirical risk. It didn't include the fact that this overlap happens, right? So this is problematic because there is not just open space, right? There's now, the same space has been filled with the unknown. So these in this feature space cannot be separated. So if I want to do better in this problem, I've got to find a way to improve my feature space, which is why we've been looking at things like objective sphere or concatenating or combining supervised features and self-supervised features, because it's different. And as hopefully we'll hear, like when Kate talks later on today, right? You can view this open world problem or open set problem as a little bit of a domain shift, but we have to be careful. The reason I defined it this way the first time with this, argmax over the space of functions was because I could not, or I'm just not good enough, right? I could not anticipate all the unknown things that could show up. And as I said, the frequency with which birds, bugs, and bags would disturb our system was not an infrequent tail kind of thing, right? We would have random false alarms when we first tried to deploy these systems dozens of times a day because birds would do things in front of the camera that we had never seen before. So we couldn't differentiate the bird behavior or the blowing trash bag from possible threats, right? So trying to minimize your risk by saying, I'm going to prove that everything outside of my feature, outside of what I know, is a good thing, but it doesn't help if your feature spaces don't separate. So the answer is, it's now both. If I want to do open set, I still have to learn features. The long tail, the towards open world, long tail open world paper, whatever it was from CVPR 2 years ago, right? Good, very good paper, and they're addressing an important part of the problem. Their problem, in my view, is open set because they didn't actually try and learn new classes. But the problem of rejecting classes also gets harder when my training becomes more and more imbalanced because the feature spaces become overly sensitive to the majority class and don't do a great job on the minority classes, and therefore the feature spaces are not well suited to handling the few classes that have to be added in there.
Thank you, Terry. I guess we have to hand over to Tom. So Tom, are you there?
Yes.
Oh, cool. So next speaker is Tom. Tom is an emeritus professor at Oregon State University. So Tom is one of the pioneers in machine learning, and he helped co-found the Journal of Machine Learning Research, and he holds many important roles in machine learning society. He has done great work on AI systems with thoughtful consideration of the open world complexity, right? So let's welcome Tom, and Tom, please take over.
Okay, well, thank you very much for the invitation to attend this workshop. It's already been fascinating. I always love listening to Terry. The work I'm going to describe today is the work of two graduate students. The first is Rishit Garapalli, who's now at Qualcomm, and Alex Geyer, who's a student working with me right now. And I think Alex will be going on for a PhD in some other place. So you should recruit him if you can. I also want to acknowledge advice from Alan Fern, Fuxin Li, and Stefan Li for the most recent work. In the past, I've also collaborated with Eric Morton and Sanisha Todorovich. So my motivation, like Terry, I came at this from application problems. So I was working with some entomologists who were interested in recognizing bugs, insects that live in freshwater streams. And it turns out the Environmental Protection Agency does a randomized sampling design every year of the freshwater streams, and they use this thing called a kick net. So this guy is trying to kick the stuff from the bottom of the stream into this net, and they bring it back. They collect the specimens, they bring them back to the lab, and then right now they manually identify them, which is very time consuming. And so we thought, well, computer vision should be able to identify these things. And indeed, our colleagues collected 100 specimens for each of 54 classes. And we achieved, well, really, Natalia Larios, who was a PhD student working with Linda Shapiro at the University of Washington, was part of our team. And she was able to achieve roughly 90% accuracy. And this was back in, the pre-deep learning days. So we were using pyramids of hog type features in those days. And this was great there, and we published several papers, but unfortunately, there are 76,000 species of freshwater insects worldwide and at least 1,200 in the United States. So when you get an actual field sample, it's going to contain new stuff beyond these lovely images of our known classes. So we have a problem of open world open, well, I would say open class, I guess in Terry's terminology, open set recognition problem. We don't really care about those other species, but we don't want to falsely label them as being one of our known species, because the labels are going, the predictions are going to be used to assess stream health. Also, we were using or trying to use an automated robotic mechanism for handling the specimens, and so we would also get non-bugs in there, like leaves, particularly small pebbles, little pieces of plastic trash, things like this. And so when we did tried some simple things to do rejection, we would end up with, say, a 20% equal error rate. So we were having 20% false alarms and 20% missed alarms in Terry's terminology. So basically, our classifier wasn't usable in practice. And I think we still don't have a solution, right, as a field. So, of course, the baseline method that people have been using for open, at least for out of distribution detection and anomaly detection, is to just train a supervised classifier and then rely on the learned representation of the penultimate layer and compute some measure that's basically a measure of uncertainty. So it could be 1 minus the probability assigned to the highest class, or the entropy of the predicted probabilities, or we find that the maximum of the logit values as it's smaller is the most useful indicator for one of those academically useless measures. But I think fundamentally, when I first saw this work, I found it very disturbing because, of course, coming out of a non-computer vision machine learning background, our algorithms in non-computer vision ML work very hard to discard all features that are not relevant to the task. And so if these deep classifiers were really doing the right thing in that mindset, then they should be discarding all aspects of X that are irrelevant to the classification. And that should make these measures fail, because they shouldn't have any information about the underlying, about the open space, right? So the big surprise was that this works fairly well. And of course, Dan Hendricks had this early paper on showing that it was a surprisingly good baseline. So in Rishik's thesis, we studied 3 questions. The first was, how well do these existing anomaly scoring methods, like these kind of anomaly scores here, how well do they extract the information that is captured in the latent representation? And so the idea was, well, let's train an oracle anomaly detector using labeled data to see how well it can use that latent representation and see what the gap is. And then the second question was, how well could any network with the same architecture perform on the task? So instead of training only on the known, or what we call them the nominal and the anomalous classes, because we're coming at this from an anomaly detection terminologically, an anomaly detection perspective. But it's the same as the open set problem in my view, that we would just use all the labels on our data and see how well that representation can work. And so for us, an anomaly is a open category, open set. It's and we think this is much harder than the out of distribution task, which I think is an academically useless task, to use Terry's terminology. I mean, the problems that we see are really as in our insect ID problem, maybe there's a mix. I mean, we have our 54 species of interest, and then there's the 1,200 other possible species. They're going to be very similar from a feature point of view, and harder to separate, right? And so in that sense, open set is very difficult. On the other hand, a bottle cap or a leaf from a tree is much more like an out of distribution data point, because those are the easy ones to detect. Okay, well, our methods were basically working with the toy data sets, as Terry calls them, CFAR10 and CFAR100. And what we do is have 6 classes be known and 4 be unknown, or in CFAR100, 80 and 20. And then we divide the data 60, 20, 20. And in the baseline configuration, only the known classes are in the training and the validation data. So then we train a classifier on the training using the validation data to tune hyperparameters and decide when to stop. And then we take the learned representation, calculate the anomaly score, and then calculate this AUC for the binary decision, is it known or unknown? We're using a ResNet 34 backbone, which is maybe a bit large for CFAR10, but necessary, I think, for CFAR100. And then we compare that to an Oracle anomaly detector. So now we take the validation data and label all the nominal classes as being negative examples and all of the anomaly classes as positive examples. And in this case, we trained a random forest of 1,000 trees using the latent representation as input. We chose this because first, it performed well, and also it doesn't require any tuning. And then we compute our test set anomaly scores and measure the binary AUC. And then finally, for the Oracle representation, we train the ResNet on all the classes and then use the learned representation with the random forest. So here are the results. And so what we see is that this is the performance if you use the anomaly score. We're using the max logit as our anomaly score here. So this is the sort of the realizable case. This is the AUC if we use the representation that was learned by the supervised classifier, but now we are using supervised information just to train an Oracle anomaly detector, in this case, that random forest. So we can see there's a huge increase in AUC there, which tells us that there's a lot of information in the latent representation that is not being captured by a score like max logit. And then if we train an Oracle classifier, there's additional improvements in the latent representation that can be obtained if you have labeled data. So there's still some headroom there to improve the representation. So this really says, at least on CFAR10, we have 2 problems: a problem of not being able to get good anomaly scores, and a problem that we should be learning better representations. Now on CFAR100, the story is the same, although it's not as stark. There is still clearly a big gap between what an anomaly score can extract and what an Oracle can extract. There's less headroom here in terms of our Oracle classifier. Of course, other folks with bigger nets or better nets, DenseNet actually seems to work better than CFAR or than ResNet on this. Can do better on the Oracle. But the big thing here seems to be there is a lot of information in that latent representation. It's not very accessible. So if you just try to use a linear Oracle, you don't see much improvement. So if we use the idea of a linear model as kind of how accessible is that information, we're not seeing it. And of course, each of the logits in a classifier is a linear model. So maybe that's not surprising. So then Rishik tried some hybrid network experiments. So of course, several groups going back, I guess, maybe to Naliznik or Oza and Patel, suggested using a shared backbone and then having both a classifier head and some kind of a reconstruction head. And people have been using autoencoders or deep density models, other things for this reconstruction. We just used a deconvolution network where we carefully controlled the capacity. We found it was very important to keep this relatively simple. But then we train on a combination of cross entropy and reconstruction error, and with this magic parameter lambda. And this trade-off parameter needed to be tuned very carefully for them. And we used the test set to do this tuning, right? So we're, or let's say, or the validation set, but using the labels of the unknown. So this is a, an Oracle type experiment, not a realizable real world experiment. So to come back to Terry's point, practitioners would not be able to use this. And the results here were that, now I'm showing those in the sort of orange. So there's a small improvement in terms of our the realizable case, but then the Oracle anomaly detector, this representation now has a lot more information in it, essentially matching the a classifier that has full access to all the classes on CFAR 10, and similarly for CFAR 100. So there's definitely a big gain from doing this. So so we're learning a better representation using this hybrid network architecture. So some reflections at this point. So one thing that again has puzzled me is several people have observed, and we have as well, that better classifiers generally allow simple anomaly detection methods to work better. And I say here, we have no theory why. Maybe I'm, that's not quite true. I think one theory is that that we're learning better representations. But again, that's a paradox, because I would expect the representation to become more specialized on the prediction task as we do more engineering on the networks. And so I would expect it to risk losing novelty detection power, but this seems to not be happening. And maybe it's partly because, I suspect it's because we're just getting lucky with over-parameterized networks. We have so much representational capacity that, that the networks just don't forget a lot of useful representational information about the input, because they're satisficing. They're just trying to get the information that is in the images compressed down into a form that is good enough to make the classification decision, but they're not really trying to eliminate everything else. It's not like an information bottleneck that says, well, I want to get rid of all of the other information that's in the image. A little parenthetically, it would be interesting to see if information bottleneck methods do suffer from this problem and would be very bad as anomaly detectors. So I feel like this pure supervised learning strategy is still based on being lucky with the particular characteristics of our deep networks. Having a reconstruction objective is theoretically much more sensible, right? Because the idea is that we're trying to create a task where the network will fail on the novel class objects, right? Now, but even there, obviously, a reconstruction objective can be tricky. If you train a standard autoencoder, which we found was very difficult, it tends to become just an image compression algorithm, and it can reconstruct novel images just as well as known images. So the trick is to set the reconstruction process up for failure. Then you have a theoretically justifiable technique. So the hybrid methods work better, but it's not obvious how to tune lambda. And from a theoretical standpoint, I think what is the supervised head doing for us? Terry also pointed out that having the supervised task really is important for getting a good representation. But is it just let's make this go away here? That was the wrong button. Somehow it's maybe regularizing the reconstruction representation to prevent it from just becoming a generic compression algorithm. I don't know. It's an interesting question. Another question is about input augmentations. As other people have pointed out, these often help. They certainly help classifier performance, but they also often help anomaly detection performance, which again is somewhat surprising, because you're making the network less sensitive to changes in the input distribution. More recently, my Alex Geyer has been playing with some other things, and in particular, a couple of things we found can do better than the supervised baseline. One is some of the ideas from this generalized Odin paper. The representational idea in the paper is that you take a softmax where you have parameterized the logits more interestingly. So H in the numerator is one function, and G in the denominator is a separate function. In our experiments, we used cosine similarity for H. So that's cosine similarity to a sort of class centroid, and a linear model for the denominator. Now, another idea from Odin was to do input perturbations, basically sine gradient method type perturbations. We didn't find those to be useful at all. And of course, you don't need to do temperature scaling. That was an idea in Odin. In G Odin, that's part of the G function here, basically. But these are good things about the generalized Odin approach, because now we don't need any known unknown data to decide on those things. So we see a consistent but modest improvement, maybe 1 percentage point in AUC. The other thing that works, unsurprisingly, is deep ensembles, although, and in particular, deep Stein variational gradient descent ensembles. But I think it is also, from a theoretical standpoint, a mystery, because if you don't have a good representation, why should ensembling improve things at all? Right? It's not clear that why the ensemble. What about the ensemble training is leading the different members of the ensemble to behave differently in the open space? I think Terry's picture showing that most of the things that are in the open space in the input representation are mapped into the middle of the representation space in the learned representation, in the latent representation. So it's really unintuitive. And in fact, here's a picture from this CSI paper from NERDS this year, and they found the same thing. They're doing self-supervision along in the Hinton family of methods. So instance level self-supervision against augmentations. And what they found was these blue points are the in-domain data, and the red ones are the out-of-domain data. And you see again, the out-of-domain data is going to the center of the space. And in fact, just using the Euclidean norm of the latent space representation is a surprisingly good anomaly score for this model. But it shows that our mental models of open space in the latent representation are really broken, and just underlying what Terry said. Okay, well, these are things we tried that we couldn't get to work. One was the idea of using geometric transformations as a self-supervised task instead of reconstruction. So, Golan and Elyaniv, Gedaris et al. So we used rotation. We also tried recoloring images, trying to reconstruct the edge detection map, but we couldn't get them to match baselines or exceed baselines for open set problems. And then we really had high hopes for the attack et al. This is this idea of contrastive learning on distributionally shifted image instances. So introducing augmentations that should destroy the class, that should change the class label. But we found this was very sensitive to the hyperparameters. I mean, they basically threw all kinds of different tricks at the learned representation. And of course, instance level self-supervision is very expensive also. But it shows some promise on some of our evaluations. And finally, we also had high hopes for the joint energy models. But we of course, this requires SVGD training, which is very slow, and we didn't see a payoff from that. So just to wrap up then, and get us back on schedule a little bit, as Terry said, I think our main problem is about representation. But we did see that the latent representations from supervised learning do contain information that we're not extracting. And so those representations in some sense are good, but the information is not easily available, for example, to a linear model. And as we see, the information may not reflect open space. And therefore, if we try to use the clustering strategies that Terry was describing, it's going to be really tricky to do clustering in that crowded area in the middle of the space, unless you have access to some known unknowns and maybe you can help learn that space. But my mental model is that for data that has a known label, our training pulls its representation out of the middle of the space, and everything else is still stuck there in the middle. Methods based on auxiliary tasks or reconstruction tasks are theoretically sound if we can get them to only succeed on knowns, but they are more difficult to train. And these hybrid methods show promise. So with that, I will stop and we can discuss.
Thank you, Tom. I'm gonna deliver one question from the YouTube chat. So
Okay.
Samuel asks, what is the latent representation used? Is that a penultimate logic layer? I might lose the context.
Yes, it's the penultimate layer, the layer prior to the logits, right? So usually after the global pooling layer. Yeah.
Thanks. Any other questions? Let me see. Oh, Hugo said Ensemble is good, but maybe we can consider multimodality data to do better, I don't know, auto distribution detection.
Certainly, but isn't that a sort of an orthogonal direction? I think we should think very carefully about our input data. And in fact, because we had the traditional machine learning mindset of trying to use only the minimal features that were necessary, in our insect work, we were not using color. Because when we looked at our known classes early on in the project, we decided, oh, well, monochrome images are going to contain enough information to solve this task. But the result was that when we would get things like the bottle caps or pieces of plastic or leaves that were very different colors, they would have been really easy to recognize and detect as anomalies. But because we had thrown away the color channels, we didn't have it. So I think that's another kind of an engineering question: is don't throw away information, and if you do have access to other modalities, keep it. Yeah, use it definitely.
Oh, the time is perfect.
Okay, great.
Thank you, Tom. So I'm gonna introduce the next speaker, Alyosha. Are you there?
Yep.
Well, yeah. Alyosha is a professor in UC Berkeley, and he has done amazing work motivated by the data delivered by the open world. Of course, for junior people like me, or maybe not me anymore, he's known for self-supervised learning, psychogan, so on and so forth. But for senior ones, not me, of course, he's more than that. Okay, let's see what Alyosha is baking in his lab. Please take over, Alyosha.
Thank you very much, Shi, for a kind introduction. And I have to warn you guys that I love these workshop talks, and of course I love it much more when it's in person, because they allow me to try different stories and kind of try to float some different ideas. So this talk is going to be really a lot about a new story. I'll show some research as well, but I think kind of what I want to have some input on is the story. Okay, and this is something I've been thinking about for a very long time, and I'm still trying to figure out how to talk about it. Okay, so first of all, let's be clear. Let's state from the start, there is no shame in closed worlds. Okay, closed worlds are fine. Antonio and I might have been part of the problem in kind of shaming closed worlds in our dataset bias paper 10 years ago. We said instead of helping us train models that work in real worlds, datasets have become closed world unto themselves. So what we talked about here really is the problem of mismatch between the world of the dataset and the world of the real world. Okay, so that's what we were kind of attacking. But actually, there is plenty of applications with no mismatch, in which case closed worlds is perfectly fine. For example, if your goal is to read checks or read zip codes, then MNIST is the perfect data set for you, and it's going to work great. You don't need anything else. You don't need to worry about any new digit arriving besides the 10 digits that everybody knows. Same thing for ImageNet. If you want to retrieve internet images, ImageNet is perfect. Even things, I would argue, something like self-driving cars might actually fall into this closed world regime because, okay, so it's a huge space, but it's a finite space, and it's not really a very much changing space. In fact, Andrei Karpathy recently mentioned that Tesla, just doesn't worry, about data. They have so much data. They have so many cars. They just have people label lots and lots of data, and they're fine. If you really think about this, there is about 8 billion people on Earth, but there is only 64 million kilometers of roads on Earth. So what this means is that we have about 100 people per kilometer, right? So out of those 100 people, if one person could be asked to label something, we're fine, easy peasy. We don't need to overthink things. The closed world may be fine. Now, where I think it's interesting to think about the open world is in the case of connecting this to evolution and to biological organisms. If for me, for example, I'm very interested in kind of figuring out how to learn to do things like a biological agent. And here, let's do this kind of thought experiment. Imagine that on some another version of Earth, evolution took a different course. Instead of evolving a brain, we would evolve a lookup table. Okay, so basically just memory, right? So you basically have this ginormous lookup table memory instead of your brain. It remembers everything, and it's basically doing nearest neighbor. Okay, and you could imagine that the more memory you have, the more you succeed. Now we know from Cover and Hart that this is, you can, and in the limit, this is perfect. You can get to Bayes' risk with k nearest neighbors. Okay. And you become like a perfect specialist because for the data that you have, you can do as good as possible. Okay, and contrast this to what actually happened on Earth, where instead of evolving a lookup table, we evolved a brain. Okay, now the brain is definitely worse than k nearest neighbors in the limit, for sure. Okay. We will not get to Bayes' risk. We make silly mistakes with our brains, okay? But it's kind of a generalist. So we are not great in any one task, but we're pretty good in many tasks, including tasks that are new tasks that we haven't seen before. And so now think about it this way. In which regime would a brain be better than a lookup table? Okay, to me, the answer is clear. It is it's if the world is constantly changing. If the world was static, a lookup table would make way more sense, because over time you will get this evolutionary benefit of remembering more and more stuff, because there is no reason why you have to, the lookup table could be passed from generation to generation. So you can have the whole institutional memory of your whole species, or even, from the very beginning, right? So ultimately you will get to the base risk, because you will have infinite amount of data. If the world is static. If the world is changing, nearest neighbor doesn't work as well, because you don't have that much data, because the data is changing so fast that you're going to it will get stale very fast. And so I think that if we are interested in the thinking about the open world, we really want to think of it as a changing world. Now, I haven't seen, I'm not sure what the evolutionary biologist will say about this. This is kind of my own argument, but I feel like from the computational point of view, it makes a lot of sense. And so now, if we want to think about the changing world, I claim that the changing world must be self-supervised. It cannot be labeled, because our visual world is constantly evolves, often adversarially, and the labels and the data itself, they become obsolete very, very fast. So here is our old work with Yingwei on just evolution of cars over the last 100 years, and you can see how large the change is just over 100 years, over like 2-3 generations. And yes, we can keep labeling, but that just kind of kicks the can down the road. It's kind of like now everybody is aware of how viruses work, and you can see that like outrunning evolution is very, very hard. But if we really want to emulate the animalistic brain, we must learn to prepare for this unknown future. We must be doing more than nearest neighbor. Okay. And so to be a generalist, in understanding must somehow continuously emerge. It should be very, very fluid, and it should be created from the data. The world needs to kind of self-supervise itself to create understanding. Nothing should be fixed. And this is my argument, that this is where self-supervision is really needed. This is really the key reason for needing self-supervision. So here's my 3 reasons why supervision can help. First is that self-supervision can get us away from fixed categories. Second, it can get us away from fixed data sets. And third, it will get us away from fixed objectives. Okay. And here I will briefly talk about all 3 of them. We'll see how far we go in terms of time. Okay, so first, fixed categories. So what are the problems with semantic categories? For example, you take category like chair from ImageNet, and you realize that this is a really, really hard thing to ask the computer to do. To basically look at all of these examples of chairs that have visually very little in common, almost nothing in common with each other, and somehow make them find something in common between them. That's what you're asking the computer to do. You say, okay, a category is about finding something that's in common. And here, there isn't really that much in common visually. What's in common is functional. It's affordances, right? And so we as humans, we have, we know how to squeeze our butts into places where we can sit. So we're able to reason about the connection between these things. But a computer, all that it's seeing is just a stack of images. There is no way, there is no reason why it would be able to connect those things together. So it's fundamentally unfair. Same thing for this category called city, which here there is a picture of Pittsburgh on the left and Paris on the right, and by some fluke of the English language, they are both called by the same noun, city. But actually, again, visually, there is nothing in common between them. the buildings are different, the windows in the buildings are different, the doors are different, everything's different, right? So the only thing that the poor computer can do is just try to kind of remember each one independently and just hope that somehow you get something at test time that's similar to what you've seen in training. But there is really no generalization going on, right? And this is why our systems have such a hard time generalizing, because we're forcing them to essentially memorize things instead of somehow generalize. And fundamentally, this problem goes all the way back to Plato and Aristotle, who gave us this classical view of categories as, something that's defined by a list of properties shared by all the elements within a category. And the argument, the Plato states that the category membership is binary, either you're in or out. Every member of a category is equal. And the thing is that this is just not true in terms of what humans do. Humans don't do this kind of categorization. People don't rely on abstract definitions or list of shared properties. Wittgenstein and Eleanor Roche have showed this beautifully. For example, Wittgenstein's famous example is, he asked, can you define all of the list of shared properties for all games? And it cannot be done. There is no such list. Things like typicality don't work. You can think about chicken is a bird, but when you think of a bird, you think of a eagle, sparrow, whatever, right? So this whole binary membership doesn't quite work. It's also language dependent. So for example, I speak Russian. So in Russian, there is no single word for chair. There are 3 words: stool, кресло, and табуретка. And so it's kind of bizarre if I were to train my my object detector in Russian, I would get different results than if I trained it in English. Shouldn't happen. And so in the 20th century, people have started thinking about a different way to think about categories. Instead of top-down categorization, people started to think about emergent bottom-up association. So prototype theory by Eleanor Roche, a great psychologist from Berkeley, was one of the first to propose this. And later there came exemplar-based methods that basically went even farther and said, okay, let's just start with instances and start grouping them together slowly into categories. And Moshe Bar has this good saying. He says, slogan: ask not what is it, ask what is it like. So this idea of associating things at runtime, on the fly, emerges a category for you instead of assigning it from the top. This is something that we have been trying to do for a long, long time. This is our old work with Tomasz Milashevitz, where we basically said, okay, instead of treating all category the same, let's say all cars are the same, let's see if we can learn per example distances for every instance. And so here what we try to do is to say, okay, this car, the focal example, let's find what things is it close to. And we can say, okay, so it should be something that's a car. So we want to find things that are similar to it that's a car, but not all cars. Like the Volkswagen bus, for example, shouldn't be close. And so we thought about 3 types of things. So we had, similar things on the similar side. We had dissimilar things that are basically not cars, but we also had don't cares, which are cars, but they're not cars that are too similar to our focal car. And so we basically trained this kind of per exemplar distance learning, and we showed that you can get a much more natural way to kind of group things into categories than if you just did standard nearest neighbor or whatnot. But of course, here we're still using the car category as a crutch. And so in the following paper called Exemplar SVM, we thought, okay, what if we don't use any categories at all? What if we just say we just train every instance against the rest of the visual world? So it's kind of like you're defining yourself by what you're not. Okay, and we basically ensembled all of those together. And what we showed is that this actually doesn't work so bad. This doesn't work worse than the kind of the classic traditional category-based classification. Just because the category is not really helping you that much. But here you're actually going to get kind of a category will eventually emerge. And we also showed how this would work in image retrieval as well. Then when ConvNets came about, we tried hard to see, okay, can we update this new stuff to CNNs? And we couldn't make it work. But Dostoevsky and colleagues did make it work with a paper called Exemplar SAM, Exemplar CNN, where they basically try to do this kind of per exemplar learning using using CNNs. And the trick that they use that we didn't have is that they didn't just take a single instance. They used a set of data augmented versions of that instance. So they created a bunch of fake instances to kind of to populate the positive space, and that's why it worked. And of course, that whole story led to the kind of the modern day explosion of similarity learning representations. Metric learning is started to be used for this, and of course SimesNet and most recently contrastive learning has really shown really cool results on this task. And here, of course, the reason why it's gotten so much better, this idea of you have your positives, which are data augmented, and then you have negatives. First, of course, is that the tool of representation learning has just gotten better. Contrastive learning is just much better than the old school stuff that we used before. But I think the second thing is maybe even more important and less appreciated, and that's that we have learned to do data augmentation better. For example, cropping, which wasn't in the original Exemplar CNN paper, is now a standard thing, which turns out to be extremely useful for things like ImageNet. Okay, but here, and remember, with data augmentation, what you do is you take an image and then you just create a whole bunch of various versions of that image by randomly doing perturbations like color changes, crops, flips, blur, etc., etc. Okay, but the thing is that the choice of data augmentation, in a sense, is in itself supervision. So a lot of these contrastive learning approaches, they sneak in human supervision through the back door by the choice of the data augmentation they do. And we pointed this out in this recent paper in iClear, that really depending on the task, the different set of augmentations is useful. So for example, for things like course level categorization, things like color augmentation and texture augmentation are very useful. But for fine grained categorization, like different type of bird, actually those augmentations will be harmful. Okay, and so there's a certain dance about how you pick which augmentations you're going to try to use. Okay, and so what we were really interested in is to try to see if we can get these augmentations from the data itself, again, to try and get the user out of the loop here and get the information from the data. And the data that we were very excited about is video, because the video data we know is one of the most important things for bootstrapping biological agents representation. We know that temporal information is the primary driver for bootstrapping all kind of visual representations. And so the idea was to see if we can learn correspondences across time, across video, and then use that in a gestaltist way to do grouping and to use this common fate as a cue to bootstrap and to have other things emerge as well. Okay, and hopefully get things like grouping also to emerge, etc. Okay. And so, people have done this before in various types of temporal coherence across frames, but this was all done on the per frame way. And then people have also tried to do this using tracking, but using off-the-shelf trackers. But we wanted to do it all in one end-to-end story. And so this is the paper we had last December in NeurIPS. And I'm just gonna give you just a very quick hint about what the idea here is. And the idea is basically, imagine that in the beginning that we had if we have supervision, and so for this kind of case, if we know, for example, that this blue patch is going to go to the green patch, we can just use this, feature distance learning to say, okay, these two patches need to be close to each other. But we can actually get a little bit more information because the intermediate frame, we have to somehow go through this. So if we can kind of track ourselves through the intermediate frame so that we can get to the correct patch, then we have extra data augmented patch, the middle patch, that we can also add into our positive set. Okay, so now we have 3 patches that are positive and everything else is negative. Okay, and of course we can go take it farther and farther. Okay, but now we can use the trick of cycle consistency to get rid of supervision altogether by turning our video into a palindrome, basically playing it backwards until the starting frame. And now, instead of knowing the starting and the ending points, all we want to do is we basically need to end up where we started. And now we have our correspondence, and we have all the intermediate points that we can use as automatic data augmentation to add into our contrastive learning setup, and then use them to learn our representation. And that's basically the idea. So we represent a video as a graph, and then we're basically doing a contrastive random walk through this graph, aiming to get back into the original thing, the green target. And basically everything that is along the path to the green target becomes a positive, and everything that ends up in the red targets becomes a negative for us. And then we just do this as a contrastive learning problem at every frame, and that basically is the whole story. It's kind of simple. And then here is some examples of this is a prior work, and this is our method. We can see that we're able to get better clustering and better tracking this way. And we also do better than even ImageNet pre-trained models for various Davis tasks. Okay, let's see how much time I have. Okay, so the second thing that I think is important is fixed data sets. Okay, what's wrong with a fixed data set? Well, again, real world motivation, biological agents never see the same data twice, right? Every new piece of data, it's first you tested it, and then if you survive, if you don't get eaten, then you get to train on it, right? And that's it. You never ever see it ever again. It's gone, right? Whereas what we do is we are repeating the same example over and over and over. And so that might actually encourage memorization, which is what we don't want. And it could discourage generalization. In fact, this might explain why data augmentation is such an improvement, because data augmentation is usually done at runtime, so you kind of get less of the sameness in your data, although of course the fundamentals are still the same. So the only reason for fixed data sets, if we think back, why do we have fixed data sets, is because of the annotation expense, because we need to label them. So if we are using self-supervision, why are we still using fixed data sets, right? There is no excuse to ever reuse data. If we don't actually need to have human labels, we should never use multiple epochs. We should just have this one pass online type setup, right? That's the right thing to do. It's the honest thing to do. Why aren't we doing this? All the other fields are doing this except us. In medicine and in polling and statistics, they're all doing this. We are still stuck on fixed data sets. Okay, so this is kind of the story of this kind of online continuous learning. We know that train val split works, but here all we are doing is we're basically doing a train val split where we are kind of the validation is the new data piece, and then we just keep doing it better and better. And so this is something that we tried to do last year, and we call it test time training, where we are using self-supervision to kind of address this, distribution shift, the domain shift story, by essentially saying that every time there is a test sample that comes in, that test sample gives us a hint about the distribution that we are now looking at, which is of course different from the distribution that maybe we trained on. And so if we include the test sample in our model, so if we adapt our model at test time, we should be able to get better performance, right? So it's kind of like a one sample training problem, like a runtime training. And we don't have the label for it, but we have self-supervision, right? So this is kind of the standard algorithm which we use, which is you have your standard loss, which is, let's say, classification loss. You have your bird here, like classification, and then you also have another loss, which is a self-supervised loss, and we just use the rotation self-supervised task just for simplicity. Okay, and then of course at test time we don't have the label for the main task. That's what we want, but we still have the self-supervised task, and so we just keep running that. Okay, and we can show that, for example, here is an image elephant that's different domain that the ImageNet that it has seen before. It's from video, I believe, and you can see that initially it think it's a dog, but as we run a few iterations of this test time training, the self-supervised task is forcing the dog down and the elephant up, and so you can see that it figures itself out. And the cool thing is you can do this kind of one sample at a time, right? And then kind of every new sample you just erase your memory and you start over again. But you can also do it in an online way where you are assuming that the data is changing, but it's changing smoothly. So what all you're doing is that every new data set, every new sample, you're updating it from the previous one that you had, and then you get even better results. And okay, I'm gonna skip all that. And recently we applied the same idea to policy adaptation during deployment. So at training time, we're doing things in simulation and reinforcement learning, and then we also have the self-supervised task. And then at deployment, you don't have the RL loss, but we still have this self-supervised loss, and so we're able to do things like this. So here it's trying to push the block onto the green thing and a red thing, and then in simulation, it works perfectly fine. But then in real world, it can also adapt itself to work well, despite all the distraction. Okay. Okay. So in the last minute that I have, let me mention the last thing, and this is the most kind of out there thing, which is trying to get away from fixed objectives. Okay. And so what's wrong with fixed objectives? Well, as most people here, I'm sure, I was in love with genetic algorithms in high school. I was very excited about this. And then, as again, most people here, I got super disappointed when I realized eventually that it's basically just another optimization method with a fixed objective function, right? And so that's why it doesn't do all the magic that I thought it would be able to do, because it's still optimizing the same fixed objective. And so that's kind of in contrast with the magic of evolution, where there is no fixed objective. That objective itself is evolving. And so that's kind of the cool thing, that objectives emerge. Even death is actually an emergent property of evolution, kind of a cool result. And so how could we get this emergent objectives in computation? And if you talk to biologists or economists, their answer is straight. It's arms races, right? And so what we are interested in is to try to set up arms races so we can get this emergent objectives. And there are several ways of doing it. Self-play is one way. You have an agent play with itself symmetrically or asymmetrically. Unfortunately, in practice, it's very hard to make it, not get stuck. And often you still need to specify the final objective. GANs, I think, is a great example of this kind of arms race. Unfortunately, GANs are not, we don't know how to optimize them, right? The discriminator is kind of always wins. So we don't quite know how to get this to work. What we are kind of excited about is the idea of prediction as a meta objective. And here, the open world is our adversary. The open world is a changing world. It changes, and we need to adapt to it. And one way of adapting to it is to try to predict this changing world. And this is kind of our story in Curiosity with Deepak Pathak and colleagues. But of course, what we really want to do is to try to do this for the real world, not just in simulation. Okay, so in summary, I talked about trying to get away from fixed categories and towards a data-driven association, to get away from fixed data sets and towards continuous lifelong learning, and to try to get away from fixed objectives and try to get ourselves some emergent objectives. Thank you very much.
Thank you, Alyosha. Okay, so why don't we just ask one quick question? I don't see any pressing questions in the chat, but I'm gonna ask one. I think perhaps the objective for human being or any animals is to do things more quickly, using less energy and more correctly. Do you think that we can model the objective in some machine learning language?
My understanding is that's not actually the objective. In fact, I don't think there is an objective in evolution. If objective was to reproduce the most quickly, then the mosquitoes would totally win out over us, right? Or viruses or something like this. I think the beautiful thing about evolution is that it actually doesn't really have an objective. You can you can see what happened, and you can look backwards and see what it ended up going towards. But I think the objective is fundamentally also emergent, and that's actually the magical thing about evolution. It's a very different type of optimizer than anything we have ever been doing. And I think once we figure out how to reason about this, that will be a great, we will be in a much better position to get generalization to work. I think maybe we should invite some evolutionary biologists here to really explain this, but I think it's quite tricky.
Thank you, Alyosha. We don't have time, so I have to introduce the next speaker, Ali Farhadi. Ali, are you there? So Ali told me last night that his internet may go die, right? So Ali, do you want to talk in person?
I'm here, but I actually am in transit, so it would be great to play the video. I'm here to answer questions.
Sure, cool. So Ali is an associate professor in University of Washington, and he did a lot of work in the term of embodied AI, which I see from the computer vision perspective that he used many modalities to solve vision problems, but he's done more than that. So let me welcome Ali's video by sharing my screen. Okay, I guess folks can see the screen. Can you hear?
No, we can't.
Okay, let me see how to share the audio.
I think you need to choose same as system under the microphone.
Oh, let me see.
Maybe.
how about now?
So you're seeing a recording of my talk.
Yes.
Yeah, it's okay.
Do I have a problem?
Yeah, I can't hear it. What again?
You have to play shoot.
Can you play it?
I'm trying, but it cannot play. Sorry, let
Can you hit the play button and see
me stop
if that
here.
works?
And
Yeah, you'll have to
do it
refresh.
again.
This means that I'm probably experiencing some internet. Specifically, I'm going to talk about two kinds of conventions and sort of seeing if you're overfitting to any of those. One would be overfitting to experimental settings in our practices, and the kinds of conventional wisdoms and practice or sort of practices that we, for the lack of a better word, inherited from the way we run our experiments and do our research. I'm going to talk about fluid as a way of actually sort of suggesting a different kinds of task to evaluate and see the gap between conventional tasks and this task. And talk about also going from instances to categories in LLC. And then we're going to talk about also overfitting to tasks and training algorithms that we use. And there we're going to talk about supermasks and learning neural network subspaces. Okay, let's start with the first question. Are we actually overfitting to experimental settings in recognition? What are those experimental settings? Sort of the way we actually split our train to test, the way we think about our categories, the way that we think about different tasks. And organically, when we actually look at how recognition, for example, evolved over the years, it organically evolved into subtasks. We started by grandiose goals of actually, let's do this generic recognition system. We realized, gee, it's too hard. We started to break it down into different subtasks. We started going after each subtask. And there has been great progress in each of these subtasks in isolation. We're all enjoying the benefits of actually that amazing progress. But aside from that, one thing that happened is that these subtasks started to organically grow independent from each other and ended up being isolated subtasks, to the extent that progress in one task might not necessarily mean progress in others. In fact, it might actually hurt in other tasks. And there are certain assumptions that we hold during our practices without actually sort of questioning those assumptions. We spend a lot of our time thinking about overfitting, and oftentimes when we talk about overfitting, we actually mean overfitting to training data. When my training and test distributions are different, we understand how to think about those problems and how to quantify overfitting problem, generalization problem. So this is actually a fairly well explored problem. But what I'm actually sort of trying to understand and talk about to you guys today is the other side of the story. Are we overfitting to tasks, to experimental setups, to the way that we actually break down our problems? And think about these assumptions that some of them might be far from realism, might be actually far from what we experience in practice. What are those assumptions? Some of them are fairly inherent in the way we practice our discipline. For example, we oftentimes assume that somebody is going to tell us at the end of the day that the task at hand is known and it can be categorized as one of the K tasks that we know. It's either a standard classification problem, or if it's not, it may be a zero-shot problem, maybe it's a meta learning problem, maybe it's a continual learning problem. And these problems oftentimes don't intersect. especially at inference time, you always assume that somebody is going to tell me that as a system deployed in real world, you are now facing a low shot problem. So go grab the low shot part of the algorithm and use that one. But that's a fairly strong assumption for any kind of actually real practices out there. And these tasks are isolated. Even if you tell me that this is a few shot problem, I still assume that the setup is in a way that I only have a fixed number of known classes, a fixed number of unknown classes. And more than that, I also assume that I have a fixed number of samples per classes. And that magical number, for some reason I don't understand, is 5. Same with continual learning and the kind of assumptions that we have in terms of the batch sizes are being fixed, the compute is available, et cetera, et cetera. So if we believe that there exists an overfitting of some form, meaning that there's going to be a gap between the accuracy of the results that we achieve on our benchmarks versus when we run them on a different task, then we can actually sort of start thinking about measuring that overfitting by measuring the gap. So what if I relax some of those assumptions and I start looking into gaps and see if there exists a gap? If there is none, then we all are going to be very happy because there's no overfitting. If there is, then we actually need to scratch our heads a little harder and start thinking about what can we do to fix the problem. And the problem is actually of two forms. We either are going to assume that whatever we do, we're going to overfit to something. Then we might actually think maybe we should overfit to a task that's at least closer to the real world task. Or maybe we're going to actually sort of find a way not to overfit as much to the experimental setups, and that would be sort of the nice and elegant solution. So one of the things that we're going to propose today is called fluid. So fluid is sort of a streaming approach to the problem where all of my examples are going to be in classification domain, but nothing is actually sort of wet to the classification paradigm. It's a more generic solution. And it's in the direction of a streaming solution. So you probably have seen many examples of which today. And fluid would be one more example in that category, where a learning system is going to observe a stream of data coming in. It has to make predictions on every single instance it receives. But instead of us forcing the learning algorithm to actually have this part as a training data, this part as a test data, it's actually up to the learning algorithm to decide what part is the training data, what part is the test data. Meaning that if you have the budget, the learning algorithm might get to decide to start retraining the model at every single data it receives, or at actually a different policy. But this is one of the decisions of the learning algorithm to decide when to train and on what data to train. The other piece is that the learning algorithm does not know if we're dealing with a low shot one or not one. If this instance that actually are coming, is this an instance of a low shot problem, or is this an instance of a continual learning problem, or is this an instance of a standard problem? And obviously, we don't know if this instance belongs to a known class or not. So a learning algorithm needs to classify if this belongs to one of the known classes. If not, should I invent a new class for it or not? And start making predictions as it goes. And also, it needs to be very aware of the budget for a computer. So that's sort of the fluid way of thinking. We want the learning mechanism, the learning systems to be as fluid as possible. They should be able to deal with whatever the stream through the input stream of the data through at them. As a result, they don't know what the problem is. And that's beautiful because that would actually allow us to be able to collectively understand, evaluate, and study all of these isolated problems: few shot, standard, continual, meta, self-supervised, auto distribution. All of them can now be studied under one umbrella of one task. And this is sort of closer. We believe that this is closer to the real world scenarios, or at least to many real world scenarios, compared to any of these isolated single task problems. And it also have a nice set of interesting challenges on how to train these things flexibly and efficiently as you deal with a stream of the data. There are all very nice and interesting decision-making challenges also along the way. Let's start by actually sort of practicing with this setup. The very first question that we would like to answer obviously is there an evidence of overfitting? And I'm going to go quickly over various examples of overfitting across different tasks. And the short answer is yes, we were drastically overfitting to the experimental settings. State-of-the-art solutions fail very, very badly compared to very simple baselines the minute that we switch a little bit of the experimental setups and relax some of those assumptions. For example, few-shot metas actually sort of, you see a big drop between the bottom two ones, which are sort of decent few-shot algorithms, compared to simple baselines in this setup when we switch from one task to the other. You would see evidence of overfitting in few shot setups where we're dealing with novel categories, and specifically when we have fewer instances of novel categories, and you see a big drop, 0.15 to 31%, and 31% comes from NCM, the bottom row here, and that's a fairly simple baseline here. So these numbers are worrisome to the extent that we should sort of start thinking and asking ourselves, are we actually making progress by working on these isolated problems? Because clearly, if you look at the benchmarks that we have per each of these independent tasks, we are making amazing progress. But when we put things together, then the problem becomes a little worse. The same thing with continual learning, and you can actually see the same phenomena that there's going to be a big gap between simple baselines and our state-of-the-art solutions. We're going to actually see the same students self-supervised learning. I'm going quickly through this for the sake of time, but there's actually a big gap between the way there's a big drop early on in the self-supervised solution. And all of these self-supervised solutions that we're using are sort of in these experiments are in the contrastive style. And you see the curves drop down at the beginning and then they start going up again. Another actually an interesting case where the self-supervised solutions also overfit severely to the initial pre-trained set. You can actually see these in these numbers as well, where these contrastive methods are going to actually perform poorly on novel classes when on downstream tasks, specifically when they have novel classes. All of them are actually sort of indicators of problems that we have in this space. Same with meta-learning categories of approaches. And again, you're going to actually see a gap there. The reason that we are I'm going quickly over these slides is I want to actually sort of be able to cover the rest of it, but I'm sure the slides will be shared and we can actually go deeper into the numbers. Obviously, you can also take a look at the fluid paper and see the numbers there. There's leaderboard there, so you can actually submit your algorithm and sort of test it on different kinds of data. There are multiple different streams of data. Images are coming from ImageNet, but they're coming in different variations. And you should be able to start thinking about submitting your new one. If you have a new shell algorithm, think about it as, now how can I actually place this specific algorithm for this specific situation into the context of a broader set of algorithms and problems. And this way you should be able to start thinking about seeing if there is progress or not. There are different evaluations. You can actually take into account the compute. There's out-of-domain distribution, different notions of accuracy, et cetera, et cetera. Take a look at the fluid GitHub repo. There's code, leaderboard, everything there. I'm going to actually shift the gear from fluid to the next topic. And then the next one that I'm going to talk about is a method that we called LLC. That's another actually sort of convention that we were trying to sort of question. And that convention is sort of in the directions of moving from categories to instances. We spend a lot of our time thinking about categories, but very little actually attention have been paid to instances. Specifically, when we think about real-world instances where we need to deal with millions of instances. Can we actually afford to have a network with million leaf nodes? Or there are other ways to think about instances. Can we find a way to encode both at the same time? Do we actually really need our standard 2048 dimensional real vector representations to encode these categories? Or there are better solutions along the ways? And one of the things that we're going to discuss about is these learned latent binary codes. We call them LLCs. Because they actually combine the class codes, the standard code learning solution, with also instance codes. So you start with your whatever backbone that you like, you pass in the input through your backbone of your choice. You have a k-dimensional projections, which k is way smaller than L, and then after that you actually have a binarized learned code book. These are, in this case, are class codes. You end up basically learning a k-dimensional binary code for your classes. We've seen examples of those before, but now we're going to actually sort of use those labels as target for your phase 2 classifiers. These are instance code learning phases, where again, you actually have this binarized bottleneck layer, which goes to sort of training k-independent binary classifications. And the setup is a multi-label setup. So when we start learning this, and I don't want to actually go through the equations for this, but what's going to happen is that we ended up actually having a very efficient and very, very tight set of binary codes. As a matter of fact, with only 20-bit codes, we could encode image, meaning that you could actually do image classification with very, very decent numbers. And I'm going to show those numbers to you in a moment, with only 20-dimensional bit codes. The other nice thing is that if you want, you can actually build decoders that are extremely light, all of one classification. If my learn codes are perfect, that means that I should be able to actually perform classifications with all of one. If not, I can actually do it with very light, like a Hamming distance or Hamming style decoder. I'm going to actually see numbers for that. But also you get very, very efficient retrieval out of that as well, because your code space is tiny. And out of the box, without any data, without any need to fine tuning, you can actually sort of do out of domain distribution. The minute that you see a code that you haven't seen before, you can actually claim out of domain distribution. Do these codes work? Yes, absolutely. So with 20-bit codes, you can actually sort of start building solutions that are very, very decent, 75% image and accuracy with a 20-dimensional bit code. If you want, you can actually sort of see the differences, the effects of the number of bits, etc. But that's sort of, I'll leave it for you to take a look at the paper to learn more about the details. They're very, very efficient and very accurate for retrieval as well. Comparing to HashNet and other greedy hashing algorithms, these solutions are very, very efficient and with very tiny bit codes, they can actually perform fairly well. You can even compare a very small 8-dimensional or 10-dimensional bit codes with the 16-dimensional or the same dimensional sort of real valued number and see the big gap between these numbers. So they're very, very efficient. They're very good at actually sort of encoding instances, meaning that you can actually build reliable retrieval systems with them. But at very, very least, if you have a larger scale problem, that means that you should be able to narrow down the problem into a smaller manageable problem and actually hand it to the second phase. Another very interesting aspect of this bit code is that they are very efficient for out-of-domain distribution detection. As a matter of fact, they just work right out of the box. No fine-tuning. You don't need to tune any threshold. You don't need to actually mess with your logic probabilities or deploy any kind of heuristics. You don't need to actually a few thousand data points to fine-tune to out-of-domain distribution. They just work right out of the box. And they encode the right taxonomies without going into too much detail. These codes actually, if you run a agglomerative clustering on top of them, you start seeing that the same kind of taxonomies that we expected are actually popping out of these tiny 20-dimensional bit codes. All of them suggesting that we're actually we should start thinking about larger scale problems going to instances and the kind of efficiency problems that we're going to deal with. And these LLCs might be one aspect of them. Okay, so enough of actually talking about the experimental settings and what we see. We talked about Fluid. Take a look at the Fluid website. play with the benchmark if you can, and also actually submit your models to the leaderboard as a way of actually sort of consolidating all of the effort across different isolated problems that we're practicing today. Now let's shift the gear and also talk about other forms of conventions that we typically deal with. And let's start actually just thinking about them as well and thinking a little bit out of the box and see what happens. So one of those is our tasks, the whole notion of task, and also the training algorithms that comes with those tasks. What do I mean by that? By training algorithms? Well, what is the standard way of training a model? We know that we actually have a network. We get the weights. We want to tune the weights so that I actually go from a loss landscape from a specific point as my initialization all the way to a good local optima that I'm happy with, and I'm going to actually claim victory. So there are two pieces into this part. One is that learning has always been to us. Learning means train the weights, and the connections are kind of given by the architecture. What if I actually flip the problem and take a look at the dual of this problem? What if I fix the weights? In fact, just throw a random generator at them and learn the connectivities and see what happens. And in a minute, you will see why I'm actually questioning this. The other piece is we've always been thinking about training a network as a point in a space goes to a point in space. Why? Can I actually train a whole subspace, a simplex, at the cost of training a point and move it from an initial simplex all the way to a final simplex that I have? And let's actually see what we gain out of this. So let me start by training weight. So in a standard neural network, I have an input, I have an output, which is f of x and a set of parameters. And all we do is start to find our way in our favorite SGD variant to go from theta all the way to my optimum. But we know that there might be other ways. And one of the key papers that sort of help us think along those lines was the Lotterer hypothesis taken. And the idea is that these neural networks, because they're over-parameterized, they actually contain sparse subnetworks. And some of them might actually get comparable accuracies. And this was sort of along the lines of there exist these subnetworks that might achieve similar accuracy. And if you think about these subnetworks, what are they? These are just binary masks, right? There exists this binary mask M, where when I actually mask a network with M and train a network, the accuracy of that network is equivalent or in the same category as the accuracy of training the standard network. The next step after the Lotterer hypothesis, the Lotterer hypothesis ticket was a deconstruction Lotterer hypothesis ticket. And the idea there is this whole notion of supermasks. And the idea is that initialization, these neural networks can actually contain subnetworks that perform surprisingly well, much better than random chance. And again, this is also another example of existential, not necessarily showing algorithms to improve those results, but this was actually a very interesting result by itself, meaning that you can actually sort of get, again, the same accuracy. And that got us thinking into what's actually hidden in a randomly weighted neural network. As a matter of fact, I'm going to actually sort of use a random generator, random seed, randomly initialize my neural network, and I would never ever change the weights along the way, but only to try to figure out these masks. Can I achieve networks that perform as well as those solutions? And the answer, and that's sort of the hypothesis, is that these masks do exist, and can we find one? And the main question is, how can I find such subnetworks? And it turns out that there exists actually sort of simple solutions to the problem. So for each edge that connects U and V in this fixed graph with a fixed set of weights, we're going to assign a score to the edge connecting the two. When in the forward pass, we're only going to use the edges that score at the top K% of the scores, and when we do backward, we actually backward all the edges, meaning that we actually allow the edges to pop up later if they need to. And that sort of allows us to start thinking about every step along the way. By doing that, are we actually minimizing the loss or not? And the answer turns out to be to be yes, if you're actually using the right set of stochastic conditional computations. One of them actually sort of at the bottom of this slide. The most surprising result to me was this one. Sort of what we discovered is that in a wide ResNet 50 with random fixed weights, we're not going to train anything out of that wide ResNet 50. It's just basically randomly weighted network at initialization, if you will. There exists a subnetwork that is obviously smaller than a ResNet 34, but matches the performance of a fully trained ResNet 34. By just messing with the connectivities, we might be able to actually discover a network much smaller than the original one, and it performs more accurate or in a similar way to the fully trained network. And that was actually sort of a kind of surprising results. And so amazing set of theoreticians actually got really excited about these results. They called it a strong lottery hypothesis, lottery ticket hypothesis. And there are actually a very nice set of theoretical results that are building upon this. I'm not going to actually go through this. Here are some interesting papers on the topic if you're excited about it. But the main question is actually at this point, you should be asking yourselves, why am I talking about this stuff? In what way is this related to the topic, and what are the conventions that we're questioning? Obviously, we're questioning the conventions in training these algorithms, but why should we care about it in the context of these networks, this workshop? So let's recap what we said. A neural network can only have one set of weights, but that is already fixed and frozen, or it's random, but it actually has countless subnetworks. This means that we might be able to actually start thinking about superpositioning these masks on top of each other, and each of which can actually correspond to a task by itself. That might mean that we might end up actually having one network that is just randomly weighted, and it's just there as a mother network, and superimpose large number of masks one on the top of each other, and be able to handle a large number of tasks without worrying about catastrophic forgetting. As a matter of fact, that's the kind of results that we actually sort of managed to show in these set of papers on the topic. So if we have a set of tasks, each of them are going to actually have their own masks, and if I see a new task that cannot be explained with any of the existing masks, I'm going to actually generate a new task, a mask for the new task. And that's the gist of the idea. So the very first point is that, hey, yeah, it works really well to the extent that you might be able to manage large number of tasks, in this case hundreds, with one network and some binary mask superimposed. That means that there's actually huge memory benefits to this. But aside from that, these networks work really well, and they're fairly close to the upper bound, 89 versus 92 in this case. An upper bound is sort of having an independent network per task, and much better than other solutions out there. But there's a big if here, and there are assumptions that we would like to relax one after the other. One of the assumptions that I sort of kind of swept under the rug so far is that I assume that at inference time, when an instance comes, I know which task it belongs to. What if I don't? And as a matter of fact, in practice, I should not know which task it is. Can we infer this? And it turns out that yes, we should be able to do that. And the trick is, let me just go through this quickly, but the trick is if I actually look at the distribution of these activations behavior and the behavior, we're going to see a change in the entropy of these behaviors, and that is a great indicator for us to know if this instance is one of the corresponds to a specific mask or not. That means that actually with the forward pass, I should be able to understand if this belongs to one of the tasks that I've seen so far or not. And if not, I need to actually figure out a new mask for it. And it turns out that actually works fairly well compared to other existing solutions. There's actually sort of a big boost in the way that this works. And remember, the methods that we're comparing with, they all know which task a data point belongs to, whereas the algorithm I'm proposing here, which is the red one, doesn't. There's still more assumptions that we can relax. The other one is, what if, and that's the one that to me is actually most related to the topic here, is what if the task information is also available during training? Can we build solutions that can decide when a set of known masks are not enough to explain what they're seeing, and they need to invent a new mask as a result of seeing a new task? And it turns out that this is also possible by, again, using the same trick. But what we're going to do is actually sort of occasional attempt to infer the task identity during training. And if we see uncertainty under some metrics, we can actually start allocating a new mask. And it turns out that the solution is actually, it is in fact possible to start learning new tasks and then their corresponding mask without knowing that the system is now exposed to a new task. And as a matter of fact, what we're showing here is we can actually deal with like 2,500 different tasks by using one mother network and these supermasks superimposed over each other. Okay, so this is sort of one piece of the training part, dealing with weights, dealing with connectivities instead of weights. The other part is sort of the one that I briefly mentioned. Can I switch the way we're thinking about it as training means going from a point to a point, but rather going from a simplex to a simplex? And let's start with a line and see what it means. So as we talked about, conventional training means that you can actually go from a theta 0 to a theta star, a theta t, and that's what training would get me. What if I actually want to move a line along the way? Instead of actually sort of moving one point, I now actually want to move a line. I have a line at the initialization, and I would like to move my line along the way to the optimal points. Why should I do that? Well, we'll see more about why, but to begin with, by doing that, what we're actually doing is we're trying to shape our subspace along the way and training that subspace the way we would like this to behave. So how can I do that? Let's start thinking about this. Obviously, I don't want to spend too much time training this, so I would like to find a way to move a subspace, to move a line in this lost landscape at the same cost of moving a point. Well, one simple solution might be so one way to think about this is that sort of these endpoints of these subspaces are going to be sort of points of high accuracy, and that's one of the things that we would like to we will show. And also a middle point of that line turned out to be a very, very good point as a single point, but also if you ensemble these methods, they're going to actually perform better than the standard solution. How can I train a line? So we can actually start from a point. You can sample an alpha. That alpha is going to actually tell you where you lie in that line. We're not actually going to line. Any parametric formulation of the shape would suffice, but in this case, we're actually dealing with a line. And then what we're going to do is we're going to actually pick that theta that corresponds to the point that came from that alpha and use that as a way to train the network. We're going to compute the loss on that and backpropagate. And we're going to actually start operating over that. One thing that we need to be very careful about is that we need to be very careful that we enforce the notion of diversity to regularize, not actually sort of go for the endpoints of the lines to actually collapse. And there are different ways to enforce that. I'm going to actually skip through this, but if you start thinking about actually enforcing orthogonality between these endpoints, that might suffice. Knowing what we know about the loss landscape and how the loss landscape look like for these neural networks, and we know that we have a good number of fairly flat local optimals, that means that so we should be able to actually find points across the point. We also know at this point, thanks to the other research, that SGD would actually get me to the boundary of this area, and it's not going to actually get me any point within the area. So if I actually have 2 points across this area, then the middle point should behave in an interesting way, and that's sort of the kind of results that we have. As I said before, we're not necessarily wed to lines. Any parametric form, it can be lines, it can be curves, it can be actually simplexes. One nice thing is that if you train a network, if I show these networks to you, you could actually easily tell me, if I show the loss landscape to you, you could easily tell me that what shapes did I pick to train these networks with. in the end, we're actually sort of shaping our loss landscape to behave the way we would like them to. And also, it is interesting because now we can actually start thinking about, does this actually work? Can I build a network? Can I build a solution that moves the simplex along the line and achieves good results? The short answer is absolutely yes. But let me skip through this for the sake of time for now. But yes, we actually sort of start thinking about, so these are tiny image results with the resonant 50 backbone. The dotted line on the top is a ensemble of two different solutions. You actually train two different networks, you ensemble them at the output space. The dashed line at the bottom is a standard, it's a single line. The solutions that we're having here is actually training a line, which is the blue one, or training a curve, which is the purple one. So in this case, this is actually sort of better than a single model. It's at the same cost of a single model, but it's still actually a little far from two independent models. But as a matter of fact, you can actually start ensembling these things together. But now our ensembles are at the same cost of a single model, but now are as accurate as two independently trained models when you ensemble them together. And that's very interesting results, because now we're training on these network subspaces, and now we can actually subsample from this trained simplex and form ensembles. And theoretically, you can actually form infinite number of ensembles and build solutions that are as accurate as actually, so better than multiple independent models ensembled together. So I think at this point, I am going over time. Let me actually sort of skip through a little bit of this. But let me actually sort of show you this results in terms of actually showing that if we keep training these ensembles, we actually end up solutions that work even better than a standard ensemble of two classifiers. In this case, this is the solid blue line that goes better than that. That's actually a line ensemble at 300 epochs. Meaning we can actually compensate for that by just training them longer, and we can actually get accuracies beyond the ensemble of two by the amount of time we spend to train one single model. So that's about it. That's sort of the kind of things that I would like to talk about. So we talked about sort of questioning the conventions, thinking about finding ways to evaluate our solutions in a more collective way, ensuring that progress in one task actually means progress in other tasks. We talked about sort of thinking about instances and how to deal with millions or hundreds of millions of actually nodes at the loss layer. We talked about questioning the conventional solutions for training. We talked about training the connectivities as a matter instead of the weights and what you gain by doing that. And also we talked about sort of messing with the way we train the neural networks and going from simplexes and training simplex and moving along the loss landscape. That's about it for now. Thanks for listening. I wish it was a real talk so we can actually interact in a better way. But till that point, great seeing you. Cheers.
Thank you, Ali. Let me see. So we are in lunch break now. So folks, feel free to grab your meal. Let me see, are there any questions? Yeah, I didn't see any questions in the chat. So Ali, you are still there, right?
I am.
Cool. Maybe I just ask another sort of an off-topic question. I like your fluid setup, which simulates the long-tailed or few shot learning and dynamic learning. I don't think folks from different modules or different subfields talk to each other much. Yeah, I'm not sure whether people accept the setup, or do you think there's a barrier among those fields? And do you think that we should move on slowly? Yeah, maybe you have some opinions.
Absolutely. So let me actually split your question to two parts. One part is technically, do I believe this is the right approach? Absolutely, I do believe this is the right approach. Logistically, what is the right procedure to start encouraging people to start to form the crosstalk across these sub-disciplines is actually sort of an important topic. To me, these sub-areas are made up, right? We actually sort of made it up ourselves. There is no fundamental reason behind them. They just organically evolved that way. And I do believe that all of us should actually collectively start encouraging the crosstalk across these made-up disciplines and start actually sort of asking the question that if I'm tomorrow proposing another zero-shot, few-shot algorithm with the standard old setup and show improvements on the benchmark task, do I actually show improvement or not? And I actually really want to encourage everybody to start thinking about that as a matter of a scientific discipline, to see, if I'm showing improvement, are we actually seeing an improvement, or this is actually an overfitting of various forms? So fluid or something else, I'm proposing one. There might be multiple solutions, but I actually want to encourage everybody to start thinking about these these boundaries, and encourage everybody to actually intentionally cross these boundaries, because at the end of the day, that is what encourage progress across the board. So you're muted if you're speaking.
Yeah, thank you, Ali. Why don't we take the break and have lunch?
Awesome. Great seeing you, everybody.
Thank you. I'll see you. I don't know when we start again. 20 minutes.
Yeah, let's start in 20 minutes.
Hey, Shu, that sounds okay. Can I set up my slides?
Yeah, please.
Cool. So let's see, so share the screen. And whoops. Hang on, I want to try to put my video on too. For some reason, I don't see those controls. Okay. You don't see the Zoom like window that I have over my slides, right?
I see the first page of your slides.
Okay. Yeah, you don't see any of the stuff from Zoom. Let's just check.
No. Hey, Derek. How's
Hey.
your day?
Good. How are you doing?
Good. Busy day.
Yeah.
So as we are recording, why don't let me introduce you, and you can start shortly.
Okay.
Hey everyone, we're right about time. So we are happy to have Derek. Derek is an associate professor in UIUC. He has done groundbreaking work in 3D geometry inference, scene understanding, and continual learning, so on and so forth. And recently, Derek has been thinking a lot about general purpose vision. And let's see what he's baking. Please, Derek.
Okay, thank you. I'm really excited to talk about this work. So I'm going to talk about some of the big challenges and some of the small but interesting steps that we've taken towards those challenges, towards general purpose vision. So I think we're at a really exciting time in computer vision where we can start to shift the goalposts in bigger ways than we've ever done. So I think what we have currently is we have some really great point solutions, abilities to detect objects in COCO, to classify images in ImageNet or CFAR, to recognize key points in action data sets, and so on. But this creates what the economist calls as an artificial idiot savant, where you have a AI system that's really good at doing something really specific, a very specific task for a specific data set, and the system doesn't generalize in the way that people expect. And that has ramifications for how well it can apply to a broad range of tasks. So as a result, they say, and I think it's true, the applications of AI have still been fairly narrow. What we want to do is create more general purpose vision systems that are able to learn a broad range of tasks over a lifetime, to continue to learn after deployment, and to just grow and be usable and predictable. So I see like three main threads towards getting to that big goal. One is in the architecture. So current architectures, we are either single task, or if they're multitask, you usually have one head per task. So you might have a branch for your COCO bounding boxes and the COCO mask, then another branch for CFAR classification, another branch for VQA on COCO, another branch for VQA on NYU, and so on. Instead, what we could have is one head per control, and the ability to perform a domain of tasks that are afforded by the controls and the inputs. So for a person, we can sense things through our eyes and ears and stuff. And we have controls, which are the ability to talk and move our bodies. And we can perform lots of different tasks using that fixed set of controls. So if I want to learn how to skateboard, I don't need to grow a new leg. I just use the legs that I have to skateboard. The other is in learning. So currently learning is largely batched. You train once, deploy, and you have that fixed model that's then making predictions. It's also heavily curated by the researcher, where we define what is the data that we're learning from, what are the annotations, what are the losses, what's the learning schedule, what are the hyperparameters, and so on. Instead, I think we need more continual learning, where you're learning even after the system is deployed. You're learning over a broad range of tasks, and the learning is self-guided in the sense that the system has opportunities for learning. It has data sets and annotations, interactions, simulations, and the system is choosing which of them to learn from and how in order to satisfy some longer-term objectives. And then the third is an evaluation. So we really teach the test and test to the teach in computer vision. So like in this cartoon here, there's some guy sits down in front of an HR specialist, and she says, I see you did well in school, but what real world skills do you have? And he says, tests, I can take tests. Well, if we put our vision systems there, they would say, COCO, I can detect 80 categories of COCO. That's what I can do. And so we need to broaden that evaluation. We need to be able to characterize the performance. Where do things work well? Where do they don't? Where do they not? The potential, how quickly can the system learn, and establish domains of expertise. So we need to think about evaluation a little bit differently as we get to more broad and broadly useful systems. So I'm going to talk about a couple of steps that we've taken towards this broader direction. One is in the architecture, where instead of doing one head per task, we propose a task agnostic vision language architecture, where using a small number of output heads, we can solve multiple different kinds of tests. The other is in evaluation, where instead of evaluating just the final accuracy, we use learning curves so that we can characterize and measure how the system's performance depends on the number of training samples. And this only takes us a tiny step towards the broader goal of general purpose vision. So the first work I'll tell you about is called, the paper is called Towards General Purpose Vision Systems. And I want to note that there's the paper code and demo are available at the link below. You can Google us and GPV or General Purpose Vision. Check out the demo. You can even do it while I'm talking if you want, if you're good at multitasking. It's pretty cool. I think it's really cool, and it's fun to see where it works and where it doesn't work. This is work with Tammy Gupta, my former student, now at AI2, and Amita and Ani, also at AI2. So the main idea is that instead of having a decoder per task, like for doing detection on each of the classes and for doing different kinds of classification and different VQA classes and so on, we instead have decoders just for different kinds of outputs, like producing bounding boxes and producing text. And a whole range of tasks can then be handled using those same outputs. So on the vision side, we basically have a Dieter style encoder. Which means that the image goes through a CNN backbone, it goes through a transformer that proposes a set of regions and produces transformer features on those regions. Those transformer features are pooled with the CNN backbone. That's like our own thing. Then for each of the proposed regions, it creates a bounding box and a objectness head that scores, like, does this look like some kind of object, or is it just like, you know, a useless box? Then on the bottom, we have, there's the other input is a task description. So in this case, it's describe this image, but it could be other kinds of tasks like what kind of animal is this, or classify, or you know, find the dogs or something like that. So it's a task description. It's processed through BERT, which converts this to a series of contextualized tokens. Then we have a Wilbert style coattentional model that is mixing and matching the tokens from the regions and the text to determine what is relevant to the task and to produce representations that can be further decoded into a text response. So it produces like a relatedness that can be used to score bounding boxes, as well as words that can be used to do classification, question answering, captioning, and other text kinds of answers. So using the same system, we can do different kinds of tasks. So if we show this image on the left and we say, what is the color of the cars? Then the system will say yellow. If we say describe the image, the system will say a busy city street filled with lots of traffic. If we focus on an object and we say, what is this? It'll say car. And if we say find all the cars in the image, then the system will try to detect all the cars. And these are not templated; they're just like natural language inputs. And if you try out the demo, you'll see that it's very flexible in how you phrase these kinds of tasks. So in our experiments, we did all of our experiments within the COCO data set. So and using available annotations for VQA captioning and objects. And training for any of the text kinds of answers, we have a log likelihood and how well the produced text matches the ground truth. And for bounding box predictions, we use Dieter's Hungarian matching algorithm. And for relevance, we use a cross entropy. So like one big difference between the way we're detecting things in a normal detector is that in a normal detector, you have like one output per class, where in our case, there's only one output, and what class that is depends on what the task is. Then we evaluate like how general is the architecture? Can we generalize the new tasks? Can we transfer concepts across skills? Can we learn new tasks quickly while forgetting slowly? So one part of the evaluation is just kind of an existence proof that given the image and given different kinds of tasks, we can produce good responses to all of these different tasks without having like task specific heads. So if you say, what color is the dog? It says brown. Are there trees being seen? Yes. Locate the dog. It gives you a bounding box of the dog. Generate a description. What is this? The other thing that I like is that every time it's producing, like when you ask it a question that requires a text answer, you also can look at like what regions did it think were relevant. So when it says what color is the dog is most relevant. When it says generate a description for the image, the dog, the bed, and the cat are most relevant, and it says a dog and a cat laying on a bed. And if you ask it, even if you say locate the object, it'll say something about that object often. So like it says locate dog, it finds a dog and it says 1. So I'll show more qualitative examples in a moment, but quantitatively, we wanted to first see, like, are we losing anything by using this single architecture to solve different kinds of tasks? So we compared to specialized models that are architectures specifically for each of these tasks. For example, faster RCNN for localization, ResNet for classification, some recent VQA system for VQA. And we found that our system, like when we train it on only one task, does about as well as each of these systems. When we train it jointly, though, it does better in most cases, with the especially better for VQA and captioning. And that's partly because localization and classification already have some strong annotation, while VQA and captioning can benefit from the strong annotation of localization and classification. So here are some more qualitative examples. And again, like what I really like is not just like, does it answer the question correctly, but you can see like, is it focusing on the right things? Or when it detects something, does it mention something interesting? So like with what is the woman doing with her hands, you can see the relevant boxes are, the most relevant is the we. There's also like looking at her arm and her body, and it says playing we. And when you ask what meal is this with the man down here, it focuses on the things on the plate and it says breakfast. If you say caption the image, then it also focuses on the man and it says a man sitting on a table with a plate of food. If you say locate all instances of cup in the image, it finds the cups and it says coffee, where one of them is a coffee cup. Here's some more examples, like generate a caption, a woman walking down the street holding an umbrella. Why does she have an umbrella shade? It's focusing on the umbrella. Find the umbrella, it finds it and it says black and white. So it doesn't always work though. So one of the problems is that it's not always consistent. So if you say, are there two people in the photo? It finds two people and then it says no. If you say here, generate a caption for this image, it says a man riding skis while holding two dogs. So it didn't really understand the relationships of these objects. It just saw that there were some men and a man holding with his hands up. And so it put them together and said a man holding dogs. Also, if you try out the demo, the system has limited knowledge because it's only seen Coco. So if I give it this, if I try to ask it things about this image with turtles, it doesn't do anything reasonable. And in fact, it thinks like nothing is really relevant. Because it's never seen images with turtles or been told that these are relevant for anything. So when I say how many turtles are on the log, it says 7, totally wrong. And also like all the relevance of these boxes is really low, like 0.02. When I say find each instance of a turtle, it gives me almost the same boxes, not great. And when I say what kind of animal is this, it's a monkey with 66% probability, 5% squirrel, 5% frog, 5% bear, 2% kite. So, I mean, of course, it's never seen a turtle or heard of it, so it's not going to say turtle, but it also doesn't know enough to say, I don't know. It doesn't have that ability. We did, the system can do zero-shot tasks, which I think is cool. So without training it further, after learning on VQA captioning localization, we do zero-shot referring expressions. Referring expressions is when you describe an object for which there's like multiple instances of that category. So you say like red across the nose, and the system is supposed to find the dog that has red across the nose. And the system can, so it's not just detecting all instances of a category, it's like using the description to find a specific instance. And the system was able to do that even without training, at least some of the time. So here it says, like if you say red across the nose, then it finds the dog here and it says leash, which is the red thing across the nose. But it doesn't always work, of course, shown as a failure example on the bottom left. If we found that if we trained, the multitask trained system got significantly better zero-shot performance by about 10% than the system that had only been trained to localize, which is the dashed blue line. And I'll get back to that referring expression experiment in a moment to show like speed of learning. But first, we also looked at how well can the system transfer concepts across skills. And the way that we did that is that we hold out some concepts from VQA and captioning and others from localization and classification. So for example, we might have like find buses and classify object and it's a bus, but no questions or captions that involve buses in the question or answer. And likewise, there might be horses in VQA and captioning annotations, but we never train to localize horses or classify them. And so then we can see how well do we do on the objects, on the categories that are seen for that model versus ones that are unseen. And the specialized model is, again, using like the state-of-the-art system for each of these tasks by itself. Unsurprisingly, it doesn't do that well on the unseen categories. one task GPV does about as well as the specialized model. So that's just training on each task by itself. But the multitask GPV in most cases does much better than both of them, especially for the unseen categories. So it's able to take the knowledge or the models that it's learned about these concepts from some tasks and effectively transfer it to other tasks. So the final evaluation that I'll show is looking at how quickly the system can learn and how slowly it forgets, or how quickly it forgets. So here we show that if you train with different amounts of referring expression training data, so the system was like initially trained with VQA, classification, localization, captioning. Then we don't show it any more of that data, but instead we show it annotations for referring expressions, or annotated data for referring expressions. On the left side is if there's only 120 training images total. And on the right side is the full data set, which will be about 120,000 data samples. And these dash curves are the zero shot. The orange curve is our multitask trained system, and the blue curve is if it was pre-trained on localization. So the multitask leads to faster learning. And then we also looked at how does the performance on the previous tasks degrade as we train with more and more data. And we see that some tasks degrade more quickly than others, but one interesting point is that the multitask system degrades more slowly than the system that had only been trained to do one task before. And this is even though we're not like specifically addressing like learning without forgetting the problem in the work, but just learning a broader range of tasks naturally results in slower forgetting. So there's lots more that we could do in this direction. So we could have more outputs like ability to control robots or use touchpads or produce segmentation masks or produce geometry. We need broader knowledge, for example, learning from webbly supervised data, self-driven learning techniques that can automatically select from training data. As you start to learn more and more tasks, this idea of like people controlling all aspects of the learning process becomes extremely cumbersome. And we want to be able to handle more complex tasks like video, longer range tasks that require recursion, and things that involve like simulation and interaction. So the second thing that I want to talk about, and this will be much more brief, is our work on using learning curves for analysis of deep networks. And this is work, again, with Tame and also my former student, Yu-Xiong Li, now at Amazon, and Mihal, a current student. So if you wanted to tell me, if I asked you which of these models is better, model A or model B, two classification models, what you would do is you would train it on some set of data and then test it on the test data and look to see which one's error is smaller. So in this case, it looks like model A is better because the error is smaller. And but this is only evaluating on one point in the curve. So we're only looking at how they compare for a particular size training set. But what if it's like automatically advancing. So let me just fix something. Sorry about that. Slideshow, yeah. Okay, so what if I want to know like which one learns more quickly, or how well would one do if I had more training data? So for that, I can train models with different amounts of training data, and then evaluate each of them and produce an entire learning curve that shows the performance as a function of the training size. And when I do that, I see that model A performs better than model B when I have a lot of data, but model B performs better than model A when I only have a little bit data, much better. And these, by the way, correspond to, this is on CFAR, and model A is a non-pre-trained classifier that's doing fine tuning, while B is a pre-trained classifier that's not doing fine tuning. So instead of just looking at the single point error, we want to better characterize the classifier performance with the learning curve so that we can see how its performance depends on the training size. So we want to see, for example, like how much does it rely on training data by looking at the slope of this curve, as well as how well does it perform given the full training set. And that gives us a lot more information to diagnose and to contribute. So learning curves have been shown useful in a lot of ways. It actually dates back 30 years. But there's still no established methodology for how to use the learning curves to evaluate your algorithms. Most of the work out there is doing lots and lots of experiments that would be way too complicated to include as like part of your paper that is not about learning curves. So our goal is to make it easy to improve the classifier evaluations with learning curves by showing you how to model, fit, and display them without using a lot of computation or paper space. And by showing that we also show that learning curves can provide useful insights. So for modeling, we find that this extended power law function works really well to fit classifier error. So where E is the test error, N is the number of training samples, which we usually do per class, and the other values are parameters. This model is well supported by theory, for example, bias variance trade-offs, and by practice, where other researchers have shown that this kind of model can fit classifier error well, or loss. We show that you can fit the learning curves using weighted least squares, where you step over gamma, then given gamma, you have a weighted least squares problem as a function of n to the gamma, and the weights account for the variance of the error observations. So importantly, we can fit them really well, even when we have very few error observations. To display the learning curves, we use 1/square root of n on the x-axis, and the reason for that is that gamma is typically close to -0.5, or like basically so that we have a square root of n, 1/square root of n, and this makes the learning curve roughly linear and also allows us to see the full range of training sizes. But one of the problems is that the parameters gamma, eta, alpha are highly covariant with error perturbation. So if you change your observed error a little bit, like gamma and eta may move a lot, for example, in opposite directions. And so you can't really compare like gammas across different learning curves in a meaningful way. So we reparameterize the curves as the error at the full training size combined with what we call the data reliance, which is proportional to the slope of the curve in this scale. And you can recover the original parameters if you also have gamma. So this beta n characterizes how the error depends on the training size. We can stably estimate it under perturbation, and it's easy to derive for other models. And so you can show the learning curves to, for example, show extrapolation up to some limit. And you can simply add another column to your experiment table to report the data sensitivity of the learning, which will help to show how the error will change if you add or remove training samples. So we also show some interesting comparisons. For example, comparing across different architectures, you can achieve lower error with less data reliance, which means that the more recent architectures make an even bigger difference when you have less training data. Looking at pre-training sources, we find that supervised ImageNet pre-training provides much lower data reliance than others for classification, which means that you see huge differences in performance when you have limited training data, but when you have enough training data, those differences tend to disappear. This is only for classification. As other papers have shown, other like self-supervised pre-training can work better than supervised ImageNet for other tests. And we also looked at things like the effects of depth, ensembles, width, and we find, for example, that features from deeper networks are better across a large range of training sizes. So for the learning curves, the summary is that in your own research evaluations, you can use our code, just train a couple of extra models with varying training sizes and report beta n and or show the curves to help show how your models are performing with a varying training size. And I think this can provide useful insights in your own paper. And I hope that you do find it useful. So finally, my takeaways are that I think it's time for us to solve really big problems of lifelong general open world vision systems. I talked about two components of that, one for the architecture in a task agnostic architecture for a vision language. The other is in trying to improve evaluation by being able to measure how a classifier depends on the training size as well as its accuracy on the full training size. But as I mentioned, there's many open challenges to architecture, to the way that we train systems, as well as the way that we evaluate them. Thank you.
Thank you, Derek. We do have a couple of questions in the YouTube chat. I'll read out one by one.
Okay.
So all those questions are from Amir. So the first one is that is this basically standard VQA with a head added for outputting bounding boxes?
So
when were you? Yeah, go ahead.
Yeah, so I guess, sorry, I'm trying to get to the architecture. Sort of, I mean, so the part, let me get back to it. Okay, so like if you just looked at the bottom row, that's almost like a standard VQA. In practice, a lot of VQA systems just say they're going to produce 1 of 1,000 responses, while ours is open-ended. But otherwise, you're right that this bottom row is a lot like VQA. Also, if you just look at the top row, it's a lot like Dieter, except that there's no categories defined here. So there's just like produces a set of boxes not per category. So in one sense, you could look at it as a combination of like Dieter and VQA systems. But I think what's interesting is that you can do different kinds of classification tests. So I could do like fine grain recognition of animals. I could deploy a system, and a user could train the system to do fine grain animal recognition, and then use it for that purpose without having any, making any change to the architecture, without adding any new heads, or even knowing what the system already knew to begin with. And so like the system can do any task, can potentially do any task that involves mapping from an image and a task description into bounding boxes and words or words. But there are disadvantages. Like one thing it can't do is it can't detect like 80 objects at once. So, special purpose systems have their special purposes. So a general system probably isn't universally better. But I think in terms of like cross concept transfer and the ability to adapt to new tasks, I think this is a good strategy.
Thanks. Okay, I'm gonna read the second question. Do you mean it can handle new questions? If so, how do you know if a question is a novel or zero shot given the large redundancies in natural language?
So there's the system has no concept of a task or like a concept of novelty. It would make sense to have it might make sense to have the ability to figure out whether something is completely novel so that it can say, I have no idea what the answer is. But there's nothing explicitly defining like the task or or like whether something is a new question. So it's in a way you could say it's analogous to the natural language processing models, which are sometimes done as a text-to-text translation, which can be used to solve a lot of different tasks. In this case, it's an image and text to bounding box confidence and text translation.
So Terry has questions. Please ask.
Okay.
Actually, I'll do it as a two-part question. So the first, I think you just partially answered, which is the system does not appear to have any way to say, I don't know.
Yeah.
That's not part of its vocabulary, which, I mean, if you're really trying to do this open world, that would be part of what you want to do is say, I don't know, and give me the label so I can learn it for the next iteration. So the second part, though, in a number of experiments that were interesting, you sort of show, here's a performance on unknown. But unknown can actually have two very different meanings. One is unknown and never seen, which is what we would call out of distribution or truly unknown. The other is, and this is common within COCO and some of the other data sets, where something might have actually been seen but never labeled. in that particular image or images. And so do you know, are these actually unseen because that's the way you labeled them, or are they just simply unlabeled?
That's a good point. So on the first point that you made, I totally agree. I think being able to say you don't know is an important thing that we should evaluate, but not something that we address in that work. And the second thing, the way that we specifically what we mean by unseen in this case is just that it's unseen for that kind of annotation, meaning that there's no annotations that involve that concept. But intentionally, these things have been observed in other task concepts. So,
that actually is important for the ability to see how the generalization matters, because in one case, your feature spaces can fold on each other, right? If I've never seen it, my feature space may not represent it. In another, my feature space may have represented it, but I have no mapping to labels, which leaves me in a better position to be able to then generalize it because my features represent it. And then you give me one or two examples of a label, and then I can learn it. We call that out of label instead of out of distribution, right? Which is very different in terms of what you can do, but it's very interesting.
Yeah, thanks. Yeah, I think, and we described that in more detail to make it clear in the paper, but that's the example that I gave here of this is truly unseen in the sense that I don't think there's any turtles in Cocoa at all. So, and the system doesn't perform a way that we would want it to, in that we would want it to say, when you say how many turtles are on the log, realize that it's asking about something on the log and be able to do something reasonable, or at least say I have no idea what a turtle is. But what it does instead is it just thinks there's nothing relevant here because there was never these things were never relevant to anything that was posed to it on the previous tasks.
Although if nothing was relevant, you would expect it to answer none, right, or zero, right? Instead, it says 7 things are relevant.
Yeah, yeah, that's true.
Okay, thank you, Derek. I gotta introduce the next speaker, Kate.
Okay, thanks.
So Kate, are you there?
Hello.
Oh, cool. So Kate is an associate professor in Boston University, and she's a consulting professor in MIT IBM Watson AI lab. And Kate has pioneered a bunch of fields such as data bias, domain adaptation, multimodal learning, so on and so forth. So Kate, it's all yours.
Thank you. Thanks a lot for the introduction, and thanks for inviting me to this workshop. Let me know if you can't see my slides. Otherwise, I'll assume it's good. Yeah, so I think this is a very cool topic for a workshop, and I'm going to talk about a couple of very recent papers that are really still work in progress with my students, and sort of my first foray into this open world learning. And of course, given my real focus on domain distribution, alignment, and adaptation, this is going to be combining open world recognition with distribution shift. Okay, so supervised learning works great, supposedly, although I think no one in this workshop probably needs convincing that it has some flaws. But in general, lots of labeled data, lots of GPUs equals success in our field. But of course, we know that with that comes some downsides like dataset bias. So dataset bias just means that your dataset doesn't cover all possible input images that you might encounter at training time. And this causes reduced accuracy, poor performance, and it's often called dataset bias or domain shift. And so this is one side of the problem that I'm addressing. Another side is novel categories. So this is actually a very common, for me, picture. Where I live, there are actually a lot of these giant turkey things, and they often decide to cross the road. But for some of you, this may be an anomaly. In fact, the first time I saw a huge turkey, I didn't know what the heck it was. But even for me, for example, I wouldn't expect to see chimps crossing the road in my neighborhood. So dealing with previously unseen categories is part of this open world setting that I want to address today. So first of all, how do we know if our data set is biased? Well, we often notice because when we deploy it to some real application, the accuracy drops compared to what we saw at training time. And you can even, as Alyosha points out in a paper from 10 years ago, you could play this game where you try to guess what data set your image came from. Now, this is less of a problem with today's data sets, but I wouldn't be surprised if it's still an issue. And you can actually guess where the image came from, which training data set in computer vision. But in fact, even if we train a model on ImageNet and then, as these authors did, collect another ImageNet using the exact same method of collection, they still saw that the deep learning model didn't generalize very well and saw a big drop in accuracy on this new version of the data. So when is this going to happen? Well, I think whenever we have high dimensional data like we do with images and the world distribution is really large and unknown, we're always going to have some bias in any finite data set that we sample from this world distribution. And in the real world, of course, we also have seen some problems like this, and we can anticipate problems with data set bias causing, for example, a self-driving car to fail to detect a bicyclist that was outside of a crosswalk when most of its training data contained bicyclists in a crosswalk or pedestrians in a crosswalk, or the turkey or chimp example that I showed earlier. Or maybe the input data distribution changes because of weather or because of something else. So what are some techniques that we can use to help deal with this issue of data set bias? Well, first of all, of course, if you can collect more label data from the target domain, that would help. But another way is to augment the source data you do have or build robust models. But how about this collecting more data solution? Is it actually feasible? Well, I'd argue that if we wanted to solve a task, let's say pedestrian segmentation, it's expensive to label even one type of pedestrian, but then if we have to throw in variation according to pose, gender, that increases our budget, and then age, race, weather, and so on. And we also do want to cover these anomalies. So I would argue that supervised learning just doesn't scale in terms of the annotation budget that we would need. So the approach that we're taking is to say, okay, let's label as much data as we can with our budget, and then we'll collect unlabeled data from our target distribution. And we are assuming that we get to see data from our target distribution in this case. And so the problem becomes, how do you adapt your classifiers or models from the training distribution to your unlabeled target distribution? And this is what we call domain adaptation. Right, so with domain adaptation, we're essentially collecting unlabeled data from our target domain. And there are several techniques that can help here, including instance normalization, batch norm, data augmentation like mix match, pseudo labeling is a very common and popular technique. And then there's distribution alignment losses, which I'll describe very briefly. Okay, so I'll talk about a few of these techniques for domain adaptation that are popular in the field. And one of the most popular ones is distribution alignment. So here we can actually do this at either the pixel level or the feature level, where at the pixel level, we're aligning the images. So basically taking our labeled source data and translating those images into new images, making them look like they come from the target distribution. So we can use any sort of pixel to pixel model like CycleGAN, for example, given that it can work with unlabeled target images. Another approach is to align the feature representations themselves, because the distributions of the features will be different for the two domains. So we can add, let's say, a domain discriminator that tries to learn the difference in the domain, and the encoder will try to maximize the error of the domain discriminator and align the distributions this way. With the pixel alignment, there are some downsides to this approach, which include mode collapse and cheating. And also with feature alignment, We could run into silent failure or divergence without really knowing that the model has diverged. So these are not foolproof techniques, but they do tend to work, at least in academic data sets, they tend to work pretty well. But what about if we wanted to do domain adaptation in the open world? So in the open world, what I mean by that is, in addition to a change in the input distribution, P of X, now we also have a change in the labels. And here, actually, I don't even mean that we see the same labels, but their frequencies are different. I mean, we actually see some unknown labels, or we fail to see some of the source labels. So the category overlap between our source label data and the target unlabeled data is unknown. So it could be full overlap, it could be partial, or we could have an open set setting. Okay, so if we have unknown category overlap between our source and target domains, we could end up with this situation where, just for illustration, let's take these two classes, the crosses and the circles, and we have the source blue points and then the target are in orange. And we also have these categories. So in addition to the shared ones, we have source only categories, and then we might have target only categories. And actually, even though domain distribution alignment works well on many standard data sets, it does not work in this setting. And it does not work in this setting because it tries to fully align the two distributions, but because the categories, the sets of categories are not the same, it ends up aligning the wrong categories together. So instead, we propose to solve this with a method we call DANCE, which stands for Domain Adaptation with Neighborhood Clustering. And the first thing we do is we abandon the idea of distribution alignment. And instead, we just do unsupervised learning or self-supervised learning on the target unlabeled data. So we do this kind of neighborhood clustering using a loss that computes the probability that a point I is a neighbor of point J, and then we minimize the entropy of these probabilities. And what this ends up doing is giving us a representation that is more discriminative and more clustered in the target domain. And hopefully it also aligns it with our source representation. But we still need to separate these green triangles, which are the novel outlier classes in the target domain, so that they don't get misclassified. And so in the end, after this procedure where we apply an entropy separation loss, we have hopefully the shared categories that have been aligned between source and target. And then we also have a way to reject unknown categories in the target. So just want to give a quick illustration of this setting where I'm showing some features from a data set. I think this is from DomainNet. And we have some shared classes like the strawberry, which in the source domain happens in the source domain and the target domain. Here, the two domains are clip art versus real images. And then we have these other green points, which are the source only classes. So these categories do not appear in the target domain. And so if we apply standard domain alignment, this is what the feature distribution looks like. And we see that we have a failure case where the source only class becomes aligned with a target class. So the clock becomes aligned with the strawberry class. And so this is obviously a failure because now we're going to misclassify the strawberry as a clock. On the other hand, if we apply our dance method, which doesn't do alignment, distribution alignment, using the standard techniques, we see that the clock is not aligned to anything in this case. And for the most part, these green source only categories are kept separate from the target distribution, while the blue target points do become aligned with the red points, which are the shared classes, which is what we want. Okay, so I showed you how this in-domain self-supervision loss can help, but how about cross-domain self-supervision? So in fact, we can still try to do some kind of alignment if we find the nearest neighbor of each point in the target in the source, and then apply this self-supervised learning, contrastive learning, or instance discrimination in our case. And that is going to pull the features that are close to the target features close together. Now this, of course, relies on having some strong discriminative pre-training already so that we have, so that the feature space is not completely random, and so this actually makes sense to do this. Okay, so we call this method cross-domain self-supervision, where we apply both of these cross and in-domain self-supervision losses. And then you can actually pre-train this way on your data with no labels, and then apply this resulting representation for downstream tasks like domain adaptation or retrieval. So I'll show just one result table. There are a lot more in our paper, but this is the Office Home data set, and we're evaluating on this universal domain adaptation setting where we have some shared and some source only and some target only examples. And we're measuring both H-score, which is the harmonic mean of known and unknown accuracies, and the known class accuracy, which is the standard metric. So if you just train with the source label data, this is what you get. Then if you apply some standard domain adaptation algorithms, you get better class accuracy and somewhat better H-score. And then with our dance method, we actually don't improve very much on H-score until we add this cross-domain self-supervision loss, at which point we get the best of all of these results on both the H-score and the class accuracy. Okay, so what about this outlier detection? We haven't really dealt with that head on yet. So this is what we looked at. This is my students' work, Kuniaki Seito's work, called OvaNet. So an outlier detector basically tells us which of these unlabeled target classes are new. So what we propose in this paper is, what if we learn a one versus all network and use it as an outlier detector? So we're going to basically take our known labeled categories in the source and train K one versus all classifiers, where each of them treats one class as the positive class and all the others are negative classes. Okay, so we end up with K such one versus all classifiers, and then we use them to detect if a new sample is an outlier or an inlier. Right, so these green examples are coming from the target distribution, and we want to reject them as unknown using this outlier detector. And the advantage of this approach is that it gives us a threshold that is learned during training. We don't have to set any threshold heuristically or using validation data or using labeled examples of unknown categories. So the way we train OvaNet is we first train these open set classifiers, the one versus all classifiers, plus regular classifiers on the known categories. Then we observe some unlabeled data, and now we're going to continue training using entropy minimization to try to align the known classes towards the source, and at the same time reject the unknown classes. So here we're comparing it again to dance in terms of the accuracy, where the x-axis is the number of unknown classes in the target domain. And we see that the blue curve is our method. It's doing better than these other baselines in terms of accuracy and also in terms of H-score. Also, as the number of unknown classes increases, it is much more stable than some of these other baselines. All right, So when we saw that this one versus all classifier worked so well at rejecting outlier classes, we wanted to see if it also works for semi-supervised learning. So in semi-supervised learning, we don't assume that this domain shift scenario, but we still have some labeled data and some unlabeled data. But compared to traditional semi-supervised learning, we also assume some outlier classes in the unlabeled data. So we wanted to see if we can do well on this problem. So with this problem, what our goal really is to, first of all, learn to correctly classify the inlier classes from very few labeled examples and a lot of unlabeled examples, while detecting outliers in the unlabeled data. And we don't have any labeled examples of these outliers. So our key insight is that we're going to separate inliers from outliers and compute the SSL loss only for these unlabeled inliers, not for the unlabeled outliers. Some related work in this field includes methods that perform pseudo labeling, and fixed match is one of these very strong methods. So fixed match basically augments the input unlabeled image in two ways and then predicts a pseudo label for the weakly augmented image, and then trains the model to predict that pseudo label for the strongly augmented image. But the downside of this, applying this to our open set SSL problem, is that we risk assigning pseudo labels to outliers, because this method doesn't deal with outliers, with novel classes. There are a couple of papers that have come out that deal with the semi-supervised learning with outliers problem, but they have some downsides, like, for example, using a threshold that is tuned to a particular proportion of outliers and not robust to varying numbers of outliers. So we do compare with these baselines in our paper. And then our approach is mostly using our outlier detector that I talked about earlier, based on this one versus all network. And then we also introduce a soft consistency regularization for this outlier detector that's applied to the unlabeled data. And then for the pseudo inliers, we use fixed match. And so what we find is that on some of these standard benchmarks, we are getting fairly good state-of-the-art performance in OpenSet SSL. And we also found that we can detect completely unseen outliers as well. So here we're training on unlabeled outliers, which is something Terry mentioned earlier. But we tested it also on completely unseen outliers and saw some pretty good performance there as well. So just very briefly, our main kind of interesting contribution here is this pseudo inlier selection approach. And then the overall training consists of all of these losses, where again, one of the new interesting things is this open set consistency regularization, which I'll describe. So this is applied to the outlier detector, and it's actually, it's just consistency regularization. So it's nothing super new. We're just applying consistency regularization where the two augmented examples should predict similar anomaly scores on the unlabeled data. And what this does is it trains the distribution to be more robust to outlier classes which were not labeled in the source, in the labeled set. So this classifier is not very robust to them, and this is going to robustify it. Okay, so here are some accuracy numbers. This is on CFAR 10 with 6 inlier and 4 outlier classes. And we're comparing accuracy on the inlier classes compared to labeled only and the fixed match baselines and also MTC. And we see that compared to fixed match, adding our outlier detector with the regularization gives a really big boost. And then also compared to MTC, which is one of the state-of-the-art methods, we also improve performance on this task. And there are a lot more results rather in the paper. I don't have time to go over all of them here. but just quickly showing this feature distribution. So here we are showing also for CFAR, the unknown categories are in pink and the known categories are the other colors. And we have, I think, 100 classes, 100 labeled examples per inlier class plus unlabeled data. And so if we just train a supervised baseline on these 100 labeled samples per inlier, we get this distribution on the left, this t-SNE embedding on the left, where, as you can see, the unknown category is completely confused with the known classes. Whereas with OpenMatch, you get the picture on the right, where the known categories are nicely separated away from the unknown categories. All right, so to summarize, I talked about how domain adaptation is a way to transfer knowledge using unlabeled data that we observe in some target domain. But in the universal adaptation setting, where the category overlap is not a full overlap between source and target, and you could have any of these settings of open set or partial or closed set, a lot of the standard domain adaptation techniques fail and really don't give good performance. And so we've made a couple of contributions towards solving this problem that rely mostly on self-supervised learning and on outlier detection. So combining those two ideas, using OVANet to do outlier detection. And then I also showed that we can apply some of these similar ideas to open set SSL, semi-supervised learning, where again, combining outlier detection with pseudo labeling is giving us some good initial results. So just to conclude with a couple of open questions, or at least what I think are interesting questions to think about, is when we have these distribution shifts, sometimes we just don't know how far is too far of a shift. So if domain becomes too different, maybe we shouldn't be trying to adapt or transfer knowledge anymore. And also in terms of the outliers, what if our outliers are very similar to the inliers? Like here, if our inliers include categories like seagull, but then the novel class is something like eagle, these are very similar types of outliers. So we haven't really experimented with this kind of setup in our paper. And then a couple other questions like, how do we tune hyperparameters when we don't have labels? How do we generalize with not seeing any unlabeled data at all, which is a much harder task? So yeah, these are some open questions that I think are interesting to pursue in the future. And I want to thank my students, especially Kunyaki and Don Hyun, who did a lot of the work that or all of the work that I talked about today. And just final slide that I'm going to leave up, I want to advertise our Domain Adaptation Challenge at NeurIPS this year, which is going to be on this open set or universal domain adaptation task. So I encourage you to participate. Thank you very much. I'll take questions if we have time.
Thank you, Kate. We do have a time, but let me see. So audience in the Zoom, do you have questions?
Yeah, so this is Terry, I have one. So Kate, can you go back to the sort of t-SNE project at the end of your open SSL work? Those were very interesting, but it went by very fast. So my question has to do, actually the next, no, forward. Next one, there we go, this one here, open match for open set of SSL. So one of the difficulties I have understanding that people's t-SNE plots are always, right, t-SNE from what? Because, right, t-SNE is computing its own, mapping, right? Is this a t-SNE from the supervised baseline known classes, from the open match results? I mean, I don't quite understand how to compare these two because I don't know what mapping t-SNE was trying to separate classes from.
Yeah, so this is just t-SNE applied to points that are generated in two different ways. On the left, the points are generated by taking the data and extracting features using a supervised baseline model. And on the right, it's extracting features using OpenMatch.
And then did you add the unknowns after that, or were the unknowns part of the TISNI computation? Because that's part of what that was really what I'm asking.
Yes. Yeah, the unknowns were part of the set of features that went into the TISNI computation.
Okay, so it's the one on the left is TISNI could not separate them. Right, okay.
Yeah.
So anyhow, this was interesting. I'll have to go read the paper. Is this a CVPR paper or?
No, this is not published yet, but it is on archive.
It's on archive. Okay, fine.
Yeah, it's called OpenMatch. Very recent. Very recent work.
Yeah, nice work.
Thank you, Kate. I guess I have to introduce Stella as the next speaker.
Thank you.
Okay, so Stella, are you there?
Yes.
Cool. So Stella is the director of the ICSI Vision Group in UC Berkeley. Stella has done many vision research, including human vision, computer vision, robotic vision, and even artistic vision. Stella has a unique view about the vision. So let's welcome Stella. Stella, it's all yours.
Thank you. Thank you for having me. Can everyone see the slide?
I can.
Thank you. Thank you, Terry. Sorry. If we look at a lot of problems in recognition, whether it's places, faces, actions, species, many categorization tasks, the data has this long tail distribution, which means that many classes have only few instances, and only a few so-called head classes has a lot of instances. Oops. Sorry about that. This training data distribution poses big challenges on recognition. In my mind, I kind of see this tug of war between the data. Data has a will, and the task, it wants to impose this top-down categorization desire on the model. And I want to share with you a few ideas we have developed to turn this tug of war into a hug of war. The usual training data in computer vision consists of balanced training sets. Cats, foxes, pandas, when they are more or less the same sizes, it behaves well. The predictions on cat and foxes are usually the correct ones. But in the real world, you have a lot more cat data, some fox data, and very few panda data. And now the cat prediction is okay, but it drops a little. The fox could be misclassified. And there's also the case of open set problems where you might encounter something you have never seen during training, like a bunny. So in order to address this open world problem, we need to tackle all these, the entire spectrum. The training data could be long tail distributed, and you also need to rise to the challenge of this open world novel classes. You need to be able to say, this is something new. If you focus on the tail instances, the challenge is that how do you leverage many instances in the training data and facilitate the learning of categorization for the tail classes? How do you transfer that knowledge, whatever that may be? And then there's this open world. The only distinction between the very tail end of the classes and the open classes is that this may have one instance and this has 0 instance, which means that for the one instance, a good model should be able to generalize from the one instance potential variations, different backgrounds, so on and so forth. You need robustness. On the other hand, the ones that with zero instance, you need to have a sensitivity, right? So that creates a challenge. If you just handle the tail recognition alone, you might have many approaches you can deal with. If you want to do open set, there are also some problems. But if you want to handle both of them together, that becomes a dilemma. Most focus people have given to this problem try to boost the performance on the tail end or the open set end. And they tend to forget that there are all these head classes you used to do too well. And usually the performance actually drops, sacrificing the performance for the sake of performance for the minority classes. So in order to handle the open long tail recognition, we need to address three problems in one at the same time. One is this imbalanced classification. It's not a big or small problem. It's about that there's imbalance of the sizes between the categories. And usually metric learning, class-wise resampling and reweighting are the approaches. Second is few shot learning. This deals with a small data learning problem. And you have meta learning and a classifier dynamics, how you transfer this across classes. These ideas are exemplary. And then the last one is open set recognition, where you deal with the distribution rectification or out of distribution detection. We need to handle all three in one. So the first idea we come up with is this attention and memory. The basic idea goes like this. You have an image, let's say this one is an instance from the tail end. You go through a neural network, it extracts some features directly from the image. But this image can also activate what you have learned about the entire data set, right? You tap into your knowledge base about what you have seen. And depends on where you focus, you may, this image may be associated with some other head of the insects, different kinds of the heads, different portion of the other images that contains the similar textures. Or it could focus on body parts or tail parts. All of these are activated from the memory. And we are going to use the finite instances in this tail class to learn what to focus on in this attention module, so that the ones that have been filtered and selected and used to enhance the direct feature, so-called memory enhancer feature, can be used to best tell this instance, this class away from other classes. Because of use of memory, we also have access to the totality of the training data. We can characterize how this feature is different from the training data at the inference time, as well as the training time. So we can associate a sense of a familiarity with this particular instance and make the right final decision. So these are the components of this approach. And we show that we can obtain a huge performance gain on these large scale data sets. And this one, while it is only 2%, but we are looking at 1 million classes. So this is quite a significant. Ever since this work, we have been focusing on, the goal of learning, especially in an imbalanced classification data set. You want to have across the board improvement, not just the ones that may pose a particular challenge during learning, for example, the tail classes. And we will have more to say in the next few slides. We extend the idea to domain adaptation. The problem is that during training, you have labeled the source data. The class concept is closed, but you may encounter images that are unlabeled, that appear with different appearances, different domains. Traditionally, it's studied as a source and target domain, sunny weather versus rainy weather, for example. And you can extend it to multiple discrete categories. There are works on that. What we are interested in study is that what if you don't have these domain tags? It's a mixed unknown domains, or it could be when you drive from East Coast to West Coast, the weather is continuously changing, and you don't really have one discrete domain to label each image. So continuous domain situation. So this constitutes our target domain, which are unlabeled, and it's made of compound heterogeneous domains. We also want to evaluate the model on some open unknown domains without access to any of the images during training. This problem, open compound domain adaptation, we coined it last year. And our idea is the following. Take this digit data set as example. You have the source domain, and these are a mixture of other digit data sets, but the tags are not known to the model. We first train a feature disentanglement network, entangle the feature into two. One is indicating the class for classification. The other is domain. And this can be done in the usual disentanglement approach, the ones that you have for the classification, you have labels for. Those that everything else goes into a domain. In the domain, there's nothing left for classification. So essentially is you find the direct sum of these two features that explain the data. Once you have the domain feature, then, so these colors indicate different domains for the sake of illustration. But once you have the domain, you can look at the domain feature and rank each instance according to the distance in that space. The one that closer may be bigger, and it's instance specific. The distance is measured as each instance to the whole set of the source domain images. And then we use the curriculum learning. We recruiting those that are closer to the source domain first. Gradually, we expand the training set and perform domain adaptation. So this shows that when we look at the proportion of samples from each domain, at the beginning, you have the domain that closest to the source domain. As the training goes on, you have more and more domains that look very different from the source domain. And this is part you can see is an extension of open long-tailed work where in the feature adaptation, we have not only the direct feature extracted from the images, but also use the domain indicator and the memory to enhance the feature. So it's using the memory from what you know about the clean, kosher source domain images to modify the direct feature representation. So I will pause and see if there are any questions on this part.
I didn't see any questions.
Okay, then I get on to my second idea we come up with. We have a model. How the model behaves depends on how what kind of data you feed into the model. And we can understand this by looking at the properties of model in terms of bias and variance analysis. That provides additional principled perspective for us to tackle the long tail recognition. Bias and variance concept is a well-known concept in machine learning. let's take this toy example. Each box illustrating a data set. Each dot is our instance. And in this particular set, I have few dots, okay? And the gray line is the underlying unknown ground truth. It's generated, so I generate X, Y according to this ground truth and add with the noise. Given that you can see that different data sets have the same underlying ground truth because of random noise and all that, each time I get a different snapshot of the underlying distribution. Each time, given the subset of data, I will be able to fit a model. In this case, it's a regression, it's a line model. If I dump all these points, congregate all the points on this plot, congregate all the lines on the plot, and then you ask the question, if I pick any point in this space, I use this approach, obtain a model, how much prediction error there is, given that I might have a fluctuating training set. And it turns out this prediction error can be decomposed into, this inherent random noise, there's nothing you can do about it. And then this so-called bias and then variance. Bias essentially is capturing what is the mean model, how mean model is close to the ground truth. And this is the bundle of the individual models due to the data fluctuation, how much variation there is with respect to the mean model. This captures accuracy of the model. This captures, as the data vary, training data varies, how much stability is the final model you deliver based on the training data you're given. So we can express all these concepts in terms of the loss function entirely. And the mean essentially is a minimizer of this expected loss over the data set. And the bias is a distance between the mean and the ground truth. The variance is the variance of all the models with respect to the mean model. When we replace L2 loss with a 0, 1 loss for classification, the only thing that needs to be changed really is this mean model. When you minimize it, 0, 1 loss over in this equation, what you get essentially is the main prediction. If you have 20 models making a prediction, the mean prediction is the majority vote for each instance. So with that, we can compare a baseline approach which does not care about data distribution, the simple vanilla cross entropy loss. On the y-axis, we're going to plot a long tail method. In this case, we use the LDAM as example. Supposedly, it's one of the leading approaches for a long tail classification. And the size of the dots correspond to the head class, body class, and the tail class. Okay, so what matters in these plots, which you're going to see in the next few slides, is this diagonal line. On the diagonal line, the baseline and the long tail methods are the same. So we want the long tail methods can handle long tail data. Ideally, they should situate above this line for accuracy. So we can see that the LDAM approach, the prior art, it does gain accuracy on the tail and the body, but it loses on the head. You sacrifice the head for the body and the tail. The method we developed boosts the performance all the way up, especially for the head. We also increase the head accuracy. In terms of the bias, for LDAM, there is a reduction of bias, and the reduction is greater as you go from head to body to tail. And we are going to continue this trend, reduce it even further. The smaller the bias, the closer we are to the ideal classifier we want. In terms of model variance, LDAM has a larger variance, whether it's head, body, or tail. And this holds for most of the algorithm out there we tested. And what we are able to do is to reduce the variance throughout and get even smaller variances than the baseline approach. So how do we do this? Since we want to reduce model variance, a usual idea is ensemble. But here our ensemble, model ensemble, takes a different architecture. We have shared backbone. We have independent classification heads. In order to reduce bias, we're going to introduce not only the usual classification loss for these classification heads, but also the distribution-aware diversity loss. If an instance comes from tail class, we want these experts to make as widely different decisions as possible, or make that decision based on different features. The usual thing that comes with the multiple experts is that the model becomes bigger. So in the second stage, once these experts are learned, we train an expert router to decide whether we need a second opinion. We first pass the image through the first expert. If the first expert decision is confident enough, we stop right there. If it's not confident, which routers tells us, we go to the second expert and seek more opinion, and the accumulated opinions will give us a new decision, and so on and so forth. And you can see that for head, body, and tail classes, the head classes, most instances can be done with one expert, while for the tail classes, most needs 3 experts. Our method achieves the state of art on all the major benchmarks, and it can be all the classifier. You can use different loss functions, different training schemes, and we show that experimentally it's a universal add-on that can be deployed to improve the performance on long tail. Any questions?
So this is Terry. I have one quick question. When you kept saying accuracy across the classes, are you doing micro accuracy, so per instance is counts, or are you doing macro accuracy averaged over the?
Yeah,
macro?
in the open long tail, we make all the test class size equal, so we can fair assessment on the performance. So in this case, because the test set is same size, macro and micro, they are equivalent. Thank you, Terry, for the question. So I get to the third idea. So far, we talk about supervised learning. Next, I want to talk about unsupervised learning, because in natural learning of vision, babies don't have concepts of semantics, right? They only have sensor instances. When the baby is little, she just needs to figure out, is this a sippy cup or what, right? There's only few items she can play with within her, visual zone or reach, the zone of reach. And the training data, in a way, is also long-tailed. The baby has massive experiences with very few types of objects and a rarer experience with many objects. So along this line, if you think about how we can computationally capture the task of the baby needs to differentiate all the instances, learn something. So when she encounters new things, she can recognize. She can visually discriminate or understand this new instance. But what is categorization? In my mind, it can be simply described as a 2-level categorization tree. The bottom nodes, the leaf nodes, are the instances, and the top nodes, each incident upon a bunch of leaf nodes. So the downstream categorization could really be arbitrary. You have one kind of organization, you have another. Sometimes you say this image contains a dress. Next time you say this image contains the woman wearing the dress. It's rather arbitrary. So how can you learn something that's universal that can be used in the downstream task and you don't know the categorization tree? One way to do this is to make sure that you learn something about each instance so that you don't prematurely collapse the representation between subsets of instances. You keep all these possibilities alive. So when you have new label data, these can be called into actions and help you accomplish the supervised categorization task. So this idea is turned into so-called instance classification. For ImageNet, you have image, you have 1,000 predefined classes, you train a classifier. You map each image in this 1,000 dimensional space along certain axes. For instance classification, you don't have labels. You have 1.2 million instances. And so this space expands a huge deal, 1.2 million instances. And so that is a computational challenge. So how do we handle this? When you do classification, you are learning the class-specific weights. But we turn into non-parametric softmax. We associate a feature with each instance so that it is not only the class classifier, in this case, just instance classifier, but it's also function as the feature, contributing to be classified by some other instance classifiers. Once you've done that, you turn this instance classification problem in the 1.2 million dimensional space into a metric learning problem, because in the loss is only the distance between instances that matters. And that dimension can be much smaller. Instead of 1.2 million dimensions, you only have 128 dimensions. Intuitively, all the instances in the data sets need to find a place, land on this low dimensional hypersphere, and each try to push other people apart, away from itself. That's the goal. In such a cramped space, something has to give. Those that share more data similarity will tend to cluster. And this is a pipeline. You have image, you have a feature encoder, you find a feature, you have these memory banks store these class so-called instance prototypes, and you compare to them, you are implicitly implementing this instance classification in a much higher dimensional space. This thing doesn't require labels, so you can train from unlabeled data. In order to evaluate how good the feature is learned, is any useful for the downstream, we use the feature to retrieve neighbors from a labeled set, and then the accuracy can be benchmarked. So this work has, led to a lot of contrasting learning approaches, but I want to point out this, instance discrimination. It only tries to discriminate among instances. So how do we develop the sense of categorization? You need this one step forward, relate different instances together. For this baby, the next step up towards categorization is to see that two different instances actually correspond to the same kind of object. How do we do that? So the training data is long tail distributed, and there could be correlated instances. And it's essential to handle this so you can go from instance discrimination to categorization by recognizing there are groups of instances that correspond to the same concept. So the way we handle this is you have different instances indexed by different I and a j, and you can engineer its twin by perturbation. And that, these arrows, the red one, these are attraction arrows, and all the different instances you are repelling. That's what instance discrimination will tell you. You engineer this attraction. You assume they're different. So our goal is to say, can I go from engineered attraction between different instances. Can I make that bridge? Can I discover that connection? So we turn this into, a characterization of this data similarity, right? They are correlated, they look alike. It's because in feature space, they tend to occupy similar spot. But we don't want to forcefully encode that. So what we do is we calculate the local grouping and in the feature space. And now if you look at it, this instance is going to be attracted to the twins local group and repel others groups. Likewise, for this different instance, these local groups, it's likely they're going to be attracted to the same group and repel the same other groups. So now if you ignore the size of the error, it's really the type of relationships. Xi and Xj have identical relationships. And this is how you, in the embedding, you will put X and I and a J in the same spot. This is how you discover different instances that actually should be the same group. So this is schematically how this is done. You have instance, you generate augmented versions, you calculate the feature, you do contrastive learning. That's the usual thing for instance discrimination. All we add is a different group feature. And we're asking that the instance feature should repel the local group of the twins local groups. It's a cross-level discrimination. And we show that with the simple idea of capturing the correlation, we can handle high correlated data, long-tailed data, and standard benchmarks, transfer learning, semi-supervised learning. Most notably, it's with much smaller academic compute in terms of number of GPUs and training epochs and batch size. And I want to conclude, I talk about three things: attention, memory, with the transformer, and this, I think that, there are new ways to implement this. I talk about analyzing the models of the behavior as a model in terms of bias and variance and impose the properties that you desire. And I talk about exploiting instance correlation, let the data speak for themselves, speak for you towards accomplishing the task you want on the long tail recognition. Thank you.
Thank you, Stella. Any questions from the audience in Zoom? No? Yeah, I don't see any questions in the YouTube chat, but maybe I can add something. It's not about a question, it's about an opinion. So Stella, I like your figure that is a long tail, and you explain on the open set, a few shot and the common classes, but I think there's a missing piece that is outlier. I think outlier data is in infinite scale. And I want to distinguish between outlier and open set. By open set, I want to say that, we may be interested in open set, but we just don't have enough data. And as we don't have enough data, we don't have a data to build the classifier. So we gather them all as open set, but for outlier, they are not interesting, but we can make use of them. Like we can do pre-training. So I think that is an essential difference between the terms. Not a question, but if you have an opinion to push back, please do.
So who tell you that the outliers are of no interest and open set are of interest? Where do you get that bit of information?
Yeah, that's my controversial claim. I mean, if we define a task, maybe we have defined the outlier concept. Like
outlier to what? To what? Outlier is something you have not seen during training.
Yes. For example,
it's the miscellaneous. It's like something I have not seen, but I don't care.
Right. For example, we have medical images, and we want to do medical image analysis, but we have image net data. So I want to say image net data is outlier in front of medical images. That is my personal opinion.
Since now it's time for this panel, I'm going to defend Stella on this, right? There's no way to say for an unknown class whether or not it's of interest until you know what it is. Right? The difference between open set is simply not something I know that I'm not currently trained on, right? So whether or not it's open world or whether or not it's an outlier, right? Open world, I want to learn it. Outlier, I don't care, right? But I don't know that until I know what it is, right? That's the question of what's interesting is well beyond vision.
So I think it's a great time to connect, to get to the next session, right, on the panel discussion.
Yes, so Carl is a new guy. He hasn't spoken. Yeah, he's not new. He's a professor in Columbia. So Carl, why don't you ask some questions?
Sure. So hello, everyone. I guess I think Abhinav and I will be the moderators for the panel. And thanks very much for joining us. So I guess on the panel, we'll have Terry, Stella, Tom, Yu-Xiong, and Shu. We have a bunch of questions. A lot of them are coming from the audience, and also some of the questions that I've thought of. And if people have more questions on the live stream, please feel free to ask them. I think then they'll get routed our way. So why don't we start off with well, there's one question I was thinking we could maybe start off with the panel, which is how do we know, which open world problems are solvable and which are not? This is one of the challenges in this area is how do you draw the line, right? Are we solving an impossible problem? So how do we know which problems could be solvable?
I guess the first thing is if humans do it, and I know that's a little hard to decide. But I think a lot of the points in the last talk, for instance, we know that children are able to learn rich representations of the visual world, and that they do that with relatively little labeling, certainly no bounding boxes that I've ever seen. So that's the main guideline. I mean, we can't know. We have to, part of the problem is we don't know whether our formulation of the problem is the same as the sort of ecologically valid the way it works in the world. And then again, often we're trying to do tasks that are really superhuman tasks. I mean, I think there are few humans that could visually recognize all 16,000 species of insects, right? It's just a superhuman task. Although there certainly people can do, well, I don't know if there are 16,000 characters in Chinese, but certainly it's a big space. So we have to just try. Sometimes there is no, I know that's a depressing answer for a graduate student. There's no guarantee of success. Sorry.
So I was going to follow up with Tom, right? So I think the biggest difficulty is not even whether or not humans can do it, because there's lots of things humans can do, but we don't yet formulate our problems. Given the lifelong experience, can you solve this problem? We often formulate it as given this very narrow bit of data. Right? And that limitation is really limiting, both in terms of what we can learn, but also what we can say, what we can learn about, because we don't know what bias is stuck in that data, what limitations are embedded in it. So we really have a hard time saying what can we solve and what we can't. Make a DARPA program, we'll try.
I think sort of a follow-up question to that. So I think there are a lot of these different communities that intersect, right? And we have had this discussion today in multiple talks. There's anomaly detection, and there's like you do open world recognition, like Terry has defined it. You have open set. You have learning from few labels, like Yu-Xiong will talk about. So like associating different samples together. I think one of the issues that is plaguing this whole community is there's so many different terminologies, and everyone has their own definition for it. And it's very hard to convince either the reviewers or other people who are doing that well, this is an important definition to work on, right? Or clearly delineating boundaries, that when you are doing that, I'll talk about it later today, co-localization, co-segmentation, object discovery, all of this is just jumbled up, right? I like Terry's push that it's open set, and then there's open world recognition when you learn about new classes, But then some reviewer might come back and say, no, you are just doing few shot learning with active labeling in between. So how can we take a step back and define, like, how should we interact with these different communities? Where do they stand in this pie chart? How do they overlap? And yeah, like open floor.
So I agree, Abhinav. I've spent more than a decade now fighting when people say, no, that's not the right term, right? That's exactly the same as, and then they describe a problem like zero-shot learning, that open world learning is zero-shot learning. It's like, no, I mean, they're both interesting problems, but they're different problems. Let's agree on some definitions, right? And I don't care if people want to use different definitions, but we shouldn't keep saying this other thing is the same thing. That's where I really get, I think it's bad for the field for us to mix them up, right? The open world, unfortunately, I tried to make a formal definition. It's a very useful term because everyone likes it. It's the open world, right? It's easy to have an intuitive definition that's not the same, right? So I think that we do get ourselves into trouble that way.
I thought Ali Farhadi's fluid framework is a kind of unifying thing. I mean, it's certainly a very challenging task that if you could do it, you would probably have solved a lot of these other problems along the way. The trouble is, I don't know if I were, well, and I am, when I think about doing a research project, I would rather, you have to do some sort of divide and conquer and say, well, to make things feasible, I'm going to work on this piece, like the open category piece. But I do think it would be important to be able to say, okay, I have my new open category module. Can I plug it into some other fluid like baseline framework and see if it helps? Because I do think it's a really important question whether the divide and conquer. I mean, the whole field of AI and computer vision is based on a giant divide and conquer, and we see that maybe, I mean, for instance, the synergy between language and vision is showing us that, oh, maybe we shouldn't have separated out natural language processing and computer vision into two entirely different subcommunities. So it is great if we could create, make it easy for people to work on pieces and yet come back and test them in a unified framework. With the robotics community, the ROS operating system has really enabled that. So could we build something similar for computer vision and for AI more generally?
Yeah, I don't know if Ali's still here, but I mean, so I think the fluid framework is interesting, but as I try to point out in my talk, I think we also have to be very careful to make sure we're measuring what matters for real problems. And the framework itself can then become an impediment, just like a data set can become an impediment because we're focused on the wrong frame, right? And I asked Stella the question about, is it micro or macro? Because in fact, the answer to which is important is actually not, in terms of an actual application. If I'm deploying a system, I might actually care about micro class accuracy, because what I really care is that I get the, how many false alarms do I get per day, or how many misclassifications do I get per day, not how often do I properly represent the minority class. That's not a science question. That's a business question or a deployment question. We can't answer it. So we have to think about how we measure what we want to measure in these complicated frameworks, especially when you start combining tasks. What's the right metric is very hard.
So I think just to add to that, I think I agree. So I completely agree with that part of the talk where like picking up an operating point and those kind of things are bad. And I hate doing that, but given the practical realities of reviewers, they love numbers, right? So the only community I've seen this do it well, maybe because of some IAPA program, was face recognition, where they do the plots and then they have several operating points that we need these many for this much false alarm and this, and what's your number with that? So do you think coming up with certain regions that these are the plots we want to look at, or maybe we can look into how Derek was defining the plots, like using the graphs as measures themselves, and define some regions that this is a false alarm region I'm interested in, this is a region I'm interested in, and so on. Do you think there's scope there, or as soon as we take a step in that direction, we go in the wrong direction?
Well, I can't answer how reviewers will behave because I'm not a very good predictor of them. I mostly fail. I learned from being burned many times. But so the idea of defining, which we do in the biometrics community, right? The idea of saying, here's a security-oriented setting, here's a convenience-oriented setting, right? We did biometrics. What we wanted to do for Google for your phone was to make sure that it didn't annoy you too often, or you wouldn't want to use biometrics. But if we're setting up a security system for a watch list, it's security. There are different parts of the curve that different generalized, deployments will be interested in. And you could choose a couple, right? You don't have to have a ton of them, right? But the reviewer is getting very unhappy. I put that plot up from the paper that's this year, right? Or not the plot, the table, right? The other reviewers will look at that and say, this is too complicated. I can't understand it, right? That's not an acceptable answer from a reviewer, in my view, who's looking at a complicated problem. But we've actually had reviews that say, this problem is too complicated. Right? We don't want formal definitions, right? I don't know what reviewers are looking for anymore. So I can't tell you how to solve that. But from a science point of view, we should say, this is this kind of setting, that's that kind of setting, so that people who are in industry who are trying to look at our stuff can make an informed decision. Is this a path I should follow? Right? Rather than, unfortunately, saying, well, implement it and try. See how well it works.
So
Go ahead, Stella.
I want to comment on, if you think about human vision, vision is so remarkable. Other measurements, like you get a sense of, you treat this as taking measurements. With vision, somehow vision has existence of its own. Every day we experience a lot of new things, right? Computer graphics generated, new virtual world. And we totally understand it. It's like our metric in evaluating what we see is somehow rooted in, something like I would call like a mid-level representation, right? How you evaluate, and that's one. Secondly, is actually whatever that is, you see something, you inferred something, but that something allows you to function very well in whatever task you want to do, right? So that's what holds for human vision. And I can see this should also hold for computer vision, right? Have some task that then can indirectly measure how good, your ability on the open world recognition helps you to accomplish that. For me personally, I'm pushing for mid-level vision, right? In terms of methodology, I'm looking into breaking apart the images, understanding what's going on, find the generalizing rules that governing the perception. So it allows you to do a lot of composition with what you have learned. Parts and pieces you have seen somewhere. It's the new composition that makes a difference. So I just make these few comments.
I think this is a great segue actually to the next question for the whole panel here is for PhD students who are just starting out kind of in their second or third year, right? What are interesting PhD topics? What would you advise your PhD students to work on and make an exciting thesis and really have impact here? Assuming that the evaluation was all set up and everything, right? And won't worry about the reviewers, right? But what would make an exciting PhD thesis kind of in this area? That silence is a dangerous answer to this question.
So I'll go ahead. So I think one of there's a whole bunch of interesting directions. I think the sort of dealing with self-supervision in a meaningful way, right, is very difficult, because if we treat self-supervision only as how does this help me solve the next supervised task, right? We'll always lose to supervise. We'll probably almost always. Right? It's a difficult problem to beat supervision at supervision. Right? But if we start doing these multitask kinds of stuff, the kinds of stuff that Kate looked at in her talk and that Derek talked about, the multitask version becomes the more interesting place to say, I need to get here, and then I'm going to use the same thing for these multitude of tasks. That becomes a more interesting way of looking at how do we evaluate self-supervision. But as I tried to get at the end of my talk, right, I was going down that path in a meaningful way, but now it's like, well, we can cluster them lots of different ways, right? What we can do with those depends on how cleverly we define the next layer of tasks. And I expect we'll see a plethora of projects where it's like, here's a new downstream task to show that my representation is good. But it's really, and I worry a lot about this sort of graduate student descent, where they just find a way to get something that's better in some new interesting direction, right? Because they can run lots and lots of experiments and find some way to do that. But to me, for the open world, self-supervision, also as Stella said, right, it is the future, right? It's the real problem that we have to look at. We just haven't come to good grips on how do we not just solve it, but how do we evaluate? So I think, Carl, to say assuming the evaluation is solved, is actually bad for a PhD student. PhD students should absolutely know how will it be evaluated. That's, in fact, I care less how are they going to solve the problem, that they understand what's the problem and how will it be evaluated, because that's when we can decide to graduate.
I hesitate to give advice to PhD students at this point because everything seems so difficult. But one concern I have about the discussion here today is that we're really only thinking about visual evidence. So when we think about self-supervision, the one exception maybe was trying to do self-supervision from video. And I think that's heading in the right direction. I mean, the baby learns about the world in order to figure out how to get food into their mouth, or how to play with a toy, or how to move things. So I think that, maybe looking at some of these questions in the context of robotics might be interesting. Or video is a kind of passive substitute for robotics, but that doesn't make it any easier. But I just feel like restricting ourselves only to visual evidence when we're trying to imitate a human system that's embedded in a world and has goals they're trying to achieve in that world, that's where categories come from, right? They don't come from a label or an ontology. And so I'd like to see some connection to that.
For me, grouping and figure ground is always the heart of many problems. Figure out what goes with what, right? Once basically break down all these patterns, don't treat them as a tapestry. You learn what becomes, tend to come together as an entity. And when they come together, what are the governing rules that at the mid-level, right? In terms of compatibility, in terms of the contextual modification. If there are a lot of demonstrations in vision, the context, even if you can detect the object, but the context can modify how you see them. So what are the low-level, mid-level cues that modify your perception? I think these are hardest. If you know what is foreground, background, simple classification, that's a very straightforward classification problem. With the deep learning, you can train a model to tease them apart. The tricky part is, you don't know what goes with what. You have so many zillions of possibilities, right? Take Mask RCN example. Once you have the proposal, the rest is trivial, right? But with the proposal, you're also missing out a lot. You're not seeing the totality of the scene. I think the amazing part of a human vision is how can you do it so fast, so effortlessly, and seeing how they are connected to each other, yet popping out things of interest. So I'm all-time supporter for students, new generation of students, bringing fresh, ideas to this fundamental problem in vision.
So I have two follow-up comments. First, I think probably we would like to encourage students to formulate the problem in a new perspective. So as the name of open world suggested, it's not only open world, but it's also open world research. So currently the way we formulate the problem is kind of narrowly defined. So we are even not sure because the open world problem contains a lot of different aspects. I think we probably even not sure by making a particular step, are we actually solving the big problem of open world? So maybe we need a different formulation of the problem rather than just treat the closed world benchmark into an open world setting and investigate. Maybe indeed investigate the problem into the open world setting. The second comment is regarding the methodology. I think Tom mentioned the self-supervision, not only in images, but also in videos. Maybe feature representation is one way, so that allows us to generalize to novel scenario, but it probably other ways for humans, like how we learn the model or how we actively interact with the environment. This is a different multiple strategies, and multimodality might be also other ways to tackle the problem.
Great. So it seems like there's kind of there's this sense of like, let's move towards video and robotics. Those are interesting directions. What about language? Is language relevant here? Would that be useful for learning open world representations? Usually in vision conferences, this is a controversial topic.
So I'll take a stab at it. So is it useful? Yes. Is it something I'm good at? No. I'm too old to be going and learning a whole new subfield now to start trying to get down that path. But for a PhD student, that combination, right? And I think we have to be very careful when people say natural language. They often actually mix two things. Part of what many natural language systems do is they start with a rich ontology that allows you to describe the relationship between objects, which might be, in fact, a lot of where the value is. The language itself is really some weak labels to go with this very strong ontology. But I don't know that, right? But they're very different problems, but that actually makes them good complementary things to learn from. And as I think Derek showed in his talk, right, there were some places where that combination allowed him to improve the localization and the vision side, right? Because I think if we think about Stella's talk, there's lots of things where we might learn features because we've seen things, but we don't know their labels. Where we've been lately calling the out of label distribution, out of label problem instead of the out of distribution problem, right? I might have seen it, I have good features, I just don't know what it's called. It's a much easier problem to solve than I've never seen this, and I don't know where it goes in my feature space, because that's a much more difficult problem. They don't associate well. So I think language has the possibility to help, but I think it's also that language data sets have the ability to help us solve that problem, because they might actually have good images and not formal labels, but somehow the language in one caption captured some of that, and they don't consider it labeled, but the caption has the word dog in it, even though there's a dog in the photo. Dogs were never a labeled class, or something along the way, right? Or they mentioned a person wearing a tie because some knowledge base told them people wear ties, right? And they have that word in. So there's lots of interesting things to combine with language.
I worry a lot about language, though, because I feel like today's language models are also not getting at semantics. And no one knows how to label language for semantics. I've been involved in some DARPA programs in natural language processing, and boy, if you want a long debate, talk about meaning representations. It's just crazy. And inter-rater agreement for producing meaning representations is, really low, which is a suggestion that it's not the right thing to ask users to do. So I feel like language has the same problem as, well, a worse problem in some sense, that it's not grounded in anything. At least vision is grounded in sensors. So I would still argue the trouble with language is it gives you the illusion that you're making progress because there's strong statistical regularities. But calling them digital parrots is not too far off. I think if we're really going to make progress on the fundamentals, it's going to be because we have agents interacting with the world. And so in natural language, maybe I think language plus robotics is also very interesting. And maybe language in dialogue, but you see the fact that we're having a lot of trouble making progress in dialogue is another symptom of the fact that we're not learning the right representations in natural language processing either. It's all about representation, right, in both fields.
So I feel sound and vision should be studied together. I would promote the integration of sound and vision, both as a sensory information, measurements you can take, and they are complementary, providing different kinds of information. Language is good for communication, dealing engineering, practical applications. It provides additional information. But the sound and the vision are more primitive, and they have common things, and they, as a sensory representation to be developed, to be studied, to be contrasted, and to be integrated. Can you imagine yourself driving with it, with the earplugs on? Can you imagine walking around the house, can't hear anything? I think investigating. So basically, we need to get out of the silent movie era for computer vision. There are people study sound vision, but it's not yet mainstream. And the data is already there for the videos.
Kind of sort of following up on that. So this leads us to an interesting venture, right? We have this, we have video, vision, audio, text, language, so on and so forth. But then when we discuss our open world models, we often discuss they don't generalize to say medical imaging, right? So there has to be like robotics. Like if it's a self-driving car, we wouldn't expect that model to be thrown a chest X-ray image and be able to parse it. At least it can say that it's out of my domain, but that's about it. So what would be a dream application where we can say, okay, within these constraints, we can say that it's open closed world, that this is my world as I define it. These are the things I want, and I can throw new tasks as it, but in this world, right? So so we go all the places. We go to long tail, we go to medical imaging examples and stuff. But how home robotics, is that the golden application? Cleaning up our table, kitchen, self-driving car. What's one like few examples of such applications which we can aspire to build?
Good question. I don't know. I like the home robotics example. Yeah.
So home robotics is one, but as I try to write, some things are home robotics isn't going to have near as long a tail as an outdoor robotic, right? And outdoor robotics, self-driving cars, right? There, in my view, they really are an open world problem. You might try and argue, as Efros did, that they're a closed world, but only if I make the world really, really big can I say, right? But if my goal is simply not to hit things that move in front of me, then maybe it is a closed world because I really can treat that category, right? But if I'm trying to visually understand that, and I'm not using a LiDAR to say something's in front of my bumper, don't move, right? Then to me, it's an open world problem. But I think the question, what applications, right? All of us are mostly academics, right? I think the applications will come from people outside who are trying to figure out what problems do they have, where does the open world hurt their current applications, and then we're going to start seeing more and more as people start saying, oh, this technique lets me solve my problem.
So I think the issue there is companies do take a lot of stuff that we publish and try to apply it, but we often don't hear like these are the things that didn't work, or these were the things that required a lot of engineering, like calibration. Object detection works everywhere, like we have 18,000 classes, it works, but no one talks about calibration in vision conferences. It's so hard to, very few people actually pay attention to such problems. So like how can we find more about like people who are trying out our models? Hey, these are the places it's working, these are the... Yeah.
Have one of your students go do a startup. You'll learn a lot.
Yes, I like these closed silo ones, like cleaning up our office desk or home desk, or cleaning up the kitchen. No matter how closed world it is still far beyond the capabilities of even a computer vision system to know what objects are stacked where and so on. So yeah, okay, all right. I think we are about to wrap up. Unless Carl, do you have a question, or Shu?
No, I think that's great. I think yeah, I think it's time for the coffee break.
Okay. All right. Thank you very much, everyone. I like that homework question of thinking about that problem setup. And yeah, thank you for joining the panel.
Hey, Yu-Xiong.
Hi, Shu. Can you see my screen?
Yes, yes, that's great. Okay, let's get us started. So now we have a Yu-Xiong. Yu-Xiong is an assistant professor in UIUC. He has done impressive work on few-shot learning, streaming perception, which I think a domain of open world. So let's welcome Yu-Xiong. Yu-Xiong, please.
Thank you, Shu, for the very nice introduction, and thank you everyone for coming. Today, I will talk about one important step towards open world computer vision, learning to learn more with less. I will focus on some of our work on reducing human supervision and learning visual models for visual concepts from limited data. Okay, let's start with a still image. Some of you have probably seen this object before, but I guess for most of you, this is the first time. This object is called Potter pot. Now, let's find the Potter pot in this image. Although I cannot say, I'm pretty sure that many of you quickly give the right answer, even though these two Potter pots are in different poses and viewpoints. You see, remarkably, we humans are able to recognize a never before seen object from even a single image. How if we want machines to recognize this novel object Potter pot? To achieve this, the current paradigm is based on supervised learning, especially supervised deep learning models. To learn the model, we show examples of image and target label pairs. Of course, here the target labels are defined by humans. With the model, this image should be labeled as Potter pot. Humans has already labeled it as Potter pot. We show another Potter pot, another Potter pot, and another Potter pot. We have to show at least thousands of photos like this in order to get the model to recognize the pattern of a Potter pot. Recall that humans only need a single image. You may think that this is not a big deal, since we are in the big data world. Why don't we just simply collect more data? Unfortunately, this is not the case. We are actually living in a long-tail distributed open world. In this world, a few classes, like cats, are coming in the hand of distribution with large amounts of the data, while many classes, like this large species, are rare or unknown in the tail of the distribution with limited data. Simply collecting data doesn't scale, since we have to recollect huge data for each new class. Also, human annotation is expensive and sometimes require expertise. In practice, it becomes even difficult to collect and annotate data for rare concepts and events. For example, while being able to recognize a child chasing a ball is critical for self-driving cars, I believe that no one is willing to actually put a child on the road to get the desired data. So there is really no way to get around this fundamental lack of data issue. How could we build more powerful learning machines that are able to recognize a rare or novel class, such as lorries, from one or only few annotated examples? This few-shot learning problem is the focus of my talk today. More formally, in few-shot learning, such as few-shot lorries classification, we are given only few training examples of lorries, and we aim to learn an accurate lorries classification model. Here, shot means a number of training examples, and for example, in one-shot lorries classification, we have only a single training example of lorries. Well, while we have only a single example for this novel class lorries, we have many common or base classes with large amounts of labeled examples. For example, we have lots of cats, dogs, and fishes. So we address a large collection of few-shot classification tasks of base classes. We address few-shot cat classification, few-shot dog classification, few-shot fish classification, and so on. By doing so, we learn how to learn an accurate cat, dog, or fish classification model from few examples and obtain certain shared experience or skill that is useful for solving few-shot learning in general. We then use this prior experience to guide the model learning for the Loris class. Now, we are not learning purely from data, but learning from experience. This line of work is called meta learning or learning to learn. More precisely, we are hoping to build a principled meta learning framework that allows us to address a rich space of few-shot learning tasks in a unified way. While existing work largely considers few-shot classification, we would like to address how to localize, detect, and segment novel objects and recognize their actions from few videos. In addition to discriminative recognition tasks, we also consider how to synthesize objects in novel viewpoints and poses from a single image, and even reconstruct their 3D shapes. Not only for single objects, but we also want to detect the uncommon object and object interaction, and even enable robots to interact with objects and humans in a dynamic few-shot environment. More broadly, few-shot learning is not limited to visual domains, but exists in a variety of modalities and their interactions, such as in visual question answering that uses both images and natural language questions, and recognition in 3D LiDAR point clouds. Not only for computer vision and robotics tasks, but we also hope the underlying mechanism to be general and applicable to other fields, including natural language processing and reinforcement learning. So, what type of experience are useful for addressing these few-shot learning problems? When we have limited data, a natural way is to generate additional data. But the question is, given a single example of this novel class Loris, why do we expect that it's possible to generate additional data? Well, the visual world is highly structured, and rich modes of intra-class variation, such as camera poses and lighting conditions, are shared across classes. For example, in the base classes, we have cats in different poses, like cats sitting and cats climbing trees. Such knowledge of the shared modes of intra-class variation, if learned on the base class, may allow the machine perception system to hallucinate what a Loris might look like in other poses or surroundings, like Loris climbing trees. These hallucinated examples could then be used as additional training data to build better classifiers. Unfortunately, building models that can perform such hallucination is difficult. There has been significant progress in synthesizing visually very realistic images by using approaches like GANs or NERF. Look how realistic these synthesized images are. But recent work shows that these images are still not that useful for recognition tasks, since they are not optimized for learning classifiers. Our key insight then is, instead of optimizing visual realism, we should aim to generate data that are directly useful for learning classifiers. Such generation can be performed effectively in a feature space, rather than going down to the level of raw images. So we first train a standard convolutional network on the base classes as a feature extractor. Now, let's see how we perform data generation in this feature space to address the few-shot classification task on novel classes. As an example, here we show a 4-way classification task that classifies 4 novel classes, including Loris, with a few training images per class. We first use a trained convolutional network to extract their features and construct the corresponding small training set as trained. We now introduce a generator G to produce some additional examples for each class. The generator G is a neural network. By sampling seed example from S-train and sampling noise vector Z and passing them to the generator G, we obtain a generated example. We treat its label the same as a seed example. We perform such generation for all the 4 classes and obtain a set of generated examples. Combining these generated examples with the original S-training, we now create an augmented training set. This augmented training set is used to learn the classifier H. The question then is, how can we learn a good generator G to facilitate the learning of H? We achieve this by first leveraging the mental learning process. Through mental learning, we simulate a large collection of Yu-Xiong classification tasks from the base classes. Here, each row is one of the constructed 4-way classification tasks by sampling 4 random base classes. Each task consists of its own small training set and held out validation or query set. The training and query set are constructed by randomly sampling a few images from each of the 4 classes. We now learn the generator over these constructed few-shot based classification tasks. Consistent with the process before, we perform generation in the pre-trained feature space. For the first base task, given its small training set S-train, we initialize the generator G to generate additional examples and produce an augmented training set. This augmented training set is then fed into a classifier H to produce a final loss on the held out query images. We backpropagate the gradient of the final loss and update not only the parameter of the classifier H, but also the parameter of the generator G. By jointly optimizing both the generator and the classifier, our generator is trained to produce the kinds of examples that are directly useful for class distinction. We then sample another base task and perform the same training process and continue updating the parameter of the generator G. Note that here we have a single generator G that is shared across different tasks. We repeat such training process over and over again on a variety of few-shot based classification tasks and obtain the generic category shared generator G. We then use this learned generator G to augment data for a new classification task on novel classes. So here, there are 2 keys to generate data that are useful for recognition tasks. First, end-to-end training of the generator and the classifier, so that the training of the generator is guided directly by the recognition task objective. And the generator and the classifier cooperate with each other to boost the recognition performance. Second, mental learning over a large collection of few-shot classification tasks, which makes the learned generator shared across different tasks and can be used to address novel classification tasks. Note that here, significantly different from GANs, we didn't use any realism objective. So our generated examples might not look pretty, but they are useful, as demonstrated on the large-scale ImageNet-based few-shot classification benchmark. The benchmark has 389 base classes for learning the feature extractor and the generator. We evaluate the performance on 311-way classification of novel classes. We compare mental learners without and with generators. We look at widely used prototypical networks and matching networks, which can be viewed as a different type of a classifier H. We can say that our generation strategy significantly improves novel class accuracy by up to 6 points for prototypical networks and 2 points for matching networks in the challenge of one-shot learning case. This shows that our approach is general and can work with different mental learners. To analyze the effect of the generated examples, we visualize their feature vectors by projecting to a 2D space using Tisney. Here, the cross shapes represent real examples of 5 novel classes. The star shapes represent the set examples, which are the input to the generator. The triangle shapes represent the generated examples. Interestingly, due to the discriminative training of the generator, our generated examples tend to cluster around the class boundaries. This explains why our generation is useful for learning classifiers, because the generated examples directly contribute to formulating classifier decision boundaries. This work can be naturally extended to address more challenging few-shot detection problem, where we need to simultaneously classify and localize multiple objects within an image. The most difficult regime occurs when there are very limited bounding box examples for novel classes. For an object detector to be accurate, its classifier must build a useful model of variation in appearance with very few examples. Therefore, to deal with the lack of variation in training data, we introduce a generator or hallucinator network that learns to generate additional useful training examples in the region of interest ROI feature space and incorporate it into a modern object detection model. Similar to before, this generator network effectively builds a better model of variation for novel classes by transfer the shared intra-class variation from base classes. Here are some detection visualization on Pascal VOC. We compare a fast RCN-based one-shot detector without and with a data generation network. We can see that data generation significantly improves the true positive detection while reducing many false positives, facilitating to improve the detection rate. So far, we have been focused on the performance of few-shot novel classes. In the real world, we often need to address a more challenging task of learning classifiers or detector on long-tail dataset with thousands of cat images, but only a single image of loris. Few-shot learning can be viewed as a subproblem of this more general, realistic long-tail recognition. The challenge now becomes threefold. First, we need to learn accurate few-shot models for the tail or rare classes. Second, we need to learn without forgetting and maintain good performance on the hand or frequent classes. Third, in the setting of the few-shot learning, we assume that each class has the same small number of training examples. But here we need to address a significantly imbalanced distribution. Different classes have significantly varying number of training examples. Well, we may generate additional data for the novel classes as before. Here I will show an even simpler strategy by reusing existing data for long-tail object detection and instance segmentation. Image resampling, RFS, is a widely used technique for long-tail recognition. However, for object detection, since each image might contain multiple objects, things become complicated. Here is a simple illustration. When we resample this whole image, we effectively resample all the objects within the image. So even frequent objects like the teddy bear are resampled. However, what we expected is not resampling the whole image, but resample only the desired rare objects. We implement this object-centric resampling OCS through a memory bank. We keep a memory bank for each class, which contains all features and proposed bounding boxes associated to any objects of that class. And we integrate our memory bank with a mask RCN model and perform object-centric resampling immediately in the beginning of the classification branch, after we have ROI features and proposed bounding boxes. Our final resampling method, our IO, combines both image and object resampling. Let's look at an image batch with these three following images. Again, let's imagine our target rare objects. Here are the gourds in our teddy bear photo. With our method, first we perform image resampling, which means the whole teddy bear image is resampled. Second, we perform our object resampling, where we specifically resample just the gourds objects. Now our bench contains 4 images and some resampled gourds. We compare against other resampling and revisiting methods on the challenge LVS dataset. Our approach achieves a significant boost in rare AP at 17.2 and 18.9 for detection and segmentation respectively. Importantly, we improve not only overall detection and segmentation AP, but also significantly improve rare categories AP. Conceptually, we could combine our resampling strategy with the previous data hallucination technique to enrich the variation of rare classes and further improve the performance, which we leave as interest in further work. So far, we have shown how to generate useful data in a learned feature space to facilitate visual recognition tasks. A natural question then is, how could we synthesize both visually realistic and useful images at pixel level? To answer this question, we propose a new task of joint few-shot recognition and null view synthesis. Given only one or few images of an object, a null object from arbitrary views with only category annotation, we aim to simultaneously learn an object classifier and generate images of that type of object from new viewpoints. These two tasks are inherently interconnected with each other. For example, the synthesized images can provide viewpoint variations for building a better recognition model. Meanwhile, the recognition model ensures preservation of the desired category information for view synthesis. So being able to simultaneously address both tasks within a single model is a crucial step towards human-level generalization. This joint task is also challenging. Because of weak supervision, where we don't have access to any 3D annotation, and a few-shot setting, where we need to effectively learn both 3D geometric and semantic representations from minimal data. To this end, we propose a fit map-based framework, FBNet, to tackle this joint task. The framework consists of a view synthesize module and a recognition module, which can run individually. And they are linked through feedback connections in a bow-tie fashion. The recognition module leverages the synthesized images from different views together with the original real images to learn a semantic feature representation and produce corresponding classifiers, leading to the feedback from the view synthesized module to the recognition module. The semantic features of real images extracted from the recognition module are further fed back into the view synthesis module as conditional input, leading to the feedback from recognition to view synthesis. This is a general architecture that can be used on top of any view synthesized model and any recognition model. The empirical evaluation shows that recognition and the synthesize facilitate each other. For example, the left result shows that the feedback-based joint training improves the 50-way one-shot accuracy on the bird species CUB dataset. On the right, we visualize the synthesized images. Compared with the state-of-art hologram baseline, our FBNet is able to perform controllable conditional generation, capture both the shape and attributes well, even in the extremely low data regime, thus generating images of higher quality and more diversity. Our FBNet also better maintains the identity of the objects in different viewpoints. Okay, so far we have talked about how to generate useful features or images. This is just a part of the story. Oftentimes, we are not lacking data, but lacking the appropriate annotation or labels. For example, in object detection, while we might not have enough annotated bounding box examples, we might have access to a large amount of images with image level annotation, such as ImageNet. So the common practice in object detection is to first pre-train a classifier on ImageNet, and then use the pre-trained weights to initialize the backbone of an object detector. The rest of the detector are initialized randomly. And the whole network is fine-tuned with the detection losses. The problem with this traditional classification pre-training approach is that, first, the tasks are misaligned. In the pre-training stage, it is a global classification task. While in the fine-tuning stage, it is a detection task, where the classification needs to be done locally. Second, the features are not explicitly pre-trained to do localization, namely bounding box prediction. Third, it is not able to pre-train the detector's specific parts, such as the region proposal network and the bounding box regressors. Based on this insight, we designed a detection-aware pre-training DAP to better pre-train object detectors. The whole pipeline is divided into 4 steps. In step 1, we pre-train classifier as Euro on this weakly labeled data, such as ImageNet. In step 2, we generate the pseudo bounding boxes from ImageNet with this pre-trained classifier. In step 3, we train a detector with the pseudo labeled data. Finally, in step 4, we transfer the pre-trained weights as initialization in the downstream detection task. Here, the pseudo box generation step is implemented by a simple class activation maps-based approach, which can easily scale to millions of images. Experiments of pre-training on ImageNet 1 million or 14 million and transferring to VOC and COCO dataset show that our improvements over classification pre-training is substantially large in the few-shot settings. In our most recent work, we consider multitask-oriented generative modeling. That is, learning a shared generative model that generates additional data to improve the performance of multiple pixel-level visual tasks, such as semantic segmentation, surface normal prediction, and depth estimation. While it is challenging to synthesize both RGB images and pixel-level annotations in multitask scenarios, our approach, MGM, enables us to use synthesized images paired with only weak annotation or image-level scene labels to facilitate multiple visual tasks. Experiments evaluation on challenging multitask benchmark, including NYU V2 and taxonomy, demonstrate that our MGM method improves the performance of all the tasks by a large margin, consists of outperforming state-of-art multitask approaches. So, in this body of work, I showed how we address few-shot learning at the data level by learning to generate the data, different from existing approaches like GANs that generate realistic images. We provide a new insight to generate data, including features or images together with labels that are directly useful for multiple visual perception tasks. We achieved this by combining generative models and discriminative models in various cooperative learning ways. So far, I talked about one important aspect of open world vision, how to learn more with less, and in particular with less data. From broader perspective, an open world AI system should be able to learn under constrained resources, not only with less data, but also with less time, less computation, less energy, and so on. This resource constraint limited the capability of our AI systems. In fact, such concept of bounded rationality is a fundamental aspect of human intelligence and artificial intelligence as initiated by Herbert Simon. Moving towards the open world vision, we would like to develop embodied robots in the wild that are able to operate in dynamic and uncertain environment, actively and continuously learn from ever-changing data stream and tasks, and make intelligent decisions based on limited information and constrained resources. The mental learning research so far has addressed a set of core component capabilities towards such agent. It will be interesting to extend this mental learning vision to deal with data of different modalities, address a broader range of complex real-world tasks under various types of constrained resources. Finally, the lack of data issue remains a universal challenge in nearly every field of machine learning. It will be also exciting to address few-shot learning and extend mental learning in a broader range of fields and disciplines. With that, I would like to thank everyone for your attention. Now I will take some questions.
Cool, thank you, Yu-Xiong. And Terry has a question. Terry.
So it's actually a two-part question. The first part, I'm going to channel Ali because he actually made a comment earlier today that I've often wondered about and never followed up on. So in the few-shot learning problem, right? So I understand you have a base set of classes, and then you're trying to learn the new one. Now, so from my point of view, open world learning includes detecting. Have you done any work where you first detect that it's unknown and then try and do the few-shot learning? And if so, how much does that impact your performance?
That's a pretty good question. So often in the few-shot learning regime, these two tasks are tackled separately, right? So in standard few-shot, you assume you know base and novel prior. But in novel object discovery, you don't know this, you're trying to do this. I think that is a very good point. We are actually working on this. So there is some kind of preliminary investigation is that in classification tasks, it's easier to decouple base and the novel. But in detection tasks, it is much tricky. So for example, you will have unknown objects that when you learn something on the base categories, right? For example, on COCO, you have already accessed this kind of objects, but you don't know it. You just treat this object as a background. You learn something. Now you have novel classes, which you have already known before, but you don't know label. You also want to know this. This is one scenario. The other scenario is you have some kind of novel object you haven't accessed before, not only the labels, but also the data. We found that it looks like the learning behaviors for these two type of novel categories are different. If we would like to tackle both novel object discovery and the few-shot learning of the novel categories. So there is some work in this direction. I completely agree with you. This is important.
So my second question is actually more directly related to some of the stuff you said. So you worked in generating features, right, to do the training in the first part of the talk, right? And,
yes.
And I've seen a couple of these papers, and I've never understood, how do I know that the generated feature is actually still in my class or is outside my class, right? Because the definition of what's a class is so subtle, especially if I'm dealing with impoverished data. I don't have many examples. How do I know when I'm stopped generating examples that should be in my class and when they should be outside my class?
That's a very good question. The short answer is no, we don't have any guarantee of that. So we also don't know actually the distribution of the generated data in this case. But the thing is that if you do some kind of post-analysis, for example, something like the visualization here, for example, once you generated this data, right, you can sort of visualize what the generated data look like in certain feature space. And also, because this is a kind of held out novel categories, you have a lot of data. Actually, if you are considering this is on ImageNet, you can sort of learn the actual underlying large sample classifier and trying to investigate or analyze if the generated examples are still within these categories. So this is some kind of post-analysis to investigate whether the generated examples are still within the desired category. And the way we enforce this is, for example, here we don't enforce it explicitly. What we want is that just the classification object. For example, you learn the classifier H based on the generated data and the real data. You hope the classifier learn on that will achieve good performance on the held out query data. So this is kind of one supervision to enforce you generate the right features or data. So, but this is not enough. We have some follow-up work in this direction. Essentially, you want to enforce some kind of self-supervision to enforce. For example, you can imagine in standard self-supervision, you learn feature representation. But here you can use it to guide the generation of the data. For example, the data generated from the same category should be close to each other. At the same time, the generated data should be far away from each other if they are from different classes. This can be sort of enforced by some kind of contrast learning. Yeah, thanks, Terry. I think this is a very good question.
Abhinav, you're asking?
Yeah, last quick question. So this, like, we haven't tried your work yet, but we played around with some of these feature generation methods following up on Terry's question. And once you generate 2, 5, 10 features, things are fine. But as soon as you go beyond that number, the performance drops drastically, which kind of indicates that you're just doing like some sort of very local data augmentation, but not being able to generate what is claimed, that you can see a side view of a cat and generate a jumping cat or something like that. So do you have any like plots on how much you generate and when does the performance plateau or drop, or what happens in those situations?
Yeah, that's a good point regarding this part specifically. So here, the evaluation is not just a simple 5-way. In fact, we are trying to do the investigation on the full set of novel categories. So that is a 311 way.
No, I mean the number of samples you generate using your method.
Oh, I see. So the short answer is that the performance increases first when you generate more and more examples, and then it becomes saturated. Sometimes it will drop a little bit. So that is the kind of observation we found. So we also do some kind of visualization here. Although here we show that the generated example is kind of different from city example, which is the input of a generator. But if you consider here, essentially this kind of generator, you still have the mode cleft issue. It is really difficult to capture the entire distribution from just one set. That is the reason if you generate more data, it probably just will make the performance saturated. Roughly in this case, we generate like 20 examples per class that achieve the best performance. Once you go beyond that, you still have some boost and some not that significant. Yeah, thanks, Abhinav.
Yeah, thanks.
Okay, the next one is so thank you, Yu-Xiong. I guess I have to introduce Abhinav as the next speaker. So Abhinav is a professor, assistant professor from UMD. He has done a lot of work in computation and machine learning, and his research spans much of the topics about data and labels. In my word, he's a guy that cares about the open world. So Abhinav, please take over.
All right, thanks you. All right, can everyone see my screen? Okay, awesome. So today we'll talk about reviving object discovery, and we'll see why we need to revive it, where we are coming from, and where we are going. So before we go into detail, if it wasn't clear from the title, we will talk about object discovery. It's a fairly generic setup where, given a bunch of images, we want to extract objects that are present in those images. So for example, you might want to find extract all these regions, group them together, and call them cluster 1, cluster 2, and so on. Now, this is beyond just finding region proposals. You have to group the regions together and know that these regions correspond to each other or not. And there is no easy way to know that that particular cluster is a cat. So all we put them are numbers on these clusters. This is category 1, this is category 2, this is category 3. So in this case, for example, we discovered 7 categories out of these set of images. So this problem setup, like object discovery, is a general term. We will see how general it has become over the years. But this is also called like object category discovery, or discovering object classes from a set of images. All right, so with this background, this is the definition that we are trying to handle. What we'll talk about is where we are. So like, what were some of the classic works? And by classic work, like, I think pre-deep learning is a classic work these days. Why is it not fashionable anymore, or not many people work on this? According to like my personal take, it's supposed to be controversial. Why does it need reviving? And where to next? So we will also propose some solutions in terms of, you can call it a benchmark, that, hey, this is how we can evaluate, try to bring all these different definitions together, provide some simple baselines that can serve as the basis for future research in this direction. All right. So with that background, let's start with some of the classic works. So one of the early few works in this domain of unsupervised object discovery. So all you are given is a bunch of images and nothing more than that, right? You have some bottom-up segmentation method and so on. And the goal is, given these sort of images, you want to extract these different objects. So on the left, it's work by Brian Russell et al. It's CVPR 2006. Where they do multiple segmentation, have topic models and stuff like that underneath, and they are able to discover these clusters together. On the right is Henry Kang's work from CMU, where he takes an activity of daily living data set, tries to cluster regions together again, do some more analysis on top, and extract these objects of daily. So the things were all good. Then we are starting to look into more problems beyond just Pascal dataset. And then this awesome work from Yang J. Lee and Christian Grauman came about, two different works which tried to use knowledge as the basis for discovering more classes. So I call this assuming prior knowledge, and your object discovery is driven by knowledge. So you know about sky, you know about house, you know about a driveway, and now you have to discover that, oh, given this context, if this is a particular object or not. The same context repeats again and again. You have some visual similarity between the object, so you can discover it and say it's a new class. And they have this phenomenal sort of feature extractor called object graph, which they built using this known knowledge. So after that, things took an interesting turn. So deep learning was picking up, larger and larger data sets were coming out. And then we moved into this new world of object discovery in internet images. So some of our prior work on Neil and everything were also in this regime. The regime was, you start with some search like car, search the internet. You have a bunch of objects, and now you want to discover segment objects in these set of images. It's still challenging. You have a bunch of noisy images. You have images that don't correspond to that particular object. And so you have polysemy and so on and so forth. And you want to discover these objects together. Now, the problem was, given the generic setup that we were early on, we moved into a more canonical image setup, which the problem by definition became more co-localization and co-segmentation. And I'll show you a particular example of co-localization and co-segmentation later. And generally speaking, a lot of these kind of approaches relied around this weakly supervised setup. Some call it unsupervised, but I would refer to them as weakly supervised because, you know, in these 100 images, there is like most of them have car present. So different bags of trading and stuff like that, but it's still single category in a set of images and you're trying to discover them. So starting from these, then we moved into, again, back to the original object discovery. Instead of segments, we moved back to regions because region proposals were popular. But most of the approaches under the hood were these co-localization approaches. So given a set of images, you know there are multiple classes and no labels. You want to discover which objects are shared between different images. Now, it can be argued object discovery is a co-localization problem, but given the trend that we were following, most of these approaches are built on doing this kind of pairwise reasoning. So you have two images, you try to connect those two images together, and then you have two more images and form a giant graph formulation over all the regions in a data set. And as you can imagine, not that scalable, so you like improve the scalability, reduce the data you're dealing with, and so on and so forth. So this is kind of the trend of, and again, I'm just following some of these work. Of course, there have been scores and scores more work every conference on object discovery, but I'm trying to give a very broad brushstroke picture from my perspective. Okay, so this led to what I call these multiple personalities of object discovery. Like different people, when they talk about object discovery, they can mean different things. Everyone justifies, like to full credit to different authors, they justify that they are doing object discovery in this setup. It's more than co-localization, but less than this. And everyone explains what it is. But it still becomes an issue when terms become overloaded, right? So these multiple personalities of object discovery, we started with this unsupervised clustering, segmentation, extract segments, extract topic models, cluster them together, and so on. Moved into how can we use knowledge to cluster more, build object graphs. Then we moved into this internet image plus noise regime, where we can rely on canonical images. They're sort of weakly supervised. Your approaches generally range from co-localization, co-segmentation. Then we move back to Pascal style images and regions. But these kind of approaches persisted. So co-localization is the rule of the land. That's how we solve these problems. Some of them are still unsupervised. We extract unsupervised region proposals and then hog features and stuff, sort of weakly supervised in the way we will build our data sets, but they still refer to them as unsupervised. And then we came to this new world of deep features. So we started throwing deep features at it. And that's where this definition of unsupervised also gets a bit tricky, because you can claim you're discovering car without any labels, but you have trained on ImageNet, which you have already seen 200 car examples in, or 200 car classes in. So it's not necessarily unsupervised, and I think we should be more careful about these kind of semantics, even when we are using feature extractors. So my personal take is around this time when big data sets were coming out, internet images were becoming more popular, there was a break in this flow that we are following, and we started 2 different rounds of work for object discovery, tried to combine co-localization, co-segmentation work into object discovery, and then things got messy. And that led to a lot of issues, according to me. And some of those issues are, so we changed the kind of approaches that we use. So on the left, we talked about, generally speaking, clustering-based approaches, where you want to associate different things that look closer, similar to each other, to co-localization approaches, which had weird assumptions. So the assumption is, if we are talking about these 2 objects, you want to segment these 2 people, and there are no other objects in this image. But for the same image on the left, if I give you another image which has a bottle, you want to segment out these bottles, and there's no other object in this image, right? Of course, you can keep doing this for all different pairs and then put all the segmentation masks together and call that discovery. And that would certainly be a valid way of doing it. But unfortunately, we never took that additional step because it just wasn't scalable. Another big issue that happened when we started conflating object discovery with co-localization or co-segmentation is this issue with metrics. Now, of course, even back then, metrics were not that great. We didn't know how to evaluate these things. We had precision recall curves for whatever labels we had. We took average precision for a single number. We had purity, number of clusters, qualitative, and so on. They were not perfect, but they had less flaws than where we went to. So we started co-opting, because our approaches are based on co-localization and co-segmentation. We started co-opting co-localization and co-segmentation metrics. So correct localization or correct detection and detection rate and so on and so forth. And I think it does deserve to discuss that in one side channel, that for people who don't know these metrics, I just want to give you an idea of how broken some of these were. So just as a side note, so correct localization is percentage of images where any single object is correctly localized. So in the scene that you're seeing, if you're seeing my video right now, if you localize that printer in the background and nothing else, you just still get +1 for that image. Correct retrieval. So given a particular image, you want to retrieve nearest neighbors. And as long as they have the same object shared in them, you are all good. No matter if you're discovering other objects or not and so on. And this funny detection rate metric, which was nothing more than just a standard recall measure. So if you are using a region proposal network underneath, it's just the recall of your region proposal network. So I don't even know why we talk about detection rate. Now, standard issues, correct localization and detection rate. They test co-localization capabilities because that's what they were built. They are good metrics for that task, but not necessarily for discovery. Correct localization and correct retrieval, again, assume that the number of instances you have per image is just 1. Or as long as you can get 1 object correct, that's all fine. Which might be fine for co-localization datasets or these internet canonical image setups. But when you go to Pascal and Coco and stuff, this just doesn't hold. And again, detection rate is just recall of your underlying proposal system. So no matter what you do on top, you are bounded by the recall. That's the performance number that you get. So that was another issue, metrics. Like we started conflating discovery metrics with co-localization metrics. And finally came this scene of datasets. So back then, we tried this Caltech, MSRC21 classes, MSRC-V2, ADL, Label Me. We were trying different things because there were no set standards. Then internet images came about, and then we started using internet images for most of these things. But then we wanted to show it on more generic Pascal setups, but things wouldn't scale. These metrics wouldn't work on those setups. So we created our own data sets. VOC 6 class 2. So we take 6 classes, car, horse, and so on, sample 2 viewpoints of those classes because Pascal has that ground truth. So just left and right viewpoint and use that as our data set. So some will do just 1 class, some will do 3 classes, some will do 5 classes, and so on. And then depending on how scalable your method is, you will show it on a subset of 2,000 images or a subset of 5,000 images or 10,000. I think the max that I've seen is 10,000 images back then. So that also became an issue, that everyone had their own setup depending on what all they could do. And that leads to a big issue if we are trying to work in this space. Do you try to do these clustering style metrics, or do you do co-localization because that's the metrics that you'll be evaluated on? Do you work with these data sets that don't really capture the task that you're doing? Or do you go back to some other data set or those earlier data sets? And then we have our favorite reviewer too. No matter what sampling of approaches you pick, there'll be some that you don't, and the reviewer too will say you didn't pick that set of approach. Right. So there's always this missing hole that lacks. And I think the reason why we are here is this lack of consistent task definition. Like object discovery is a very, very general term. It's objects and we want to discover them. Even region proposal generation is object discovery. So everyone has their own interpretation. Everyone wants to solve a slightly different problem setup, which is all fine. But that leads to this issue where we don't know how to compare apples to apples for good science. Second issue, I think, are scalability issues. So none of these approaches can scale to, I think one of them can scale to 10,000 images with 5 or 6 objects, but most of them cannot scale to either large number of images or large number of object categories, or just complexity where you can have more number of objects per image or just the total number of objects that you deal with. And finally, a lot of these approaches do rely on this global reasoning that we want to reason on all the boxes in the entire data set all at once. And to do that, you need to fit features in memory, and you cannot do that. If I throw in a new image, you cannot process it online. You have to go back and look at the whole thing again. So that also makes it slightly more difficult to scale it up to the kind of data sets that we want to scale up. So this lack of consistent task definition also gives rise to these problems with current benchmarks. So current benchmarks, and again, I'm not calling out any particular work. This is just a combination of like different things that, again, 50, 60, 100 papers in this space use. They have some or the other of these issues. For example, they might not be realistic in terms of complexity. So if you want to do COCO style object discovery, you might be doing an internet images data set that might not capture it. Unrealistic assumptions that there's only one object per image, for example. Some of them are designed more for classification than for discovery, right? And like I've said enough times, a lot of them are suited more for co-localization or co-segmentation as opposed to doing in the wild object discovery. And finally, some data sets are good, but you cannot really evaluate a lot on it because there are no labels that you have to see how well did you discover objects. So to fix these issues, we in one of the recent work that we uploaded to archive, we proposed a slightly different take to this problem, which is see what all people have done, try to generalize it into a setup which we hope people will like more. And this is kind of inspired by this notion that like Alyosha talked about labeled data sets and stuff. So suppose we have a compromise with Alyosha and say that Pascal VOC was the last labeled data set that you're allowed to have for object detection. So that's the last of the labeled data set, right? Then you have this nice big data set called COCO. We can just treat it as our in the wild setup, right? Now, we went through this debate today multiple times that still not really open world. You can see a lot more things. But I would say that might be a good enough starting point, that even if you assume COCO is your in the wild setup, let's see how Pascal detectors work on COCO. How can we discover new objects on COCO? How can you do open set, open world recognition, all those in this new, your open world is COCO, your closed world is Pascal, and that's the new world we are in. So what would happen if you train a detector? So you train a detector on the 20 classes that you have labeled on Pascal, right? The standard detection output that you will get on a VOC image is something like that. But on COCO image, you will get these kind of detections where you'll have this incorrect detection on a bear, where it might call it a dog or a horse or something like that, right? So incorrect detection will happen because of out of distribution setups. In this benchmark, the goal would be to actually find out which of the first find out these are out of distribution, if that's how your framework is working. Then try to put them together and say that all these things belong to the same class. Now, there is some notion of co-localization in this. You can treat it as a co-localization problem and solve it, but it's much more challenging, much more large scale and complex set of images. So you want to discover these bears, these street lights are same. All these red ones are known objects. So you put boxes around people and cars, and all of them are known from Pascal. And these pink one is bear, this orange one is street light, you have tie in green, and so on and so forth. Okay. So, and again, I'd be more than happy to debate the pros and cons of doing something like this in terms of a benchmark. So we treat last labeled data set. Again, we have ImageNet and Coco and Pascal, because we are in deep learning world. We want to pre-train on deep learning. So your training is, you pre-train on deep learning on ImageNet and your object detector on 20 VOC classes. Now I have the ImageNet star there. So star because you actually remove the Coco classes that are unknown. So Coco has 80 objects, Pascal has 20. So Coco has 60 unique objects. So you remove all the classes that overlap with those 60 and create a reduced ImageNet set. And that's what you train it on. So that when you're quantitatively evaluating, you can say, I've not seen labeled data for these particular classes before. Okay, and then we have more details in the paper about that. So training, pre-train on ImageNet, reduced set, which has never seen those Coco 60 classes or overlaps, and detector on Pascal. For testing, you detect your known 20 VOC classes, right? So that evaluates your standard object detection. You can evaluate your open set detection. That is my car classify firing on a truck or not, if you have never seen truck in Pascal VOC. You can do semi-supervised learning, collect more labeled data, add it to the set, and improve your classifier. So just evaluating on known classes helps us support this. You can do quantitative evaluation on unknown classes. And this is something that was missing from a lot of prior works. So we know we have labels for the 60 Coco classes. So you can perform object discovery evaluation on these 60 Coco classes. And then you can do qualitative evaluation on a lot more classes than 60 for object discovery, right? Because we just don't have labels for them right now, but hopefully some good Samaritan will collect those labels and we'll be able to do quantitative evaluation. But at least for these 60, we can do quantitative evaluations, right? So what are some of the benefits of this setup and what all does it try to fix the issues that we had seen in the past? So I would argue one of the big benefits is these data sets are widely used and well understood. We know the performance that your detector will get if you train it on all 80 classes. So this is sort of an upper bound. No, not exactly upper bound like I've debated this with Takeo enough. It's sort of an upper bound. You train on all these labeled data, this is the performance that you get. The discovery set is quite rich. So you have all known classes present in those set of images, a variety of unknown, and the unknowns are related and unrelated to knowns. So you have to worry about semantic drift, you have to prevent out of distribution setup, and so on and so forth. They have a lot of images that are distractors, which doesn't have any of the knowns. So that I think breaks almost all setups in the previous data sets. Images are complex, Coco images are complex, you already know. Data set is large scale enough, there are 80,000 images in Coco, you can split and dice things different ways. And it's focused on localization. So we have bounding boxes available at least to evaluate those 60 classes. So we can evaluate how well we are localizing. And whatever future work happens on these data sets, for example, Elvis, the federated learning data set that they collected, we can always evaluate on those because they are built out of this Coco data set. So if they collect more labels, we can always evaluate on them. In terms of difficulty, even with these 60 unknown classes, it is extremely challenging. It surpasses the scale and the difficulty of everything that people have worked on in object discovery. Images are very, very realistic. Performance is so low for a reasonable method that reviewers just say this is an impossible problem and reject the paper every time they see it. There's distribution shift. So you go from VOC to Coco. So there's some distribution shift. The images are more complex, more objects per images, large number of distractors. So there's no known class in a lot of images, which breaks most of the current methods. And you have to worry about semantic drift. You have to detect that bear, zebra, truck are actually separate from dog and horse and car. Otherwise, your detectors, if you do semi-supervised learning, start doing semantic drift very, very quickly. Right? So that's the benchmark proposal that we have. What kind of evaluations can we do on it? Now, this is a slippery slope. We don't have all the answers figured out. We hope the community can tell us some better ways to evaluate it. Just to keep some reviewers happy, we have the co-localization recall metrics, all the standard one. Supported, but we recommend discontinuing it, and we hope that people stop reporting it and people stop asking for them. There are these discovery or pattern mining metrics. So cumulative purity versus coverage plots and so on. There is AUC. I know Terry doesn't like reducing them to one number, but you can do plots. You can do that. You can actually evaluate the number of novel objects you discovered. You can do fragmentation metrics. You can do clustering-based metrics. You can do a lot of those metrics. And my favorite, you can do this oracle detection metric. So one thing that we can do, we cluster all these objects together. We can give them to Mechanical Turk and ask labelers to give us one label per cluster. And once they give us that label, we combine all the streetlight clusters together and train a detector. So instead of going through this active learning framework or trying to ask users to give us labels, which might not be reproducible across methods, we can use this oracle detection metric where we use majority voting from the ground truth labels that we have. So we won't be able to do this for beyond those 60 COCO classes. Train a detector for those 60 unknown classes and test on the COCO minival set. It's reproducible. Everyone uses exactly the same annotations. Everyone can have their own way of how they want to do the majority voting, but at least everyone has the access to the same set of labels. So this oracle detection metric can show us how good of a detectors are we trading by doing this in the wild setup, right? So that's the benchmark that we want to pitch, or I want to pitch. Now, when we talk about this, it always brings up a lot of different other types of areas that people have explored. So I call this, doesn't this sound like X, right? So I'll move through this quickly to talk about a baseline, because what good is a benchmark if you don't have a decent baseline to beat on it. So I'll go through this quickly, but some of the areas this is similar to is this never-ending learning or Webley supervised learning, our work on Neil and this work on Levan by Santosh Devala and Ali Farhadi and folks. There are some key differences. I would say the primary difference, which according to me is the most important difference, is that these methods were more language driven in the sense that they start with an a priori list of, sorry, there is a bug, spelling mistake, a priori list of concepts. So they start with, I know I want to search for car and bear and dog and horse and so on and so forth. Then they search online, find these images and train models for it, right? So that's a big issue, because now in this particular image, for example, there are buildings and there are bridges, and you'll never discover those objects because you never set out to find those objects. So you're kind of limited by the words that you start with. Second, I think almost all of these type of approaches rely on some canonical images that, hey, there will be enough canonical images in my data set that I can train a detector on the full image, fire it on the rest, and then localize these small ones. But they can never start with a complex image. They ignore the complex images in their first few iterations. And finally, these are not public data sets. They're crawled images from the internet. They haven't released. I don't think they can release those images. And every day, these images are changing, depending on how Google and Flickr and everyone are changing their algorithms. So we cannot really have an apples to apples comparison with any of these prior work. So I think it's important to have a set of open world images which we can actually, all of us can compare on the same set of images. Then open world recognition, Terry talked a lot about it. So there's a subtle difference. You reject unknown classes, then you collect labels for those, and then you train a detector, where with this human annotator in the loop is the difference. But you can always cluster those things together and do the same oracle thing we talked about, and that can potentially be done on this data set. There's online learning for new classes, there's incremental learning. We have had enough talks about these. There is continuous, semi-supervised, omni-supervised. All these are related fields, but there are differences, or there are some are subset of this benchmark that you can do on this benchmark. All right, so that's the benchmark that we want to propose, and we'll see like how it takes up. But the next thing I want to talk about quickly are some ways of doing object discovery, some very, very simple techniques. So what is the simplest approach you can think about trying on this data set? You take a pre-trained ImageNet network or ImageNet, reduce that network. You train a class agnostic region proposal model. Then given all these COCO images, you run the RPN, extract all these regions, extract deep features from the same network, cluster them together, and you're done. All these different cluster labels that you have basically give you your classes. But this, as simple as it sounds, this has a lot of issues, and people who have tried these kind of frameworks would know the kind of issues that this might run into. So one issue is scalability. So if you only take 300 regions, 80,000 images, you have close to 24 million features. any clustering on large scale feature space especially has issues with it. How many clusters is an issue? What should be your K for K means? If you do fringe, what is the level at which you should sample? What should be the complexity of objects? Should you cluster people? Should you cluster clothes? Should you cluster car, wheels, windows? And we don't solve all these issues with our framework, but this is an important object recognition discovery question anyways. And there's not a satisfactory way of dealing with background patches. Like these clustering methods cannot throw out a lot of background data and just keep the important stuff. So our solution, first of all, we have a baseline which does this clustering thing, makes it scalable by running it on a subset and then doing label propagation like semi-supervised learning and stuff like that. But we also have another approach for this online discriminative clustering thing, which is inspired by mid-level patches work from Saurabh Singh from ECCV 2012. Very, very high level description of concepts. Starting from regions, you want to separate them into two groups, known concepts and unknown concepts. Now, known concepts are objects that look similar to your VOC objects, so those 20 classes, or similar to the discovered objects. So if I've already discovered a bear, it should look similar to a bear. Unknown concepts, they're similar to some unseen patterns that you have started seeing, so you have started recognizing them now, or they're not similar to anything that you have seen before. So in our approach, we have this dual memory formulation. So we call these known concepts as semantic memory. We know about them, we can model them well, and this working memory, where we want to just accumulate more and more information as we are seeing it. And then we'll try to group them together as we go on. So given an image like this, semantic memory, you get a bunch of known classes, you put some regions for person and car in these clusters, and then you build these unknown pattern clusters or unknown pattern slots in this memory. Now, given this new image, you want to do reasoning of assigning it to, again, these two groups, and this is how your new set of examples or patterns in the memory look like, right? But how do you do this, and what do you do once you have something like this? So there's some properties you have to be careful about. So for semantic memory, it has to be discriminative. It's a classifier you're training. It should be very selective because this is what you're treating as my known objects. Should be fairly fast to apply because you want to check it on a lot of images. It's fine if it takes some time to train because you won't update it this frequently. Like this is known concept. You have to be very confident to put something in here. And working memory, you're just collecting data and grouping them together. So it has to be super fast to compute. It will be updated very, very frequently. So you need a fast way to do that. And once you have enough support or enough examples of things in a particular memory slot, for example, you will just update a list of concepts with that particular concept. So one very trivial way you do this, you'll take a concept that we saw before, train a classifier, do some self-cleanup, introspection, take the positive side, train a new classifier, and that classifier gets added to the memory, right? And this is like enough people have done enough things around it that I won't go into too many details. But for the left semantic memory, you can train an ELDA classifier from Bharatari and et al. So update new models, train new models. Decision is just ELDA score. On the right one, you need an online clustering method for these slots. You can maintain a centroid. You add a new example if you want to create a new slot. And similarity with existing centroids is basically what becomes your decision, right? Skipping over all the details in this framework, which are these bullet points which we won't go over. I see Shu here. So Shu, give me one more minute and I'll wrap up. All right. So we start with this working memory and semantic memory. You extract new regions. You try to do this retrieval operation in memory processes. You have this retrieval operation where you want to decide, right? Does this belong to a known, an unknown, or should I create a new cluster? So if it's known, you update the semantic memory. If it's unknown, but you have previously seen it before, you update one of these slots. You have not done it again, you've not seen it ever before, you create a new slot, right? Continue it for a while. When your memory is full, you consolidate your memory, learn new concepts, and you move on. So that's a very simple online clustering way of discriminative pattern mining work, which leads us to discover these kind of classes. So these are some qualitative results. These on top are labeled unknown. So we have ground truth labels for these so we can evaluate, put a label on them. And these are some other clusters that we don't have ground truth labels for. So these are labeled unlabeled unknowns. You can take that Oracle label that I talked about and train a detector. So you can see that for fire hydrant, you get close to 4.8 AP. For bare, you get around 17 AP. You can try different IU thresholds and so on and so forth. Baselines are a bit iffy. We do k-means and fins and make them scalable. You can do all the different plots that we have discussed throughout the day. To evaluate with some other object discovery co-localization methods, we have a smaller scale setup as well, but I want to get rid of this. People should stop reporting on those small scale and those metrics. So with that, these are just some more examples of the clusters that we have discovered. We have a website where we have more examples. I'm more than happy to take questions and discuss the benchmark and whatever have you. All right, with that, I'll give the control to Shu. Thank you.
Thank you, Abhinav. Any burning questions from the audience? I guess not. All right. Thank you, Abhinav.
All right. Awesome. Thank you.
Yeah, I'm going to introduce our challenge, the championship of the challenge team. So cool. Yingwei is on board. So he's representing JD AI Research, which is a top research institute in China. His team won the teaser challenge. So I believe he has many insightful techniques to present. So please, Yingwei.
Oh, okay. I will share my screen first. Okay. Yeah. Good afternoon, everyone. I'm Yingwei Pan from the CV lab of the JDI Research. It's my great pleasure to present and share our system for the Open World Vision Challenger today. Actually, it's a collaborative work with my colleagues, Yehao Li, Chen Yang, Jin Yang, Wang Yu, Yao Ting, and Mei Tao. So the key contributor is Yehao Li. Meanwhile, I also want to thank for the challenge organizers for hosting this wonderful challenge. The key task for our work is OpenSet image classification that performs K+1 way image classification that distinguish the novel, the semantic null, unknown, for example, the OpenSet test time examples. So this is the outline for this talk. First, we will introduce the main task explored in this track. Next, several preliminaries are present, which will be adopted to compose the main framework. Finally, we will present the detailed architecture for our framework, composed with the corresponding experimental results. And first, the key task for our work is the OpenSet image classification that performs K+1 way image classification that recognize the testing examples with the predict class label if it comes from one of the key null classes, or with the K+1 label if it's an OpenSet example. For example, from an unknown class. Here, note that the novel images in validation test sets contains some novel classes. That means the unknown in training are also called as the OpenSet examples, which with the novel attributes, a novel subclass, and also augmentation novelty. So before introducing our detailed systems, I will introduce the preliminary technologies behind our system. So we also frame this task as a typical classification problem. So the first question is how to pre-train a backbone better. As we all know, the most common way for pre-training CV is the ImageNet pre-training backbones, which can be easily adapted to the downstream tasks by just fine-tuning. However, in these challenges, as we all know, any annotations from ImageNet cannot be used. So here, instead of just training from scratch, we adopt the recent famous unsupervised feature pre-training technology, which named as momentum contrastive pre-training, that is MoCo. So this MoCo will train a visual representation encoder by matching encoded query queue to a dictionary of encoded keys with contrastive loss. The dictionary is then built as a queue with current minimum batch enquire and the oldest minimum batch decode. The keys are encoded by a slowly updating encoder, driven by a moment update with a queue encoder. And after we pre-training the backbone in an unsupervised way like MoCo on the training set, we will further fine-tune the backbones with the parameters initialized from this pre-trained model. So meanwhile, we also adopt the supervised MoCo pre-training, different from the self-supervised contrastive loss that just contrastive a single positive for each encode against a set of negatives. So here, for the unsupervised MoCo, so here, okay. So here, different from the unsupervised MoCo, we just treat the augmentation of a single sample as its positive samples. So here, the supervised MoCo will treat all samples from the classes as the positive samples. And then after pre-training the backbones with the supervised MoCo, the backbone can be further fine-tuned on the training set. So next comes our key contributor, that is how to design a better backbones. So the transformer with self-attention has led to the revolutions of NLP field, and recently indeed inspired the emergence of transformer-style backbones in CV domain. So here, we also design a new transformer-style backbones, named under the contextual transformer networks. Different from the conventional self-attention, which solely explores the isolated query key pairs to measure the attention metrics, but leaves the rich context among keys on the exploit. So here, our contextual transformer blocks can capture the first order context among label keys, which is further leveraged to trigger the self-attention that might the second order context. So just to see the figures, this figure on the right, first, our COT will first mine the first order context among keys via 3x3 convolution. And then based on the query and the contextualized keys, 2 1x1 convolutions are utilized to perform the self-attention, leading to the second order context. And then we will fusion both the first order and the second order context to compose the final output. So this ways can unify both context mining and the self-attention learning into a single architecture for visual representation learning. So after here, I also want to introduce how to plug our device, the COT block, into a ResNet style network, which can compose the transformer, the contextual transformer network, named as the COT net, which will be act as the key backbones in our whole system. So here, I will show how to construct the COT net. Specifically, the COT net 15 is built by directly replacing all the 3x3 convolutions in ResNet 15 with our COT blocks. This table shows the effects of utilizing different replacement settings on the 4 stages, the REST 2, REST 3, REST 4, and the REST 5, the stages within the RESTnet architecture. So here we can see by just replacing the last 2 stages in RESTnet 15 with our COT block, we can achieve the most performance boost. That's why we only replace the 3 multiply 3 convolutions in the REST 4 and the REST 5 stages with our COTs under this SE RESTnet 15 backbone. Moreover, as shown in this table, compared to the SE RESTnet, our SE COTNet D can achieve better performance. Next, I will show our COTNet, the performance on the ImageNet compared with self-observation backbones. So from this table, we can see our COTNet with 152 layers can achieve the same performance with RESTnet RS, which has 315 layers, while the training and the inference speed is much faster. So after introducing how to pre-train a bad backbone and how to design a bad backbone, now here comes our overall framework for these challenges. So here we adopt the self-supervised learning ways to construct the whole framework. So where we treat all the training data as a labeled samples and all the validation or testing data as unlabeled tests. And then we perform self-supervised learning also can be treated as the semi-supervised learning. So here, our system actually the 2-stage architecture. So for this open set classification task, first we will, in the first stage, we will train the networks. For example, the COTNet, EfficientNet, RESTnet from scratch or initialized from the pre-trained model, which is pre-trained by MoCo or supervised MoCo. And then we will achieve the pseudo-label for each unlabeled test samples by averaging the predictions of the 16 models. And then we will fine-tune the backbones over-label the training data plus the test samples with the predict pseudo-labels. So after training each backbones, now we will have we will introduce our bird type fusion, which can fuse the probabilities of the 11 crops by bird instead of just a simple average. So here, the 11 crops means the whole images, the 4 carbon corners, and the central crop, plus their flipped version. And then we utilize the probabilities as inputs to train a 2-layer bird type model for pertaining the final probabilities of the images, instead of just simply averaging them. The parameters of the bird models are shared for all backbones. The final results are obtained by averaging the probabilities of each backbone with bird type fusion. So here comes our experimental results of our 2-stage systems on the validation set. We first show to further fully explore the effect of pre-training, we show the performance or from the training from scratch or pre-training. In the results across different validation subsets shows that consistently indicates the advantages of pre-training. For example, after applying the Moco VI or supervised Moco VI into the ResNet RS15, the consistent performance boosts are observed. And then one further utilizing the pseudo-label, also our semi-supervised learning manner, we can achieve also the performance boost. And then next, we also evaluate our COT net 15s on the validation set. So we can see our COT on validation can achieve a better performance compared to the ResNet RS. And then our COT net can exhibit better performance when further equipped with the 10 crop average. So here comes the performance on the testing set. We just show the final performance of our submitted systems with different settings on test set by simply ensembling 9 models. That means two kind of COT nets, 152, and the 3 COT net 101, and the efficient net, RegNet, YResNet, ResNet RS, without any pseudo-label fine-tuning and bird fusion. We can see the macro top one accuracy can achieve the 18.1.7, which is already the best performance. The performance is further improved to 18.2.6 by additional using the pseudo-labels. And finally, our system can achieve the final result of 18.3.6 by ensembling 16 models with pseudo-label and bird style fusion. So thanks for listening. We will release our systems and all the source codes through the GitHub. This is the link. And we also will archive our our report for these challenges and also the papers for COT-NET in the recent days. So welcome to use. Thanks. Yeah, that's all. Yeah.
Thank you, Yingwei.
Yeah.
Oh, Terry has a question. Please, Terry.
So nice presentation. Parts of it were very clear. You trained the pseudo-label stuff using unlabeled test data. But for your Moco pre-trained, what was it pre-trained on for your Moco V2? Was it on just the training data, train plus val, train plus val plus test, or ImageNet?
The Moco is trained over the training set.
Okay, so Moco didn't use a test set, only the pseudo-label part used the test set?
The Moco is only pre-trained over the training set. And we also pre-trained the supervised Moco over the training set. Yeah, just over the training set, yeah.
So why do you feel it's appropriate to have used the test set and the pseudo-labels on the test set to train your final features, as opposed to treating the test set as you get an image and you respond?
I think the unlabeled testing samples is indeed very important for the open set samples. Actually, this is the experience from our previous challenges. We also attend many the DOM adaptation problem challenges. For example, the Vista, we always adopt such two-stage systems which can show the indeed very surprising performance on the cross-domain, or also we can treat as the open world problems here. So that's why we choose the pseudo-label. Also, we can treat it as a semi-supervised learning to tackle the new samples from the open set class or a new domain here.
So yes, you can always do better if you train on the test set. Doesn't surprise me.
Yeah, that's just one reason. But we also compared many backbones, and we show our transformer style backbones also contributes the most performance boost. Yeah.
mean, it does seem, this is Tom Dietterich, this does seem like it's a problem formulation question. Are we in the transductive setting where we're given the test data, or are we in the sort of online setting where we get one instance at a time? And depending on the application, either one, it would be interesting to know if we, and this is more a question to the organizers, suppose that the data was in batches of, say, 100 images per batch or something, and you had to process that batch before you could see the next batch. You had to give your answers, which probably would be more realistic. I think it's rare in an application. You can't wait until the end of the year to do all of your recognition tasks in a web application, but you could wait to the end of the day. So I think maybe you sometimes have a natural batch structure.
Yeah, so Tom, Terry, yeah, we debated about that. Like, I think we just like put things online for in the setup for and ask them to upload the results for ease of our evaluation framework setup. And Shu can correct me if I'm wrong, but I think that was the reason we uploaded that. And then we're planning to figure out a better way to do that so that doesn't get leaked. So the kind of servers that we have and stuff, like we will set up something where they don't see that image till the evaluation is actually running. Now, the evaluation system can try to update it on the fly, and that's the ultimate question. But it'll be more restrictive batch-based setting, and I think that's where we wanted to go for next year's challenge.
Yeah, it's very interesting questions. How much power you get out of the collective classification of the test data?
Yeah, and it doesn't. It's challenging because it's always tricky to implement someone else, run someone else's work and show the results, and then like go back and forth a lot, which was for the first iteration. I don't think. No, I don't think she wanted that responsibility. I don't think I wanted that responsibility. So yeah. All right.
Very nice.
Okay. Thank you, Yingwei.
Thank you.
So we have the next speaker, Doyup. So Doyup is a researcher or PhD student from POSTECH and Coco Brain in Korea. And his team is interesting. His team is not the top one team, but he said they didn't spend much time on this challenge, but still got the 7th place. So Doyup, please.
Hello, can you hear me?
Yes.
Hello, everyone. I'm Doyup Lee at POSTECH and Kakao Brain from South Korea. First of all, I am sincerely thanks for organizing a nice workshop and competition in CVPR21. And I'm glad to introduce our method and lessons learned on the Open World Vision Challenge. In my talk, I will introduce our main approach, contrastive regularization, which is proposed for semi-supervised learning actually. In our recent study, the contrastive regularization was not proposed to serve the open world vision task, but for semi-supervised learning. However, during the competition, we found that our contrastive regularization can also improve the performance on the open world vision data set. After our main approach is introduced, I will present the main results on the open world vision dataset. Finally, I will finish my talk sharing some lessons learned from this challenge and takeaway questions about the direction of future work for out-of-distribution generalization. First, I will introduce our main and simple approach, contrastive regularization. Actually, our method is proposed for semi-supervised learning with limited labels for a specific task. Semi-supervised learning aims to achieve high performance with limited labels while leveraging large amount of unlabeled data for a specific task. Here, an important assumption is that the unlabeled data comes from the identical distribution of labeled data in training or test situation. It is not a realistic scenario such as the open world vision task, but it's our starting point to decide to participate in the open world vision competition. The main approach is in the semi-supervised learning is consistency regularization. The method is very simple and use pseudo labeling and strong data augmentation such as random augment. First, same with the supervised learning setting, the weakly augmented views of labeled data are trained by cross entropy. Then consistency regularization makes pseudo labels by the prediction of weakly augmented views of an image. And by the pseudo labeling, a model is trained to produce consistent prediction on strongly augmented views of an input. In the fully supervised setting, the ground truth label can also be used instead of the pseudo labeling, but in our primitive experiments, there was no difference between pseudo labeling and ground truth label when the labeling information is fully provided, because a model can memorize the weakly augmented view of training samples with high confidence. One of the most important parts in the consistency regularization and semi-supervised learning is the confidence thresholding. According to the confidence of prediction on weakly augmented views of an input, the model decided whether its strongly augmented views are used in training or not. There are two main laws of confidence threshold. First, in semi-supervised learning, it prevents confirmation bias on wrong predictions of unlabeled sample. Second, in both supervised or semi-supervised learning, the confidence thresholding implements an inherent curriculum learning. If a model is confident on a weakly augmented view of an input, in other words, a model thinks that a prediction on a weakly augmented view is easy, the model progressively tries to learn a harder example with strong augmentation. Despite its popularity in our work, we show that the training with consistency regularization is biased only on the confidence samples and cannot learn well-clustered representation. So the training speed was very slow and required large number of training iterations in semi-supervised learning. So the main motivation of contrastive regularization is to learn well-clustered representation on various data augmentation, because the well-clustered representation can improve the generalizability and discriminate the power for a classification task. For its implementation, we just use the contrastive loss as the regularization on the feature representation during training. The contrastive loss is not used for pre-training and just used on the fly. First, for implementation, a projection head for lower embedding of the input is added after the penultimate feature of encoder backbone. Then after a model produces pseudo labeling on weakly augmented views, we use contrastive loss considering the positive samples as those with same pseudo labels or ground truth label in a mini batch and vice versa. Here, same with the consistency regularization, which is the most important part in the competition. Confidence thresholding is also used in our contrastive regularization. Thus, contrastive regularization moves the confidence features to aggregate the features in the same cluster. In semi-supervised learning, we found that our method significantly improves the accuracy on various SSL benchmarks and training speed. However, I will skip the detailed experimentation because it is not related to our workshop. In our paper to be uploaded on archive as soon as possible, an interesting result is related with open-set semi-supervised learning. As I mentioned earlier, assuming that identical distribution of unlabeled data with distribution of labeled data is unrealistic. Thus, we assume that out of distribution samples, which are totally different from the labeled samples, are included in the unlabeled data. The main goal of open-set semi-supervised learning is also achieving high performance on the test set, leveraging unlabeled data both from in distribution and out of distribution. In here, we assume that in distribution is CIPA 100 and out of distribution is SVHN or CIPA 10. Then we find that our contrastive regularization improves the robustness of SSL training on OD samples in unlabeled data, especially when about half of unlabeled samples are from out of distribution. The performance degradation does not occur with our method, different from the consistency regularization. As the extension of our work of robust training on open-set semi-supervised learning, we decided to participate in the Open World Vision Challenge for out-of-distribution generalization. Our main questions were two. First, can our contrastive regularization also improve the generalization power of deep learning model in the fully supervised learning setting? And the second question was whether our method can improve out-of-distribution detection performance or not. However, not limited with the conventional setting of out-of-distribution detection, which means unknown class detection, the open world vision dataset consider mixed problem of out-of-distribution generalization, such as novel classes, data augmentations, and attributes. Because of the limited time of our team, we focus on validating the power of the contrast regularization on conventional OD detection with novel classes. However, we expect that the improved version of our work can be submitted after the test server is reopened after this workshop. In the competition, we used LegNet 50 and LegNet 152 as the backbone model of the encoder, and random augment is used for strong augmentation. For out-of-distribution detection, we simply add additional unit in the output layer for unknown class and use the novel images in the training data as the unknown classes, regardless of the characteristic of the novel images. We think this approach is the most simple baseline for detecting unknown classes in this competition. And we did not use additional technique to improve OD detection, such as temperature scaling or other fine-tuning. The key was the confidence thresholding. Although it is not semi-supervised learning setting, we thought that the confidence thresholding is in consistency or in contrastive regularization can improve the performance on the open world vision data set because of its inherent curriculum for training. Deep neural networks are known to sequentially learn different samples according to their training difficulty. Then our approach considers two kinds of difficulties, samples difficulty and augmentation difficulty. By the confidence threshold, only weak augmented samples are used in the early stage of training. After the training proceeds, a model starts to learn each sample and becomes confident on its prediction on each sample. Then the model starts to learn strongly augmented samples of the confident example. However, during the training, the model does not learn strongly augmented views of unconfident samples. Strongly augmented views are more difficult to learn than weakly augmented views. Thus, the model learns sequentially according to the difficulty order by confidence threshold. In the last stage of training, after the model learns a hard sample, the model starts to learn strongly augmented views of the hard example, which is more difficult case. In addition, we assume that well cluster representation can improve unknown class detection. Let's assume two classes of in-distribution samples denoted by circles are represented in the feature space. Here, the right case has more cluster representation. Then we can assume out of distribution, which is different from the orange and green distribution is given. The baseline of OD detection use confidence score in the softmax output. Then in the right case, where cluster representation can distinguish the out of distribution sample by the confidence itself. However, in the left case, unconfident region contains both in distribution and out of distribution samples and cannot distinguish the two by the maximum softmax score as the OD detection baseline. Now we introduce the main result on the open world vision dataset. Before we submit our model on the test server, we conduct some experiments on the validation dataset. We evaluate 4 models on the validation set. First, in the fully supervised learning setting, we simply train LegNet 50 only with weakly augmented or strong augmentation. When the LegNet 50 is trained with strong augmentations, the result is rather worse than weakly supervised setting. We think that the open world vision dataset contains various hard examples, so training only with strong augmentations of hard examples, especially in the early stage of training, does not help the performance improvement. However, for the case of fixed match, which is consistency-based approach, and fixed match with our contrastive regularization, both approaches improve the performance on the validation dataset. Especially, our contrastive regularization improved about 1% of micro accuracy on the validation dataset. Then we evaluate the effects of the selection of the confidence threshold. We find that the selection of confidence threshold is important for the performance. In the ablation study, 0.7 of threshold shows the best performance on the validation set. We conclude that same with the semi-supervised learning setting, too much low or high threshold cannot make moderate curriculum learning. Then we check the detection performance of unknown class samples. We also find that consistency or contrastive regularization can improve the detection performance of unknown class samples on a validation data set than the fully supervised learning setting. Finally, we check that the effect of the size of the backbone model. We test 2 models, LegNet 50 with 26 million of parameters and LegNet 152 with 61 million of parameters. When we scale up the model size, the overall accuracy was improved both on validation and test data set. Thus, by the training LegNet 152 with contrastive regularization, we achieved 76.5 macro top-on accuracy on the test server with the single model. For our final submission, we make an ensemble of 5 LegNet 50 models and 1 LegNet 152 model. All models are trained with consistency regularization and contrastive regularization with 0.7 confidence threshold in 200 epochs. Of course, our result can be improved by further techniques such as making an ensemble of LegNet 152 models or additional fine-tuning. However, we started this competition too late, so we didn't have the time. Our final result recorded 7th rank in the final leaderboard. On the other hand, without any post-processing, contrastive regularization achieved the best result of the conventional OD detection setting, which is AURC for unknown class detection from known samples without modification. But we know that from the previous talk, AURC is just meaning of the academic and usually has metrics, so we can develop the metric for out of distribution detection. An interesting point was there was no correlation between the primary metric and unknown class detection performance. Before I finish my talk, I will share some techniques for performance improvement or takeaway question for future direction of out of distribution generalization, which is the most important topic for machine learning application in the real world. First, our method is a data augmentation friendly framework. Meanwhile, some data augmentation techniques are known to improve OD generalization performance, such as novel attributes or augmentation. We think that stylization or algorithmics or deep augment can be also applied in our framework or fine-tuning. In addition, we use the most simple architecture for encoder backbone, but model architecture is important for OD generalization. We just recent study, vision transformer shows promising results and often outperform convolution neural networks when a large scale of training data sets are available. And the two very recent studies shows that vision transformers are also more robust to various distribution shifts, occlusions, or background shift than conventional convolution-based model. The robustness comes from the properties of vision transformer, which abstract visual feature in an instance-wise manner and extract permutation and invariant representation. And self-training such as noisy student can be also used to improve the performance of generalization. In addition, the self-training is also known not to degrade the out-of-distribution detection performance. And after the submission, we analyzed some failure case to understand the room for performance improvement on the open world vision data set. We checked and plot the training accuracy of samples of each class. We find that regardless of the class imbalance problem, a model cannot memorize some classes in training data. And thus, we conducted further data analysis and derived 5 interesting findings. I will share only findings without the solution, and I think you can solve the various issues in the future research. The first finding is that open world vision dataset contains samples of different fine-grained subclasses. Here, there are 2 similar images. Interestingly, the two images are not from the same class, but different classes. The left visual object is a kind of rocket, but the right object is a kind of missile. The visual characteristics are very, very similar, but the classes are different. Only with the visual characteristic, without some knowledge about the object, human cannot also well distinguish the 2 classes. The second finding comes from that many images contain multiple visual objects, and the visual object in the image is not center aligned. For example, both left and right images are from same class, personal computer, PC. However, the right image contains additional visual objects such as monitor, keyboard, telephone, pencil, and so on. When the number of visual objects increase in the same image, the classification difficulty also increases. Let me take another example. In this case, left and right images are not from the same class, but included in the different classes. Left image is from personal computer and right image is printer. An ambiguous point is that the right image already contains the personal computer, but how can deep neural networks can predict printer class to improve top-down accuracy is open question. And the problem is going harder and harder in training step because we use randomly sized crop for default data augmentation. The default setting random crop from is cropping the 8% to 100% of resized images. Let's assume the red boxes are randomly cropped area. Random resized crop is known to make a model see various parts of image in training time and improve the power of representation learning. However, in the multiple object cases, the model cannot learn proper characteristic of each class or discriminative power of fine-grained classes, or the case of PC and printer. we can remove the randomly sized crop and replace it with center crop like the test time, but we find that the overall performance is degraded because of overfitting can occur by the samples in easy classes. The third is small object. The left and right images are from the same class gun. However, in the right image, the gun is very, very small and deep neural networks cannot easily detect and classify the image as the same class. The next finding is label noise. Same with the ImageNet dataset, we find that the open world vision dataset also contains some label noise. Thus, we have to treat this issue to improve the overall performance in the future. I think the last finding is very important for the generalization of deep neural networks. Images in some classes have little common visual features of the visual characteristic. In other words, some labels are not defined solely by visual characteristic, but knowledge about the concept or functionality of labels is required to understand the classes. Let me take an example. Below three images are from the same class. However, how can human correctly classify the three images as the same class? We can see that the three images contain different shape, color, or texture of borders. Thus, if we only use visual features, we cannot easily classify the three images as the same class. However, human can use the knowledge about the functionality of the three images, or which is that all objects in the image can filled with water. This is another example. The three images are from the same class personal computer. However, the three images contain different parts of personal computer. First image does not have monitor, keyboard, and mouse. And third image does not have the mainframe. However, we know that the three visual objects have same functionality of computer. Here, there is another example. What is the class of this image? This image is from the class of hanger. The three images are from the same class, but there is no common visual feature in the visual characteristic. However, human can infer that their functionality for the hanger human can infer their functionality for the hanger and can make a legion to classify. Then we can rethink whether image level representation learning is enough or not for out of distribution generalization of a deep learning model into the unknown situation. This is the end of my presentation, and thanks for your attention. Thank you.
Thank you so much. That's very impressive. Audience, questions?
So this is Terry. I'll go ahead and ask a question. First, I want to compliment you. You did a great job of actually embracing trying to do open set, not just optimizing close set accuracy, although a bunch of your techniques actually did that. I'm curious in terms of you're trying to determine the contrastive losses effect on open set, right? It's sort of interesting. You did very well on AUROC, right, which I've already complained about, but you still show some performance there, right? On the classes with no modification, but it was much weaker on the classes with modification and the other two categories, right? Why do you think that is? So if you go to class 20, I don't know if do you have a slide where you had all the different metrics you reported? I don't remember you having that, but.
I didn't understand the question well. Can you?
So you did well on AUROC for without modifications.
Yeah.
But there are two other categories with novel attributes and with novel augmentations. And your AUROC was not so good for those.
Yes. We agree that AUROC is not a good metric for out of distribution detection, and it's not practical, but it's still meaningful in academic research. And there are additional metric of AURC with novel attributes and novel augmentation. But we thought that when the image contains novel attributes or novel augmentation, what is the right decision process between to predict unknown, it is unknown class is or robustly predict, although the image contains the novel attribute or augmentation, a model can predict robustly with high confidence or predict it is unknown situation. So we find that low AURC with novel attribute and novel augmentation, but high AURC without modification means that all novel situation have low confidence prediction.
Okay. So actually, I believe this is in Abhinav and I have had conversations. So I think it's interesting because you may have actually gotten with attributes, you may have given it the right class. You may have said rocket, right? But it has some novel. So it's analyzing this kind of stuff is rather difficult. So as we work forward in the competition, maybe we'll have to try and refine not just the metrics, but also deal with the fact that even though they said it has a novel attribute, that maybe you still call it the dog, right? And it's still the right class, right? The belief whether or not a new subclass, a new fine-grained category is a new class is a semantic question, right? You can say it's still the superclass. So, and I think that's actually where your technique probably actually just put them in the original class for lots of those. Anyway, nice work.
Thanks.
Any other questions? If not, then thank Doyup again, and nice work. I'm gonna introduce the last speaker today, and Decheng. So Decheng, are you there? Hey, Decheng. Let me see. Hello, Decheng.
It doesn't seem to be connected by audio.
Can you hear me? Hey, Decheng, can you hear me? He's typing, but I cannot hear.
I suspect he needs to oh, now he's got a microphone icon.
Hey, Decheng, can you unmute yourself? Hello, Decheng. Hey.
Sorry.
Yeah, no problem. So yeah, let me introduce you quickly. So Decheng is a researcher from Hikvision Research Institute, which is a top research institute in China. His team is ranked the second place in the teaser challenge. So Decheng, please take over.
Yeah.
I suspect he needs to oh, now he's got a microphone icon.
Hey, Decheng,
can you hear?
can you unmute yourself?
Okay. Can I start the presentation? Okay. Sorry.
Yeah, no problem. So yeah, let me introduce you quickly. So Decheng is a researcher from Hikvision Research Institute, which is a top research institute in China. His team is ranked the second place in the teaser challenge. So Decheng, please take over.
Okay. Yeah. Thanks for the invitation from the workshop organizing committee. And I'm very honored to give a brief Okay. Can I start the presentation? Okay. I'm very honored to give a brief report to represent our team HRI How.
Research Institute, which is a top research institute in China.
Decheng, you'll probably need to mute the YouTube video. I think the live stream is playing in the background.
Please take over. Hey, Decheng.
Hey, hello. Can you hear?
Yes, please.
Okay. Sorry about that. Okay. Now I will give a brief report of our team HRI How. Yeah. Can you hear? Okay. First, I want to give an introduction of open world image recognition. This year, we have witnessed great success of closed set recognition, which means both training and test classes belongs to the same set.
Hey, hello.
Yes,
please.
Okay. Sorry about that. These days, open set recognition attract more interest due to the real application. Test samples may belong to unload classes in open set recognition task. And next is the task description of the challenge, which is a K+1 way image classification task, and the K+1 class for unloads. And there's an extra requirement of the task, that is ImageNet pre-training is not allowed, and any annotation from ImageNet is not allowed. And next is data analysis. The computation data is part of ImageNet, and the overall known class number is 413, and the total image number for training is around 484 solid. And the figure shows this distribution of images over all classes. That is ImageNet pre-training is not allowed, and any annotation from ImageNet is not allowed. And there are some challenges for the data. The firstly is lower class diversity. Samples in unloads are from diverse classes outside the 413 closed set classes. It's a challenge for the classifier to recognize these unload samples. And next is novel attributes. Samples belongs to closed set may have attributes different from the training samples. That make the classifier difficult to recognize those samples and may fuse with the unloads. The third is novel subclass. Tested images may contain novel subclasses. And the last one, augmentation novelty. Samples with augmentation novelty. That means the images in tester set may aid with noise like blur, rendering noise. Next is novel attributes. Samples belong to those sets may have attributes different from. And after we analyze the above challenges, we find that there are two key point problems of the classifier. That's the first one is robustness against null classes. The classifier should be robust to the diversity of images on both null classes and unknown classes. The second is generalization. For unknowns, the model may output high probability on null classes even for unknown instances. So it's important for the classifier to have to be generalized to unknown samples. And after we analyze the above challenges, we find that. And next we will introduce our methods. First is data augmentation. The classifier should be robust to the diversity. It's quite important to use augmentation in training for not only for the augmentation novelty in tester set, but the augmentation strategies may also help the classifier to avoid overfitting and get better performance. We select 6 augmentation strategies. There are motion blur, rendering, random fog, random brightness, and hue saturation value. This strategies helps the classifier to perform better. It's quite important to use. And the second is pre-training strategies. There are 3 pre-training strategies that we can use. The first one is pre-training models on other datasets. That means we have to use extra data to train our a model. For ImageNet is not allowed to use during training, so collect extra data may be difficult. And second one is training from scratch. Training from scratch is a convenient way to train the classifier. However, training from scratch may make the classifier easily overfit with the training data. And the last one is self-supervised pre-training. Self-supervised pre-training nowadays attract more interest due to its excellent performance in obtaining a good feature extraction model backbone. And we choose SWAV pre-training method as our pre-training strategy. Self-supervised method SWAV was first used to get a pre-trained model, which was used as a backbone for classification model. And the reasons for choosing self-supervised pre-training, that is self-supervised training performs better on few short tasks. The table shows the results of SWAV pre-training on few short tasks. When 1% labels and 10% labels SWAV can outperform supervised models. Self-supervised method SWAV was first used to get a prediction model, which was used as a backbone for classification model. And the reasons for choosing. And the next method is feature mix-up. Feature mix-up was used to augment offset samples. As mentioned before, the samples from owner set is diverse and may have is diverse, and the samples in training set may be limited. So it's important to generate offset samples. We use feature mix-up to generate new owner samples. That is, we use features in the mid layer or mid layer, and we take features from different classes and fuse them to get the new a new feature that and set the label of the new feature to unload. And the samples in training set may be limited, so it's to generate offset samples. We use feature mix-up to generate. And next we'll introduce the experiments. And for implementation details, we use the we only use the computation dataset for experiments, and no extra data was added in. And for backbone, we use ResNext. The devices we used are a server with 8 Tesla V100 GPUs, and the input images was first cropped with a ratio from 0.75 to 1.33. Then the cropped image was resized to 220. And as for the optimization, for SWAV pre-training, we train 800 epochs with batch size 4,000 and 19.6. We use SGD as the optimizer. The initial learning rate is 0.6, and we use cosine strategy. For classification model, we train 100 epochs with batch size 256, and the SGD server is used. The initial learning rate is 0.1, and we also use a cosine strategy. As for the optimization, next is the ablation study. The first line illustrated the original model without any tricks used. After augmentation, the top one accuracy improved to 74, and the unknown top one accuracy also improved much. After SWAV pre-training used, the top one accuracy improved, further improved, and also the unknown top one accuracy. And the feature mix-up helps the classifier to recognize unknown samples. The unknown samples improved to 66. Finally, we assembled the model to get a better performance. We fuse the result from 32 8D and 32 16D. And last is our final submission rank. We add the validation data in training to get final model, and our final summation achieves 81.2 top 1 accuracy and wins second place in the challenge. That is the result of the first 5 team. Finally, there are some other methods that can be used in this challenge. We listed three methods. The first is large-scale dataset pre-training, and the second is the large-scale model like transformer model used nowadays, and the last one is multimodal method. The combination of vision and language may be used for this task. That is the result of other. Thank you. That's all. And there are some other methods that can be used in this.
Thank you, Decheng. Actually, I muted him just after he finished. I'm not recommending ask questions by vocally. Maybe if you people have questions, text that question in the chat box, and Decheng, yeah, please answer. So Decheng and his team prepared a very detailed write-up. If you don't mind, I can release your write-up after the workshop. So please let me know. I guess we are finishing the workshop. Let me do the final remarks. Let me share my screen quickly. Okay, so I think this is a very successful workshop. Sorry for the shamelessly claim, but I thank you everyone, every speakers and every audiences sitting behind the scene. I hope everyone stay safe, stay healthy, and stay happy. Especially today is the Father's Day, and I hope to see everyone next year in person. So last is just enjoy the CVPR and relax. We're done.
Nice job, Shu.
Thanks for organizing.
Thank you all.
Since you said to type, I typed. He might still be answering. I can't tell. It doesn't show when someone's typing. So if not, I can reach out to him separately. So
yeah, please.
You're gonna have a hard time removing that delayed echo from the video. I don't know of any filter that's good enough to do that because of the long delay.